testing. Oh, that's way too. Hi. Do you have your Can you listen to the stream? Hi. Do you have your Can you listen to the stream?
Yeah.
Why does this sound so scuffed?
Because they will never talk with the mic so close to the mouth.
Does this sound better?
Yeah.
That's a lot better.
Testing. 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 1, 2.
Is this on? All right. So we may as well open the session. My name is Alex. I'm the SPLASH Steering Committee Chair, and I'm also here on behalf of SICPLAN. I happen to be the Treasurer and Executive Committee member. We decided, before we get to the keynote, to award one of the SPLASH Awards before today's keynote. One of the awards we do is the Most Influential Paper Award for OOPSLA. So this would be for OOPSLA 10 years ago, presented 10 years later, all right? And so, without further ado, this year's Most Influential OOPSLA Paper Award goes to Wu Le, Chengyan Sun, and Zhendong Su. So please clap and please come out. On Finding Deep Compiler Bugs via Guided Stochastic Program Mutation. We do have a committee that looks at the papers from the respective conference, in this case OOPSLA 2015, I guess, 10 years earlier. And I'll read the citation, and we'll take a photo, and then we'll move on. So please, oops. So let's just take a photo so that we don't. Yeah. So that you can relax. So this paper has made substantial contributions in establishing the automatic test generation as a very widely used technique in practice through the equivalence model inputs, or EMI technique. And EMI-based compiler testing observes which code is not executed for a given program and input to that program, and then modifies the unexecuted code and checks that the resulting program behaves identically to the original program on the same input. And the key innovation paper was to insert the new unexecuted code into the program, leveraging the MCMC search to generate various mutants that are more likely to expose the bugs. And then the general impact of these EMI-based techniques can be observed over the many papers, if you look in the last decade of work, which was the main reason we sort of highlighted that paper as one of the most influential within both software engineering and PL community from the papers that year. And it was used to expose thousands of bugs, basically, in GCC, LLVM compilers, in a variety of other languages. So the impact was actually quite wide-ranging, given the work that was only 10 years ago. So that's why it was well-deserved. And if you like, you can say a few words. It's totally up to you. I mean, otherwise, Zhendong is obviously going to be introduced shortly by Charles. So yeah. I think the first author should say something.
Yeah, so let me tell you a story. Basically, like the original story, like of the history of the EMI technique. Basically, I was like an intern at Microsoft Research back in the day, and then when I came back, Zhendong just said like, "Whoa, you have to come to my room." And then there he just like draw a piece of paper. I have this hunch that like this may work, but we have to prove that it's working. So over a couple of days, I went to hack into the spec benchmark and trying to prove that actually we can generate some sort of like candidate that can make it work. And turns out that we could make it work. We were able to find a variant of a spec benchmark program that trigger a crash in the GC compiler. Now at that time, we were not able to reduce that into a small enough program to actually report to like the bug report for GCC. So that's why we actually have to use like CCP compiler, and that like how we were able to generate a lot of like bugs. And the credit actually go to Zhendong, because what I did is just like implement the tool, and then he has to run the tools and make all the report in both GC and LVM. So I think like as a professor at that time, I have a high kind of admiration for him, like doing the groundwork to submit all the bug report to the community.
Thank you again. And so thank you. And I will ask Charles to introduce our next speaker. So please have a seat. Yeah, you have space to put it. Oh, yeah, I will put it. And I'll let Charles, our general chair for SPLASH, introduce the next speaker. Thank you.
All right, good morning, everyone. It's my great pleasure to help you to put it right here. So it's my great pleasure to introduce Zhendong as our second keynote speaker. Zhendong is a good friend of mine, at least as of this morning. And I think you won the award because I invited you, right? No, I was done independently. So Zhendong is a professor, Department of Computer Science at ETH Zurich. He's passionate about fundamental and practical innovation for building software. His research spans programming language, compiler, software engineering, computer security, deep learning, education technologies. He's a member of Academia Europaea, a fellow of ACM and IEEE, and participates in the ACM Distinguished Speaker Program. And without further ado, please, Zhendong.
So thanks for the very nice introduction, Charles, and also thanks for the invitation to be here. And also was a very nice, sweet surprise to us that we received this most influential paper award from OOPSLA. We were very happy and grateful for the recognition from the community. So I look forward to many engaging deep discussions with colleagues, friends, old and new at SPLASH'. And as the title suggests, I'll focus on compilers in this talk. In fact, I'll argue that there's nothing more exciting than compilers. My hope is to take us on a short journey of reflection and imagination by sharing some personal perspectives. In particular, let's rethink how to build much better compilers. To do so, let's think how to build that perfect compiler. Let's first take a step back, reflect a bit on the past, and then try to reimagine the future. As any discipline, it will be useful to reflect on its core mission. So let's start with this question. What is the key mission of computer science? Each of us may have our different answers. To me, the answer is to help people turn their creative ideas into working systems. And we want to do it well with low cost. In particular, we wish to have a magic ball. We speak to the magic ball about our exciting creative ideas. It produces the perfect working software for us. Software science is about building that magic ball. Indeed, software research and development is central to this mission. As a community, we have made a lot of exciting progress over the past decades. So our general field, software science, namely programming languages and software engineering, has been at the core of computer science. So we should be proud and try to keep it relevant and at the core. Toward this goal, I believe the high-level key mission of our general field is to advance and reimagine the science and practice of software construction. Science to cure our scientific curiosities, practice to have significant real impact. Now let's reflect and imagine about building software to see how things are going. Despite the great progress, the perhaps sad fact is that when one closely examines any software, bugs are common. This figure shows new and accumulative publicly disclosed vulnerabilities from 1988 to 2020 over a more than 30-year span. It could be interesting to contemplate on the many ways to read this figure. But clearly, we have a very long way from having reliable and secure software and systems. What can we do? It is clear that building high-quality software needs solid software foundations. If these foundations are buggy, any software built based on them will also be buggy and cannot be relied upon. What are these foundations? Languages and compilers, which are dear to our hearts here, databases, operating systems, and so on. We have, for example, compilers like GCC, LLVM, Rust-C, and so on, databases like SQLite, MySQL, Postgres, and etc. Let's focus on languages and compilers. and I'll focus on compilers. And as good languages have to rely on good compilers. Indeed, I argue compilers are the most important technologies. Just imagine a world where compiler optimizations are turned off. Everything will just halt. We'll ponder how to build good compilers. Good compilers need to generate correct and performant code. In fact, this tension between correctness and performance underlies all of computer science, and particularly for building good software. Building only correct software compilers is straightforward. Building only performant compilers is also trivial. But building both correct and performant compilers is a long-standing grand challenge and an enduring topic for us. So, what is the job of a compiler? It is a translator. It translates source programs to binary executables. For example, from C or Rust to x86. It's also an optimizer. It aims to generate code of high quality. Let's look at it under the hood. A compiler applies multiple transformations. We call them passes throughout the optimization process. These passes are informed by analyses which aim to determine the semantics of the compiled program. This is necessary, for example, to determine whether it's legal to apply a transformation. A compiler also uses heuristics to decide if and how certain transformations should be applied and whether they are profitable. All these components interact with each other with the goal of producing high quality code. We would all love to have a perfect compiler, one that generates correct and best performing code. The community has invested decades, in fact, getting close to not too far from 100 years of efforts to build more and more advanced compilers. Compilers are certainly getting increasingly more feature-rich and more advanced and of significant complexity. But do they get close to that perfect compiler? Now, let's take a step back and reflect on getting to this moonshot ambition. In general, most good research is similar to building taller and taller buildings. That is incremental but solid work by adding new bricks. But can this really help us get us to the moon? The moon for us is that perfect compiler. The answer would be a clear no. But then, how do we may be able to reach our moon? Let's think different. Many of us may have seen Hamming's essay on you and your research, and this particular soul-searching question he asked. What may be our answers to Hamming? What might be our individual scientific and technological moonshots? Next, let's ponder and discuss. One of my answers to Hamming's question would be the pursuit for that perfect optimizing compiler. Recall that we discussed this tension between correctness and performance. Certainly, both need to be tackled. As we know, production compilers are very complex. These numbers were from 2019, a few years ago. Now, all of these have grown a lot bigger. For example, Linux has more than 30 million lines of code, and GCC is getting very close. Thus, definitely a seemingly impossible pursuit to go after a perfect compiler. First, regarding correctness, in fact, we know quite a lot and made much progress, especially in the last decade or so. I'll only talk about briefly. Here is a concrete compiler bug in Clan LLVM, which we'll look at in more detail later. It is a correctness bug called a miscompilation or wrong code bug in compilers. These are the type of bugs we certainly don't want our compilers to have. We have techniques for compiler testing, such as CSmith and EMI. We have translation validation tools like Alive2. And certainly, we also have Concert as a realistic, formally verified compiler end-to-end. These are all essential and influential efforts that advance compiler correctness. Let me briefly highlight EMI, as that's work from my research group. So the problem it tackles is how to find miscompilations in real compilers like GCC and LLVM. It's a daunting task as they are extremely complex. Let's see how we may make a breakthrough. Let's focus on the notion of program equivalence. Here is a classical standard notion. Two programs, P and Q, are equivalent if they yield the same result on all inputs. All makes sense, but for I makes things difficult, as is typically the case in computer science. Our insight is based on a simple but yet surprisingly difficult to obtain aha moment. That is, to relax program equivalence to only with respect to a single input I rather than all possible inputs. As highlighted here, now we got rid of the universal quantifier. It may not be super clear yet, but this insight and simple relaxation led to a series of powerful techniques to validate compilers and other related systems, inspire successful commercialization. Let's consider the example from earlier. It is a simple C program. We have a struct tiny with 3 character fields, C, D, and E. We have a function foo that takes a struct tiny x as its argument. If x.c or x.e not equal to 1, the function aborts. In the main function, we have a local struct tiny s with all its fields set to 1. We then feed s to foo. The code then returns. It is clear that above the boards should not be triggered, and the code should return normally. When we compile it using clan at -0, everything works correctly as expected. However, when we compile it at -01, the produced executable aborts with a core dump. Thus, we have a serious compiler bug, a miscompilation of wrong code. The bug turned out to be quite tricky to fix and took the developers a couple months to figure out the root cause and fix the bug. Now let's see how the relaxed definition of program equivalence, EMI, provides a powerful suite of techniques to find serious compiler bugs. Like the one we saw, it is probably not quite clear yet what is the connection. Now let's see. We assume a given program P and input I for program P. We profile the execution of P over the input I. We mark those executed statements as green and those not executed as red, and record output O. Then we mutate the program P by keeping the executed statements unchanged, but mutating the unexecuted or dead statements. For example, we can delete some of the dead statements, inject some, or both delete and inject. The only requirement is that the mutated programs should still compile. What interesting properties do these mutated programs have? As a matter of fact, they're all equivalent to the original program P with respect to the input I by construction. This should be quite clear, I believe, as we didn't change the executed statements. Now we can use the mutated programs to help find compiler bugs. If we produce a mutated program P prime and output of P prime on the same input I is different from the original output O, we have found a bug. And this is guaranteed, no false positives. Now let's see, how do we find the bug in clan that we saw earlier? Here is the original program P, which does not take any input. That is, it is a closed program. For this program, clan behaves correctly, both under -0 and -01, so the original program did not trigger the bug. We profile the execution of P, for example, using a coverage analysis tool such as GCOV. We notice that all the abort statements are not executed as expected, that is, they're dead. Thus, it is possible to produce a mutated program with some of the abort statements deleted, like this one shown on the slide. Interestingly, this mutated program now triggers a clan miscompilation under -01. Imagine that this mutated program is still very large, Typically, it will be helpful to shrink and simplify it before reporting it to the compiler developers. This process is called test input reduction or minimization. One may use tools like delta debugging, creduce, or Persis for this purpose. This is the one that was reported by us after test input reduction. You may wonder why Clan miscompiled this simple piece of code at -01. It turns out to be quite interesting. First, when calling the foo with the parameter s in the main function, optimization called GVN, global value numbering, decides that it's better to change the struct with 3 character loads into one 32-bit integer load. Turning 3 loads into 1 load sounds like a good thing to do. However, another compiler pass, SROA, scalar replacement of aggregates, notices that the 32-bit integer load reads past the struct's end because the struct has only 24 bits. Therefore, the compiler decides by mistake that the code has undefined behavior, although the original code does not have any undefined behavior. Once the compiler decides, whether correctly or incorrectly in this case, that a piece of code has undefined behaviors, it is free to do anything to the code. In this case, it decides to remove the 3 initializations. Recall that local variables in C and C++ are not initialized and may contain random values. Thus, it is possible for the C or the E field to not contain the value 1 and trigger the abort. EMI has led to a suite of effective techniques which have helped find a large number of critical bugs in both GCC and Clan LLVM and other commercial compilers. We have made GCC and LLVM a lot more reliable, and the effort is continuing. Correctness is well defined, and we have solid methods and tools. Thus, it's more or less tamed. Performance, on the other hand, is a totally different story. So, how do we pursue our dream of that perfect compiler? It seems an impossible pursuit. But despite this general impossibility, it benefits to consider this moonshot objective. In particular, I hope to advocate the following perspective. Let's systematically quantify how far our current compilers are from the perfect. Through this, we can identify the critical and profitable gaps and try to bridge them. In particular, although we do not have a perfect compiler, we can still have certain expectations of its behavior. As some initial steps, we have used several expectations to gauge the gap. Let's discuss some of such expectations. This is the figure we discussed earlier. A compiler has various transformations or passes which are informed by analysis and guided by heuristics. So what are these core expectations? First, heuristics play a crucial role in optimizing compilers. Therefore, we expect a perfect compiler to have optimal heuristics. Second, a perfect compiler should not miss any optimizations. For example, all constants will be folded, or dead code will be eliminated, and so on. Third, a perfect compiler's behavior should be monotonic. In particular, given more information, it is expected to do a better job, at least not worse. These are a few examples that we have explored. There are certainly many, many more. We use these 3 expectations to guide our exploration. Next, let me briefly motivate them. First, perfect heuristics. The community has made significant efforts to improve heuristics used by compilers. But how good are they from the optimal? Does it make sense to spend more efforts doing this? If we could replace the current heuristics with perfect ones, we can answer such questions. This is precisely what we aim to do. Second, transformations. Decades of work aimed to improve compiler transformations analysis so they better optimize code. But how far is this optimization process from the perfect? How can we quantify this gap and identify what is missed? This is another challenge we aim to tackle. Third, compilers are expected to be monotonic. That is a core assumption in compiler research and development. That is, The more information a compiler has, the better code it should generate. A perfect compiler should certainly behave this way, but what about production compilers? This is the question we aim to answer. In the efforts I'll present, I'll highlight the conceptual, technical, and practical contributions with fresh perspectives, novel techniques, and practical relevant results. I'll now present the first piece on perfect heuristics. In particular, we focus on optimal function inlining from SPLASH' 2022. We were happy and grateful for the best paper recognition. There have been decades of work on improving inlining in compilers and inlining heuristics. However, none on the problem of optimal inlining and quantifying the window of opportunity. We took upon this challenge. So, what is inlining? It is a transformation that replaces function calls with the bodies of their callees. For example, we can inline the call to bar, resulting in the code on the right. Inlining expands the scope of many intra-procedural optimizations and analysis. Here, after inlining, we're able to infer now the if condition to be always false. Thus, after inlining, the compiler can easily eliminate the redundant if statement. And finally, fully simplify the code. On the other hand, overly aggressive inlining is bad, can lead to code duplication, as illustrated on this slide. Therefore, good inlining heuristics are important and need to balance such benefits and cost. With the right inlining choices, there is significant potential for improvement. Here we see the size reduction in the SPEC 2017 benchmark suite with inlining enabled versus disabled and up to 3 times improvement. This initial work focused on binary size because it's less noisy than performance measurement. First, as we saw, inlining is clearly an important transformation. Compilers use heuristic to decide which calls to inline. Our question is, how far are these from the optimal decisions to minimize binary size? To do this, we cannot naively try all combinations. The number of candidates is exponential in the number of calls. Any non-trivial program has a huge number of candidates. In this work, we show by carefully considering the structure of the search space, it is possible to drastically prune it and make the exhaustive search feasible for many more programs. I will not discuss the details here. It is a recursive partition of the call graph and leads to sound and drastic reduction from 2 to the hundreds down to 2 to the tens. Using our methodology, we can now measure the gap between the heuristic and the optimal. This plot shows the size increase due to heuristic inlining decisions from LLVM. The baseline is the optimal minimal size. The data set is based on the SPEC 2017 benchmark suite. We can see that in around half of the data points, the heuristic already achieves the minimal size. However, there are also cases with room for great improvement, the largest being an almost 300% size increase. A quick summary of this work along the 3 dimensions perspectives. Are heuristics perfect? Technical, drastic search space reduction. Practical, optimal inlining dataset for many applications. In fact, the same methodology could and should be systematically applied to other heuristics. The second work examines from the angle of perfect optimizations, also from SPLASH' 2022. We're grateful for Distinguished Artifact Award. It tackles the problem of detecting missed compiler optimizations. 2 difficult challenges. First, to determine what is possible to optimize. That is, what would the perfect compiler do? Second, to determine what our testing compiler has failed to optimize. Our insight for general and effective method is to use DCE, dead code elimination. So, what is DCE? It's the removal of code that cannot be executed or whose execution does not affect a program's behavior. In this example, the if statement body is dead, as the condition is always false, therefore it can be eliminated. The store A to 1 is also dead, as A is never read afterward. Thus, we can eliminate both. A perfect compiler will generate the code on the left, essentially return 0 in x86. However, real compilers fail at optimizing this simple piece of code. GCC generates code for the if statement and the dead store. Does LVM do better? It does not. In this work, we use whether dead code is missed to help detect diverse missed optimizations. But why do we care about DCE? What makes it interesting for our purpose? Our first insight is DCE is what we call an optimization sink. Removing dead code simplifies the remaining live code, which in turn makes analyzing and optimizing it easier. Therefore, compiler passes running after DCE have potentially a higher chance of doing their job. Compilers also try to repeatedly remove dead code. Thus, these passes also affect DCE quality. Also, there are other passes that DCE directly depends upon. Thus, a failure to eliminate a piece of dead code can be an indication of a failure in some other passes. In this work, we developed a method for making DCE failures easily observable. We can use DCE as a signal to detect these missed optimization opportunities. This is a quite simple and general insight, an idea which already inspired applications in other settings. But how can we detect that there is a piece of dead code in a binary? We can use multiple compilers to tackle this problem. Let's look at an example. Here we see the control flow graph of the code generated by two compilers, namely LLVM and GCC. We can highlight which blocks of the graph correspond to which if statements. Doing so reveals that LLVM eliminated the first if statement, therefore GCC has missed an optimization opportunity. But how can we do this matching? The compiler's output is just a sequence of assembly. So we don't have, in fact, this correspondence. Our third insight is to make this detection trivial by massaging the input program. We insert something in the source code such that if it remains in assembly, we know that the corresponding basic block, for example, if statement, was not eliminated. We call these markers. Here, we implement them as function calls, and there are many other ways to implement this. Looking at GCC's output, we see that both markers have survived. But in LVM's output, only one remains. Therefore, we have detected a missed optimization in GCC. To quickly sum up, our length of dead code elimination is the following. Given an input program, we insert markers in all divergent control flow points. We compare the set of surviving markers from different compilers. If there is a difference, we have detected a missed optimization. In all examples, I use GCC and LVM as two compilers. But the method is flexible. We can compare different optimization levels of the same compiler, like GCC at -03 and 01, or different versions of the same compiler, like LVM 19 and 20, and so on. We can now answer the question of how good are compilers at DCE, and how do they compare against the ideal one that eliminates all dead code. We use a corpus of 10,000 programs generated by the random program generator CSmith. There are around 3 million dead blocks in these programs. A perfect compiler would remove all of them. But GCC and LVM at the highest optimization levels missed around 5% of these dead blocks. This demonstrates that there is room for improvement. As a benefit of this analysis, through analyzing different compilers and compiler versions, We also found and reported many missed optimizations in GCC and LLVM. A quick summary of this work along the 3 dimensions. Perspective, are optimizations perfect? Technical, DCE as a general lens or technique. Practical, many detected missed compiler optimizations. This next work focuses on the 3rd expectation, namely, to what extent are compilers behaving monotonically. It was presented at last year's PLDI. As users of compilers, we expect them to behave monotonically with respect to the information that they are given. That is, if the user provides more information or analysis such as value range is improved, we expect the generated binary to improve also, or at the very least, not becoming worse. Let's look at example. Here we have a function that compares 2 integers and another function bar that calls it. We can also see the x86 output. Imagine, as a programmer, we know some additional information that the compiler does not. For example, x is always greater than or equal to y. We can include it in the program via this annotation. The compiler can use this information to generate better code, as shown here. But do compilers always behave in this expected manner? Or can it happen that adding more information can result in worse binaries? Let's look at another example. This example contains more complex control flow, nested loops, and if statements. But as we can see, the compiler simplifies everything, doing a very good job. Because the outer if statement condition is always false, let's now try to do something like what we did before. We'll use the fact that argument in the h function call is always non-zero. We'll inject this information in the callee, again, using an attribute. Surprisingly, the compiler now generates way more code than before. Looking at the control flow graphs, clearly something has gone completely wrong. Our goal in this work is to find such cases automatically. Let's see how we do it. Starting with a seed program, for example, produced by a generator, we want to do the same thing as in the examples. That is to inject some information and test if the compiler is getting confused. We start by executing the candidate and observing its behavior. For example, what value do its variables take at various program locations, similar to our examples? Next, we inject this information back into the program. We use compiler built-ins. Again, like in the examples, the new program is semantically equivalent. Now we have 2 versions of the same program. We can compile both and use the oracle to decide if there is an interesting difference. If there is, we have detected an issue of non-monotonicity. If not, we can repeat the procedure. I'll now briefly explain the various steps in this pipeline. For the refinement step, we use compiler built-ins, as I mentioned. For dead branches, the built-in unreachable informs the compiler that the particular source location should never be reached. For value ranges, we use the same built-in, but guarded by the derived range. For example, we know V is between the lower bound and upper bound, therefore its negation is unreachable. The last step involves an oracle. We can use function markers as we did with DCE earlier. If a marker is eliminated from the original program, but not from the refined program, then the injected information has hindered the compiler. Using such a framework, we can now study the prevalence of this issue. We use, again, 10,000 sysmiss programs. Our goal is to measure in what percentage of these programs are degraded given additional information. We see 9% degradation for LLVM and 17% for GCC. In total, we could trigger this behavior with around 20% of our test programs. And some of the degraded programs are common to both compilers. Clearly, production compilers can be very counterintuitive, and it is a challenge for our compiler community to make them more predictable. Using this end-to-end pipeline, we identified and reported quite some issues in GCC and LLVM. Most have been confirmed or fixed. The issues were related to a wide range of passes. For example, various analyses, peephole optimizations, and loop transformations, and so on. In this work, we measured to what extent a compiler is behaving monotonically. For reachability, namely, we use dead code and value range information. Our recent work at PLDI 2025 also has relevant results on alias analysis, but I will not discuss in detail here, and happy to chat about this later. A quick summary of this work along the 3 dimensions. Perspective, a compiler's monotonic, technical, introduces a fully automated detection pipeline. Practical, many detected misoptimizations. The 3 examined expectations: perfect heuristics, perfect optimizations, and perfect utilization of information. And a recap of the highlighted perspectives and the results. Toward that perfect compiler, these are some new but early steps. I believe this is a long yet fruitful journey to reimagine how to build compilers. The quick takeaways: compilers are foundational for trustworthy and performant software. It is a moonshot ambition for the community to build that perfect compiler. Our perspective is to understand the gap from the hypothetical perfect optimal compiler, and I discussed several efforts along this direction. I argue that the future compilers should have intelligent heuristics, be interactive, finding what is critical information and interacting with the user, or more powerful analysis, and perform both low-level and high-level domain-specific optimizations, so being a universal optimizer. Of course, there are many, many conceptual, technical, and practical challenges and hurdles. So, the dream is to build that ultimate optimizing compiler, turning the dragon into the super dragon. I cannot express how excited I am about this quest and direction. Thank you. I'm happy to take any questions now and discuss with folks later.
Okay. Thanks, Jintong, and if there are any questions.
Hello, is it my, oh, great, it's on. Just a simple question. You had a table with bugs you reported and bugs that were fixed. What's the gap in between? Did other people fix it or just nobody fixed it?
That's from the EMI part, the earlier part.
Yeah, from the earlier part you had a table.
Yeah, with a couple thousand bugs, right?
Hmm.
Yeah, so maybe a bit more. So the numbers were from a year ago. First of all, the numbers should have been updated.
Yes.
And now they're getting close to 3,000. And I think the bugs fixed also close to 2,000 also. And of course, there are some bugs which are very difficult to fix. And some bugs are, there's some duplicates as well, maybe reported by us, maybe also by some other teams as well, or maybe by the compiler developers themselves. And some bugs are not interesting to the compiler developers. And of course, inevitably, sometimes they also report some invalid bugs as well, because our misunderstanding of whether a piece of code has undefined behaviors or not. And that's a tricky issue. Yeah.
Thanks.
Thank you for that question.
Hi, Sam Westrick from NYU. You mentioned two ideas in the talk, optimality, often like optimal performance, and also predictability. And we want to understand what the compiler is doing. And these two, I think, can be in tension with each other. For example, as a performance engineer, I might want to understand what the actual code is that's running. But if we have an optimizer which is optimal, a small change to the input program might drastically affect the generated code and completely ruin any intuition I have about what code is actually running. So I was wondering if you could just say a little bit about that tension, this optimality, which is kind of not predictable, and yet this desire to have a predictable compiler.
Yeah, I think that's a great question, right? And although maybe I will, answer this with one bug from the security perspective, bug in quote, right? So, I think as a developer who's very conscious about security, not to write secure code, and we're very, very careful. And sometimes compilers assume that the code, when compiles the program, has no undefined behaviors, may remove whatever you did for secure engineering, right? So that's also tricky. I think it's connected to what you said. And I don't really have good answers to that. And but again, a perfect compiler will be able to give us both, but in reality, not, right? And that's, I think, really a challenge for our community to think how to move forward, right? So I don't really have answers to this question. Yeah, thank you.
Thank you.
All right, maybe the other side.
Thanks for the great talk, Ben Titzer, Carnegie Mellon. So one dimension that you didn't mention is compilation time. And so I often work on JIT compilers, and they have quite different designs. They might be a baseline compiler, there's no intermediate representation, and they might do speculation. I'm curious if you thought about applying some of your work to JIT compilers and what the issues are and what you might think are things that we could move forward with.
Yeah, Ben, yeah, thank you for that question. Yeah, so not from the performance side, not from the compilation side, but from using EMI, the method of EMI to test JIT compilers. We have done that. Some work published at the SOSP a couple years ago, how to find, I think, bugs in hotspot, in J9, and so on, right? Performance side, I really haven't thought too much about this, but happy to chat with you offline. Yeah.
Thanks.
Here.
Yes, my question is not so technical. It's rather I want to have your view on the intersection between the compiler research, compiler work in the LLM era. So one thing is, there is a tremendous important work on compilers for machine learning pipelines, but I'm more interested on your view in the other direction.
That's right.
So if the compilers of the future are these LLMs, and we have the Meta LLM compiler, and the authors of that paper published at GCC compare the quality by using the BLEU score, which is string comparison.
Right.
What's your view on this?
Yes,
What's the future? What should we do? What compiler communities?
Thank you for that question. I'll point to this particular word, intelligent. So for the part that I mentioned about optimal function inlining, now we have perfect data set. That is, for a call graph, what is the best inlining decision that we can use? Now we have this perfect data set, and we'll be able to use this, perhaps, train a machine learning model that to replace the heuristics within compilers. Inlining is one, and we can gradually replace all the heuristics by such models, perhaps. And that's what I call intelligent heuristics, right? Yeah. So I hope that's an okay answer to your question.
Also, I think your methods that you have developed, or others in the community, about testing compilers should play a key role. When we have LLMs trained to play compilers, they need to be evaluated in a different way than they are evaluated today, because that community, I'm saying, has no idea about. I'm exaggerating, of course, but using a string comparison, string matching heuristic to value the qualities.
Yes, yeah. I think that's a very hard question, right? Because there is based on, one thing I did not mention, that for the EMI line of work, we focus on integer programs. I did not mention any thing about floating point. And in machine learning, floating point, that's really at the core, right? And so that means we have results that's different by a little bit. We don't know whether that's expected or not, right? So that makes it hard. But so I think maybe the biggest challenge is how can we develop very good, reliable oracles to tell whether something has gone wrong or not, right? Yeah.
Hi, thank you. Michael Koblenz, UC San Diego.
Yeah.
So I'm thinking about a lot of this work from the perspective of property-based testing. And it seems like a lot of what you've done is you've identified very clever properties, and then you cleverly produced generators, and then you found a bunch of bugs. And so I'm wondering what lessons we can draw about property-based testing. So, for example, do you typically find it's very hard to come up with a relevant property, but once you come up with a property, then you find a pile of bugs?
Yes.
Or possibly, actually, it's really easy to come up with a property, but most of the properties don't produce a lot of bugs.
Yeah.
And so I'm wondering what your insights are about how to produce good properties,
Very
how
interesting
to see
question.
which properties are good properties.
Yeah, very interesting question. So EMI is one property, right? It's actually a very simple property. It's easy to capture how to realize it. Makes, I think, make it powerful and also general to be able to detect a lot of it. It's actually a hyper property. And I know the recent work that people explored using property-based testing to find bugs in compilers, right, by capturing some expectations of what things should be. And I think that's interesting work, interesting direction. But again, it's always this balance, right? That is how easy it is to express the property, how powerful this can be used. And so, yeah. So I think it will be interesting, perhaps not treating the compilers as a black box. What we have been doing is treating compilers as black box. And I think in order to use property-based testing, we probably need to go inside to make it white box, right? To maybe to say, look at a particular like a transformation, then it will be clear, similar to translation validation, right? We can view that translation validation like Alive 2, maybe as a very successful example of property-based testing. Yeah.
How dense is the space? Do you find when you come up with a property, you typically find a pile of bugs? Or you typically find that property wasn't very good, we got to try a different property?
I guess EMI, again, is a very universal property, right? And the property-based testing work that I have mentioned is very, I mean, you have to think really hard to come up with very specific property locally, right? Perhaps even about the program that you want to test. For this particular program, what property you expect, right? So that's what I'm aware of.
Thank you.
But happy to chat with you also offline. Yeah.
I'd like to ask a question that's in the same general direction as the last one from this side of the room, thinking broadly about using machine learning and other approaches that can write code automatically. I wonder what you think about the prospects to move to a world where compiler passes just aren't written by people, they're found by search processes, maybe even search processes that have integrated formal verification, so that maybe counterintuitively, by leaning into AI, we could actually increase our assurance in the quality of the code while lowering the costs of building it.
Yeah. Adam, thank you for that question. That's a great question. And recently, during one of my PhD student defense, and Till, who did, I think, most of the work here, at least for the second part, and one of my colleagues from ETH, machine learning colleague, asked us, why don't you try to learn a full crack compiler fully automatically, right? It took us a long time to try to argue and debate with the colleague that is hard, it's impossible. But I think he was not convinced, right? So maybe just adding that note here first. And I think if we do have a reliable oracle again to know whether the compiler is doing the right thing, and that's a big if. And if we have that, I think we can couple that with the AI technologies to be able to make compiler building, having heuristic is always easier because usually heuristic means any choice is fine, right? It's really just for the transformations and so on. And that's hard. So for that, we need a reliable oracle, right? Maybe, again, coupled with maybe a proof of the correctness of the transformations. Yeah? So I think that will be very fruitful, and, but there are some really hard challenges we have to think about. Yeah.
Thank you.
Leo Marker, Jane Street. Looking at the how point on this slide, you talked about heuristics, you talked about optimization. I think this is the first time that I'm seeing interactive design. I don't think you talked much about that. Could you say a few words about what you mean by that?
Yeah, that's right. So it's more related to the recent work that my student Michel Weber has done, is on understanding alias analysis impact on compiler optimizations at this year's PLDI. And what we found is, for the spec benchmarks, if you remove alias analysis totally, the impact was minimal. But there's a small percentage of these alias queries are supercritical. So then the question becomes, how can we identify this small percentage of information that is critical for compiler optimizations? And then try to get this information maybe by interacting with the user, or maybe try to improve our analysis, right? So maybe that's, I think, one way to look at it. But in general, beyond alias analysis, I think that's true as well, right? So that is, how do we figure out the most critical questions that will make compilers do a much, much better job? Let's not try to build maybe a fancy analysis. Let's try to ask the user, is this true or is not true? Right? Maybe they are just to follow upon this. And I know we have a lot of colleagues here who work on formal verification and so on. But imagine a piece of code that has been formally verified. We put so much effort. We have the specs. Why don't we try to have this information not just thrown away by the compiler, but being leveraged by the compiler? I think that would be very, very nice to have.
All right. Hi. So my question is kind of the opposite of the property testing one. So you've shown us 3 example results, which started from, let's examine if a given optimization method is implemented correctly or optimally by these compilers. And I wonder if you can go even more black box. And what if I just have a program that I know is not compiled into something that is as efficient as I would expect it to be, but I have absolutely no idea which optimizations are the ones that are at fault there. So
Okay.
in that case, so can you go even more black box? Can you start from, oh, I don't know, because this is not fully black box, right? You still make assumptions about, okay, these are the optimizations that happen inside the compiler.
Yeah, thank you for that question. Let me try to answer that based on my understanding of your question. And perhaps what you are thinking is, well, I put this very vaguely as a universal optimizer. That is, usually when we teach compilers to our students, we say, you should think really hard about the data structures and algorithms, and then pick the right data structure, pick the right algorithms, and then give the job to the compiler. But I will argue that's not. Let's try to, maybe as you said, right? One step back, and we try to ask the compilers to do even more, to be able to discover these kind of high-level deficiencies in our code and try to optimize it.
No, I mean, I meant more like you don't, the compiler internals are the ones that you wouldn't make any assumptions about. Like, what if you don't know that, oh, this program is compiled into something inefficient because that code elimination doesn't fire correctly, or, oh, because the inlining is not optimal. You just, all you see is that, okay, there's this program, there's a reasonable, in my head, I have a reasonable way that it could be compiled efficiently, but yet what comes out of the compiler is not efficient, but I have no idea which transformations in between are at fault.
I see. Yeah. I think a lot of times we as developers already maybe try to do that, right? Try to work around or together with the compiler, right? And I guess as you suggest, maybe we should think more, right? How to be able to tell, suppose we have expectation. Yeah, usually I mean, we can do we do a lot of profiling already, right? Profiling gives us a lot of information to see whether there's anything surprising can guide us, right? Yeah, but I think I see your point, and I think it's an interesting direction to think more. Yeah, thank you for that question.
Maybe the last question.
John, yeah.
So, John Hughes from Chalmers. I have a question about your dead code elimination. So you wanted to have ground truth to compare against, and you obtained that by saying if a piece of code is eliminated by any compiler, then it's dead. But that, of course, is an under-approximation of the real dead code. Yes. However, if you were to take the generated programs and then test them, then code that is executed is definitely not dead, and by doing that, you could get an over-approximation of the set of dead code. And you can imagine that maybe if you used a good concolic testing tool, something that aims to improve coverage of the tested program, you might be able to get a test suite which reaches almost all the non-dead code. That might give you an overestimate to compare against. Have you considered using that?
Okay, yeah, John, yeah. Thank you for that question. First of all, let me clarify before I answer your question that for the study we did, we used C-Smith generated random programs, and these programs don't take any inputs, which means the runtime gave us the perfect information, right? So that's the optimal. We compare against that optimal.
Okay.
I just want to clarify that aspect.
You talked about looking at the dead code detected by different compilers and comparing that.
Yes, right. So that's, in practice, of course, you know, like by running the runtime information gave us the perfect information, right? To tell us which blocks are dead, which blocks are not. We use that as a reference. But for bug finding in practice, it's because the production compilers are now close to that perfect compiler. So we want to focus on those interesting bugs. So that's where we say, oh, if GCC is able to do this, but LLVM cannot, then that's perhaps more interesting. Or vice versa, if -03 GCC can do it, but -01 was able to eliminate a block, but -03 couldn't, that's a surprise. So mainly it's for programmatics.
Okay, thank you.
Okay, yeah.
All right, so this concludes the keynote session. Let's thank Zhendong again for the wonderful talk. All right, see you in the next session.
I'm afraid the next session we will start starting now. And I have an announcement to the speakers of this session. So I'm going to wave my hand around 10 minutes after your talk. So please finish appropriate time. And around a few minutes before your talk begins, come to here and get your microphone. Okay, then let's start the first talk of the compilation 3 session. The talk will be, by the way, talk will be given by David Moon. He's going to talk about the syntactic completions with material obligations. Okay, let's start.
Hey, I'm David Moon. I just finished my PhD at the University of Michigan, and today I'm going to tell you about our paper, Syntactic Completions with Material Obligations, which is the focal chapter of my dissertation. The goal of my PhD work has been to support live programming experiences. And when I say live, I mean semantics on tap. Your program semantics should be freely available and queryable whenever you want them throughout development. Of course, this isn't the full picture. All of these semantics are downstream of your program's well-formed syntax. This means the flow of semantics can be compromised by syntax errors. A naively implemented parser might simply fail on the first unexpected token and produce no structure, in which case we no longer have a live program. Instead, we just have some dead text. To keep the semantics flowing, modern parsers will try to recover from unexpected tokens so that they can structure as much of the program as possible. Often this involves some form of implicit repair around the error site. Panic mode is a common and especially simple form that limits itself to deletion-based repairs. On encountering an unexpected token, a panicking parser will drop tokens around the error site until parsing can resume normally around the dropped tokens. Panic mode is easy to implement, but it can lead to large skipped regions of code with no semantic feedback. More sophisticated methods consider the full space of textual repairs. Here, a drop-down menu enumerates and sorts different possible repairs to the first line of the program, where repairs now combine insertions in green with the deletions in red. The benefit of incorporating insertions is that this minimizes skipped regions of code, as shown in the first 3 repairs. On the other hand, there are often many similarly structured insertion-based repairs, as shown in the last 4. It's often unclear a priori how the parser should rank such choices, while asking the programmer to disambiguate can be distracting and risk information overload. In this paper, we consider repairing errors not just with text, but with a more abstract set of what we call syntactic obligations, which I'll now demo in our prototype editor, Tall Tyler. All right, so here's Tall Tyler. It's just almost like a text editor, but you can see that there's some funny shapes on all the tokens. The first and most common kind of obligation is the operand obligation. Just like holes in structure editors, they act as placeholders for missing terms. We can understand missing terms more generally as an inconsistency in multiplicity. In each of these positions, we expect one term but find 0. Dually, it's possible to expect one term but find many. If I delete this comma here, Tyler inserts an infix obligation to join together P1 and P2 into one term as expected by the surrounding parentheses. And notice how this abstracts over the various possible operators that strictly textual repair-based approaches would consider individually. With such natural defaults at hand, it starts to become reasonable for the parser to choose a repair and materialize it to the programmer such that they and the system are on the same page. Sadly, this is often not the case with IDEs today. There are still many situations where there isn't a natural default, which typically arise when have to do with the placement of delimiter obligations. It's perhaps natural here that when I delete the delimiters to leave obligations behind in their place, but the choice is less obvious when inserting forms in the middle of your program. So here I'll start to retype this line over here. And here Tyler has chosen to insert the matching in at the end of the line, which is what we want in this case, but it could have been that I meant to bind the following expression to my new variable. In that case, I can simply insert the in delimiter where I want it, and Tyler will remove the now redundant obligation. There's one more kind of obligation in Tyler's toolbox. Here, Tyler has inserted a prefix obligation to buffer between the expected pattern sort and the provided type sort. These appear rarely in this particular language, but you could imagine postfix obligations appearing often in a language like Haskell when constructing the pattern that begins a top-level definition. Okay. So that's it for the demo. Powering Tall Tyler is a novel parsing framework dubbed tile-based parsing because raw tokens are first molded into tiles before they are parsed into terms. A tile-based parser consists of a melder and a molder. The melder is an error handling generalization of operator precedence parsing, or OP parsing. And there are many things to love about OP parsing. It's simple to implement and runs in linear time. The method generalizes naturally to handle errors. And especially nice is that it enjoys the bounded context property, meaning it's possible to parse any subrange of input knowing only the single tokens on either side of that range. And what this gives you is parallelization and incrementality for free. And so I think this makes OP parsing an especially appealing foundation for modeling program editors. Meanwhile, the molder assigns molds to tokens so that they can be melded. Later, I'll talk about how this eases the grammar restrictions of traditional OP parsing and why I think molds are a better primitive to design for than the items that underlie methods like LL and LR parsers. First, let's talk about melding, in particular how melding extends OP parsing with obligation-based repair. Here I'm referring to the method as first described by Floyd in the 60s, which goes beyond just infix operators, as OP parsing is commonly understood to be limited to today. This method described by Floyd is an early pioneer of shift-reduced parsing. So we're going to go left to right, stopping at each of these points, and construct our term bottom up. And the spiky tokens at the ends are marking the start of input and end of input. At parser generation time, we can derive a set of precedence comparisons between symbols, which we'll use to drive the decision to shift versus reduce at each point. So at the first stopping point, we have a less than comparison. And what this means is that let begins a right descendant of the start of input symbol. And if we see a less than, then we're going to go ahead and shift. We see another less than, so we're going to continue shifting. And then now this time, we see a greater than symbol. And what this means is that we've reached the end of a term. The colon is the delimiter that closes the X. term. And so we're going to reach back, find the nearest less than symbol, and we're going to reduce that and continue comparing the tokens on either side. And we continue like so. In this case, we encounter an equals relation, and this means that these are matching delimiters. And like less than, we'll use this to shift. We'll interpret this as a shift decision. And we can continue that similarly. And then finally, we reach the end, and we are happy. OK, so now let's consider how we can handle errors when doing this. So I'm going to consider parsing this input, but I'm going to take out these two tokens here. And let's see what happens when we reach that gap. So traditional OP parsing, it would find that there's no precedence comparison connecting the let and the num type. And so it would get stuck, and it would fail, and that would be that. But if we recall from the previous parse, we saw that were there an x and a colon, then we would be able to just continue parsing. And so one of the generalizations we make to OP parsing is to generalize single-step precedence comparisons to multi-step precedence walks. And so in this case, the tokens that we generate in between the compared tokens are the completed insertions that we use to repair the code. Now, so far, this is not that different from just purely textual repair. But we can, with our language of more abstract obligations, we can instead choose to pick these natural defaults instead. So here I might replace the x with an operand obligation and the colon with an infix obligation. Or I might go further and just combine them into a prefix obligation here. And if we take a look at these various options, Tyler would choose the top option over here because it inserts the fewest obligations. But whatever choice is made, we show in our paper that for any grammar where we extend that grammar of tiles with additional grout forms that can be used to that can be used to serve as these default completions, we can show that melding is sound. The output is always grammatical, which is actually not the case for traditional OP parsing, and it's also total. Output is guaranteed. OK, so that's melding, and now we'll touch on molding. And given that melding is sound and total, one nice thing about the molder is that we can make choices between different possible molds simply by the same trick of minimizing obligations. So I'll show you an example here. So here we have this is the grammar that we use to that we represent in this language, and you'll notice that there are multiple parentheses that appear in this grammar. And if this were a purely textual grammar, this would actually fail to be an OP operator precedence grammar because the appearance of the open parentheses across different positions causes there to be ambiguities in the precedence comparisons that you can make between that opening parentheses and other tokens. So what we're going to do here is we actually assume that these are just unique and distinct tokens, and we are going to simply try each of these options. And because we have this sound and total guarantee, we can simply inspect the results and see which produces the least obligations. And in this case, when we are considering which of these open parentheses choices to take, we see that the pattern parentheses produces the minimal obligations. So that's tile-based parsing. It looks like I'm out of time, but check out our paper for also our user study in which we considered how participants respond to obligations appearing in the editor. And yeah, there are some interesting takeaways about directly rejecting obligation-based repairs that I hope you check out. And that is all. Thank you. Yep.
Awesome. Thank you for your talk. A question that I have is about, again, the grammar, the restrictions that you mentioned about the grammar. Are there any other things that a programmer would have to do in terms of, I don't know, massaging the grammar so you get nice or proper results? Right, I see. And the other question that I have is about grammar composition. So you have two different grammars and you want to compose them somehow. Do you have to do anything about that? Do you get that for free still? Are there any possible complications that you get when you're trying to integrate two different languages based on this?
There are some, let's talk about that more offline.
No worries. No worries, no worries. We can talk about it later. Yes. Yeah.
Is there like volume? Oh, wow. Okay, cool. Thank you for the intro. I am unfortunately not Mohammed Usman Tariq. No, it's all good. It's all good. He couldn't make it. I'm Shiv Sundram. I'm a fourth-year doctoral student at Stanford, and today I'll be talking about tiling recurrence equations. So this is work I did with Fred Scholstad, my advisor, and it was led by Mohammed Usman Tariq. He couldn't make it due to some unforeseen engagements, but I want to be clear that this is all his creativity. I also want to be clear that he is young, he is brilliant, and he is applying to PhDs this fall, so please look out for his application. So as I said earlier today, we are talking about recurrence equations and linear solvers. A linear solver is just a set of recurrences like the Cholesky decomposition shown here. It solves a matrix system AX equals B, particularly when A is symmetric. Now when A is not symmetric, you can use a different algorithm, the LU decomposition, with the recurrences shown here. And if your matrix is triangular, you can use a triangular solver, either with multiple right-hand sides or a singular one. If you want to solve it through inversion, you can use a TR-TRI, recurrences shown here. And these are all just sort of the code names that the linear algebra community likes to use for these fancy linear algebra routines. And they all have a similar syntactic structure. It's similar to the matrix multiply equation, which I show here to the right, in that they include 2D index tensors, summations, and element-wise operations over matrices. And if we look at it, we'll notice that there are similarities, deep similarities between linear solvers and matrix multiplies. The most fundamental one is that they're both compute-bound. They require a lot of flops. Most solvers are accordingly O of n cubed, just like a matrix multiply. They benefit from cache tiling and register tiling and writing stuff in handwritten assembly. But there are also some very fundamental differences between the matrix multiply and the solvers. So first of all, there are no output dependencies in a matrix multiply. You can see over here that to calculate Cij, you can calculate all of the elements independently. So there is a sort of embarrassing parallelism to them all. This is not the case in a direct linear solver, which is a recurrence. In a recurrence, like the one shown here, future outputs depend on previously calculated inputs. You can see over here that Ri depends on Ri minus 1. That means the outputs have dependencies, and that limits the parallelism. Another fundamental difference, the one we're most interested in, is how these algorithms get tiled. When we tile a matrix multiply, the tiles are identical. What do I mean by that? If I take this output matrix here, decide to tile it up, every small tile is basically just going to run a smaller matrix multiply, which means all tiles are really just smaller versions of the larger operation we are trying to execute. But this is not the case in a linear solver. When I tile a Cholesky decomposition, for example, we end up having to calculate this blue tile and this green tile separately. And as you can see, the blue and green tiles have different shapes. One's a triangle, one's a rectangle. And calculating them requires different operations, which I've shown to the right in those funny code names again, SYRK, POTRF, gem, that's a matrix multiply, and a triangular solve. I'll talk about those later. These tiles are different, so optimizing these are actually just much, much harder than optimizing a plain matrix multiply. So how do we execute these solvers in the real world? Well, the easy answer is just use a library. You can use BLAS or LAPACK. We've had these since the beginning of time. They're really well optimized. So they'll get you the performance you want. But if you're stuck in the case where you have a direct linear solver, some fused or composite version, and nobody implemented it or put it in BLAS or LAPACK, you're kind of screwed because it just doesn't exist and you'll have to implement it on your own. Alternatively, if we want generality, we could use a recurrence compiler. So the user would just input the equations, we would compile them to C code or something, and that'll give us some nice generality, and in, say, sparse cases, we'll get handwritten performance. But for something really dense and tiled, we're just not going to be able to beat the handwritten assembly that's been written over 50 years. Now, ideally, we want a solution that gives us both, right? We want the generality of a recurrence compiler, and we want the performance of a library, and we want to interpolate between the two. So how can we do that? If we take a recurrence compiler, introduce tiling optimizations, and then build a system where we can execute certain expensive but commonly found tiles with a library function, we can get both the generality that we want and the performance. So we built a system called RepTile, short for recurrences plus tiling, which takes in an arbitrary set of user-provided recurrences, tiles them up, associates any tiles with available library functions, and then emits code with performance that matches or outperforms state-of-the-art libraries, in our case, MKL. We'll use the same Cholesky decomposition as before as our motivating example. And as I said, the blue and green tiles implement completely different operations. They're not matmols, they're something else. Once we tile the algorithm, and this only happens in the tiled case, like other linear solvers, the Cholesky decomposition is going to exhibit a recursive call stack. We see that when tiled, Cholesky simplifies into 4 subtiles right here. There's a recursive call to the Cholesky decomposition, POTRF is the code name, a symmetric ranked update, a triangular solve, and a matrix multiply. That's just your gem. And the cool thing is that each one of these is associated with a recurrence. So there's the input recurrence for Cholesky, of course, and the recursive call is going to have the exact same equation, but then each one of these other 3 tiles have equations associated with them too. And the main thing I want you to take away is that these equations are all completely different, right? So you can't just do some recursive tiling, you have to do something a little bit more sophisticated than that. What we want our compiler to do is discover what these subrecurrences are, associate them with tiles in a library, and then just generate the code. The other interesting thing is that all of these tiles are actually hierarchical. So we can do more than just unroll the recursion down one level. The TRSM, the circ, and the gem are all hierarchical operations. So in this case, we can decompose the TRSM, the triangular solve, into a gem and a smaller triangular solve. At that point, we want our compiler to either take these tiles, the leaf tiles, and execute them with a library call. Or if the tile is very small or a good library kernel doesn't exist, or the overhead of invoking a library via a function doesn't really justify the performance benefits, we want to take the compiler approach and generate explicit loops. So in RepTile, our compiler, that's pretty much what we do. The user is going to provide 3 things. The first is a list of recurrences expressed in a mathematical syntax. Very easy to describe. The second is going to be information about our tiling strategy. Which dimensions do we want to tile over, right? The size of our tiles, et cetera. And then the third is more interesting. It's actually a repository, a sort of bank, if you will, of library functions, which are decorated with their associated recurrences. And this is going to let us compile individual tiles of recurrences into tiles of library calls. We're going to generate each tile, deduce what its associated recurrence is, shown in the middle, and then we're going to lower each tile one at a time to generated loops or a library call. So how does this compiler actually work at the equational level? I'll walk through an example of how Reptile would do this for a Cholesky decomposition, as I've shown kind of before, same triangle. I've shown one version of Cholesky to the left. The main takeaway is that it's a triply nested loop, right? So it has a 3D iteration space, which I'm just going to visualize with the cube to the right. So each tile is also going to be 3D, so it'll just be smaller. So I'll represent every tile with just a smaller version of that cube. So there's the global iteration space, and here's just a subspace of that. And what we want to do is essentially intersect this abstract representation of our solver, of our recurrence, of our Cholesky, with this 3D tile. And if I do it for this one specific tile here, I'll just choose a random one out of the bag. What I'm going to get is the symmetric ranked K update. It's a mouthful. Of course, this, in theory, should be done by analysis of loops in old compilers. That's how we used to do it. But for very arbitrary inputs and loops, that's just not a very easy problem to do. These things get very complicated very fast. We'll instead show that if we have the corresponding equations, that's all we need. We don't need to reason about loops at all. It's just the user can give the equations, we can analyze the equations, and then just go straight to loops after that. No other program analysis is needed. And we generally think it's a good idea to do this, right? To sidestep difficult analysis programs and just reason on a higher level, more mathematical representation. So instead of this code, I'm going to instead take these recurrences and intersect it with the bounds. So what does it actually mean to intersect equations with bounds? Well, I'm going to take this cube right here and replace it with the inequalities that represent that subtile. There's 3 of them because it's a 3-dimensional iteration space tile. And then when I intersect them, something really interesting happens. The outer expression for this very specific tile, those who are mathematically inclined may realize what's happening, the outer expression just disappears. For this specific tile, it doesn't matter, it's never going to execute. We're left with these sub-equations right here, and this is the exact equation that we see in the symmetric ranked update. So I'll walk through that a bit more step by step to kind of intuitively explain why this outer expression is just disappearing when I intersect with this tile. So imagine we have this equation here. For the sake of simplicity, I'll remove the subtraction. So then all we're left with is a summation and a square root on top of it. Let's say it's just 8 elements. And I want my first tile in blue over here to execute the first half of the summation. And our second tile will implement the second half of the summation in green. It'll finish up the accumulation. Now, once we finish those 2 half summations, what we can't do is what I've just shown on the screen right here. We can't take the square root of each and then add them together. Why? Well, simple mathematics. Square roots don't distribute. They can't distribute over the inner summation, so it's not going to work. And that's sort of why the tiles all have to be different. What you have to do is take the first tile, and that's free to do the summation, as before. Have the second tile, which comes after, finish the second half of the summation. And then you can have the second tile execute the terminal square root, which it can do because the second tile just finished the entire accumulation. So that sum is essentially ready to be executed. So you have one tile that's just doing summations or multiplications, and then you have a second tile which is doing the same thing for the second half, but then doing the square root on top. And the result is that the first half and the second half are different tiles, and they simplify to different recurrences shown here. We do this for every abstract tile, and that lets us discover this recursive call stack that I showed before with lots of different equations at every level of the hierarchy. So what I showed you was the intuition behind our core algorithm, and for the details on how we generated the candidate tiles, how the intersections are implemented in the weeds, how we handle dependencies, please see the paper. So to go to our evaluation, we evaluated our Reptile generated code against MKL for the Cholesky, LU, and triangular solves, and we got 1.4x speed up. Now, the ironic and kind of funny part about this is that we're evaluating against MKL as our baseline, but when we linked to external functions for individual tiles, we linked to MKL calls as well. So we got better performance by mkale, but by using the library against itself and simply discovering a better schedule. So basically just 1.4x speed up 1.1 to 1.4 for all the major solvers. For less commonly used solvers that you don't see in the wild, we notice we got up to 2.7x, and that makes sense because they don't get optimized as well as, say, a matrix multiply. We did compare against a matrix multiply, and we got no speed up whatsoever, which makes sense because artificial intelligence and yeah. And then we also evaluated this against some non-solver occurrences just to show it's possible. So in this case, we have some bioinformatics algorithms, and we were able to get about 1.6x speed up over the handwritten baselines. Yeah, so once again, I am not Usman Tariq. This is Usman Tariq. He's taking this to some pretty ambitious directions, and of course, he is applying to graduate school this fall. And we do believe that this path gives us, this work gives us a path to portability over architectures for direct linear solvers. We're looking at compilations to GPUs, to supercomputers, and generating custom spatial architectures from the recurrences themselves. And that's it.
Hi, Shiv, great talk. I was wondering, since you're using SMT to solve the intersections, are all the terms generated for these kernels affine? And if they are, do you foresee any useful programs in the future that would generate undecidable intersections?
Right, so we don't imagine running into problems there. There's a lot of interesting problems like Floyd-Warshall, which aren't exactly affine, they're like pseudo-affine. We could perhaps run into problems there. We actually simply used SMT because the interface is just so clean and it's really highly optimized. The correct thing to use, from a purist point of view, would have been integer set library or something like that to do integer set intersections. So I don't foresee anything for solvers. For pseudo-solvers like Floyd-Warshall or graph problems, maybe. I'd have to look into that.
Gotcha. Thank you.
Yeah.
No worries, my name is underlined. But
he's going to talk about the structure analyzing the data for our program. So please start.
Yes, thank you very much. So welcome to the presentation and hello everyone. And first of all, I want to start with a small question. Who in here ever had the pleasure of working with the R programming language that's part of the title? Okay, so a couple of you, maybe that's a small bias in the people coming to the talk. But for those of you who don't know, R is a programming language that's mostly used in research for statistical computing. So by people who want to do data science, who want to do visualizations, data cleanup, do some model statistical testing, so on and so forth. And hence, it's mostly used by non-programmers. So by people who are expert in statistical domains like physics or social sciences, and who have not had any classical training in software engineering or programming, as most of you here probably have enjoyed in their past. And in practice, R provides these users with many powerful capabilities. There's a huge collection of libraries. There are many functions that R provides that are really helpful for explorative data analysis even. But on the other hand, these powerful reflective and dynamic capabilities might cause some difficulties when we try to analyze the language statically. And now you might ask, why would we even want to analyze such a language statically? So first of all, there's a lack of sophisticated static analysis tools, and I hope I don't have to tell anyone here what static tools can bring in terms of merit and support in the development cycle, but also in the analysis. We've heard a couple of talks at OOPSLA as well regarding to the benefits. And now if we want to write such a static analysis tool, we are confronted with the challenge that the language specification or the language that we're dealing with is incomplete. So we basically only have the interpreter, and the way that the language is defined in the interpreter is a way to guide us through how we should interpret some of the semantics, some of the more interesting and more esoteric edge cases that are present in the language. And now, yet again, the question is still open. Why would we even want to undergo such a challenge? The people seem happy. Well, if we look at recent studies that analyzed how well these R scripts in the wild as part of peer-reviewed and published publications to actually reproduce, we come to a very shocking number that, again, there were several studies, some of which reported slightly different percentages, but all of them are in the same range, that roughly 75 to 80% of these scripts not just don't reproduce, but usually don't even execute to completion due to various problems. And if we're tasked with such a problem, even though the language is very dynamic and we might want to analyze it dynamically, if the script doesn't even execute, well, then we're only left with the abilities that static analysis provides us with. And if now the average R researcher wants to analyze these scripts, wants to find out what's going on and wants to repair them, he's actually challenged with another problem. Now here we have such an average real-world R script. It's completely unreadable, but that's not the fault of the authors. That's probably the size of the beamer. But still, in this R script, there usually are a lot of things happening, and a lot of things happening that might not even be directly related to each other. So in this script, for example, we have various models and figures that are created, and this is completely normal in the R community, that of course you want to have several visualizations, not all of which depend on the same data set or depend on the same operations. And so with all of this happening in the same script, they are usually also hard to comprehend. So it's not just that you can just execute this script to maybe reuse a figure from the publication, or maybe just try to see and realize what the authors actually did. It's also that when you just look at the source code and try to play static analyzer yourself as a human, it's very hard to really analyze and find out what these scripts are doing. And again, if you try to reuse parts because, for example, you found a nice visualization or there was a nice statistical operation that people did in another paper, to just extract this operation is usually very difficult because it might depend on other operations done previously in the script, somewhere way above or somewhere completely else. And so again, if you want to reuse or extract some parts of the script, that's very hard. So okay, I hope I convinced many of you now, or hopefully maybe all of you, that there's merit in statically analyzing the language. And then if we try to do this, we are again tasked with the challenge of the dynamicness and all of the, for the statistical part, beneficial features that R provides. And just to give you two examples why this is hard to analyze, we have, of course, as in many interpreted languages, string-based evaluation. So you can hear these are real-world examples, and if you want to, you can look at the slides and check out the original papers that use these things. But you can, of course, use string-based evaluation, and yes, other languages have them as well, even though ours has a couple of tricky things that make it even more challenging to analyze it here. But the main thing is that these evaluations happen in many user scripts because they tend to reuse patterns that people have used before them, and they're usually used for things where they're not even necessary. So here, for example, they only read a variable. I mean, technically period could be anything, but in the context of the script, they're only trying to read a variable, and for that they construct a string that they then evaluate in the current context. And you might think that this is still sane. There are other examples which are even crazier, and this is a lot of code, so we focus on the important parts. Here we can see two functions, one of which is called pullcat, the other one is called upcat. And what upcat does, it takes the body, so the implementation of pullcat, and redefines the first expression that we see here to now read bins equals upbins, which is an open reference in the other function. So once we execute upcat, it will effectively redefine the definition of the function to now have a different implementation, which then reads upbins from the closure and will change the semantics. And of course, now this is a still very systematic example. It can do anything, whatever you like. And in general, there are many more of these examples. In R, you can redefine the assignment operator, you can redefine if, you can redefine while, you can even redefine the opening brace if you like. And so if you want to do the static analysis part, in one way or another, you have to deal with all of these things. Okay? So what did we now do in our work? So first of all, to underline the claim that the existing static analysis solutions are insufficient, we effectively looked at 31 existing implementations that in one way or another do static analysis. Those who are stricken out here are no longer maintained. And of course now we can take the time, the remaining 10 minutes of the presentation, to just look at the table and parse it. You can do that in the paper if you like. So we quickly summarize the existing findings. So analyzing all of these solutions and the capabilities they provide, we found that effectively the existing static analyzers offer no interprocedural analysis, and given that I hinted at that you can redefine the assignment operator, that you can redefine ifs and everything, in R, in the end, everything is more or less a function call, so just like ignoring them or performing summaries on these function calls already is a very, very gross over approximation. and they usually ignore most or even all reflective and dynamic features of the language. So if some of the things like the body assignment I've shown you earlier happens, they just give up or do some assumptions and then continue their analysis. And in general, another problem is that most of these tools, again, they don't even provide a way to extend on the analysis, so they calculate some results and then they use it internally, and the only thing they expose to the user is effectively a short information about, hey, this variable is global, or hey, this function does this and that, and there's no way to really extend on these existing capabilities, and many more. And with our work, we effectively try to address all of these things in one way or another. So how does the analysis that we actually conduct work? So we don't have the time to go into the gritty details, and again, I point you to the paper for this, but on a very high level, we follow a pipeline architecture where we, of course, first parse the R code, then we normalize it to abstract away from version dependencies and some of the nitty-gritty details that the R language has. Then we perform the data flow analysis. I have another slide for that to go into a little bit more detail what this magic stack implies, and then we can use these results to do further analyses. And as a proof of concept in the paper, we implemented a backward program slicer. Again, I will talk briefly about that later. So effectively a way to condense the scripts to just focus on a singular figure or on a singular statistical test, for example, right? But in general, the pipeline architecture that we provide is general enough that you can theoretically extend it with many more things. So once we have the data flow and control flow graph that we generate, we do many more analyses that are possible. For example, a dependency analysis to find out which figures are created, where statistical tests happen, what library versions are used, and so on and so forth. But now, how does the actual core analysis that we provide work? Well, the challenge with R is, again, that there are so many reflective features that intertwine with each other. There is lazy evaluation, which may entail side effects. Again, any operator may be redefined, so you need full context information to be even weakly aware of what could happen in a certain scenario. And we do this by taking a simple piece of R code, transforming it into the normalized AST. Again, you don't have to follow and read all of that. This is just the simplified normalized AST of this code above. And what we then do is we effectively do a tree walking interpreter approach where we take the AST, do a stateful fold, and incrementally construct the data and control flow information of the program by repeatedly applying all of the passes that we essentially have, intertwining data flow, control flow, and any other abstraction all the time to be able to even find out what various operations in the program are doing or are maybe able to do. And hence, for example, here we have the assignment to the @ symbol, which is represented in the normalized AST over here. And for this, we start by building a small data flow graph, which is visualized here. We track additional information, and then we subsequently incrementally construct the data flow graph, doing the fixed point iterations over the tree structure as well by combining the results. And here you can see the add graph again. This is the body of the function, stitching effectively the subgraphs of each subtree together until we reach the final data flow graph of the program. And again, this is a very, very brief summary of what we actually do in the paper and what we actually do in the work. So again, if you're interested in that, please check out the paper, right? And now to get to one real-world application of what we can use this analysis for, I already hinted at the static program slicing approach. So if we again go back to our wonderful R script, which does several visualizations and several modeling operations, what we can now do if we take on the hat of a researcher and we are, for example, just interested in a single figure or in a single statistical test, we can pick this figure or this statistical test, and the program slicer will reduce the script to just the parts which are relevant to produce this specific figure, okay? And so in this scenario, now this is the real-world example, but again, it's hard to read on the beamer. In the real world, when we do this, we achieve average reductions of 80 to 90%. So if you're aware of program slicing, these numbers are really high, and this again underlines how interestingly written and exploratively written maybe these scripts are. But what this number means effectively is when we are interested in just a single figure in the script, on average we only need 10 to 20% of the original program, and that again speaks to how it may be easier to understand these programs than if you're only focusing on a specific figure. There's also an extension for Visual Studio Code and Positron that you can use, but we stick to the research part here. So in general, we now have this analysis, but without a normal or a fundamental specification of the R language, it's very hard to know whether what we're doing is actually correct, right? I'm just telling you that we have 80 to 90% reductions, but the slice could just be wrong, right? And so we conducted an extensive evaluation that I'm now showing in a simplified form because we did multiple steps to at least empirically underline the correctness and the performance of our approach. So simplified, what we did is we took all R packages on CRAN, which is the comprehensive R archive network that were available at the time, and we did took a couple of R artifacts. We conducted our analysis, we measured timing information, of course we did that repeatedly. Then we sampled slicing points in these scripts, conducted the program slicing, again measured the timing and the size reduction, and from there on out did the performance evaluation. In here there's still no correctness evaluation, so this is now just the performance part where we measured the speed of our analysis and came to roughly 150 milliseconds on average per package and 580 milliseconds per script file, which is mostly due to the fact not that script files are technically more complex, but they're usually longer compared to the average package file. And again, the slicing reduction I was referring to earlier, here we achieved an average reduction of 88%, but we still don't know whether the slices are correct. So, or the data flow graph in that matter. So what we did, we did multiple correctness evaluations, but just to show you one of them, you can find the others in the paper. We took a couple of these scripts. We tried to find scripts which were already executable or which we transformed manually into an executable state that were also deterministic. In there, we labeled points of interest according to the paper. So we looked at the paper, found the visualizations, and labeled them within the script under the assumption that these are possible the points that real-world researchers would be interested in slicing for. Then we ran an automated instrumentation execution to effectively arrive at the ground truth, so what the script is supposed to execute in a given scenario. And then we took the same scripts, the same point of interests, conducted our analysis, computed the slices, reran the slices to check whether the output for the figure or statistical test in question is identical. And if it is identical, then we know that at least the slice contains all of the information that is required to reproduce the same output. But again, we could just return the full program and would still be fine because the full program is always the trivial slice. So what we then did with the correct slices is we shrunk these slices to find the minimal subset of slices, and I'm speeding up to get to the point. What we found in the end is that of these correct slices, we achieved roughly 99.7% of correct slices, which means for 99.7% of these points of interest, we produce the identical result to the complete script execution. And precision-wise, we achieve a precision of roughly 94%, which means if the resulting slice, let's say, has 50 lines, we usually only have 2 to 3 lines that are superfluous and redundant in some way that we included just to be safe. So, and we are also reducing the runtime of the actual script. And we also compared to the state of art, but again, for the sake of time, you can check this in the paper. So just to recap, we looked at the state of the art, we propose a new data flow analysis framework, we propose a program slicer that can then be used to make the script more easily comprehensible. And if you're interested in more of these things, here's a link to the project, which is open source, and a link to the paper, and below there is my email. So if you're interested, feel free to reach out. And with that, thank you. No worries.
Yes. Yes, perfect. Thank you very much for the intro. Okay, is this thing on? Yeah, good. Okay, last session before lunch. Let's make this quick. I'm indeed Michael Schröder. I'm a PhD student at TU Wien in Vienna, Austria, where I'm supervised by Jürgen Zito. And this is our work on static inference of regular grammars for ad hoc parsers. This is an ad hoc parser. It's a parser because it's a piece of code that makes some decisions based on the contents of a string. It's also called parser. Yeah. It is ad hoc because it uses only common operations. It doesn't use any parser combinators or any parsing frameworks, right? It uses string indexing and string comparisons and string length and some asserts and so on. So if I ask you now what is the type of this input variable s here, then obviously you would say it's a string, right? In Python we can even give it a little type annotation here to indicate that. It's very cute. Now if the type here is indeed string, then I can put any string into the function, right? So let's try this out. Let's put in the string a. Okay, nothing happens, kind of as expected. Then we might also well put in the string b. Oh, we get some kind of error. Okay, maybe this parser really wants to have A's in there somehow. So let's try the string AB. Okay, we get a different type of error. Maybe the B's are the problem. Let's try out the string BB. Okay, that works again. So clearly there is something more complex going on here. It doesn't just take any kind of string. And if we look at the code a bit, we can quickly figure out that S cannot just be any string. It has to be one of a set of possible strings, right? I mean, those strings that don't make the program go wrong in some way. And this infinite set of strings is a language, and a language can be succinctly described by a finite grammar, or in this case, equivalently by a regular expression. So S can be any string as long as it is accepted by this grammar or matched by this regular expression. This grammar describes the language that this parser parses. Now the question really isn't what is the type of S, it should be what is the grammar of the string. For this parser we have the answer right here because we thought about it a bit, but is there a way to answer this question for any other parser and maybe ideally without having to manually reason about it? Introducing Panini, our end-to-end automatic grammar inference system. Panini starts with ad hoc parser source code written in some general purpose programming language like Python, which is translated into a language agnostic intermediate representation that we call lambda sigma. Lambda sigma can represent all relevant parsing operations, but it's simple enough to enable complete refinement type inference. This allows us to synthesize string constraints over a parser's input string, which are then abstractly interpreted into a concise string grammar. Now in the remainder of this talk, I will walk you through each step of the back end of the system, starting from the intermediate representation. I won't be able to always go into so much detail, but I can hopefully give you a flavor of everything that is happening. It's kind of a whirlwind tour. So we begin with our parser translated from its Python source code into the lambda sigma intermediate representation. You can kind of think that this is somehow possible. Okay, so lambda sigma is a simple lambda calculus in a normal form. Common string operations and other functions of the source language are given merely as axiomatic specifications. So lambda sigma has a refinement type system in the style of liquid types, and this is also how these axioms are specified, directly in the type system of lambda sigma, using logical predicates to express the semantics of these string functions and of other operations in the source language. Note that these axioms do not have any implementations. They merely exist as type specifications because they don't need to have an implementation because lambda sigma programs are never actually evaluated. They only exist for type inference. They're the perfect programs. So doing type inference, the refinement type system generates so-called verification conditions, which are logical constraints whose validity entails the correctness of the inferred types. You would usually use an SMT solver to prove these valid and thereby prove your inferred type correct. Now, what often happens is that these verification conditions that you get along with the inferred type signatures, that they contain what's called kappa variables, which are placeholders that represent unknown refinements that the type inference mechanism just couldn't figure out on its own, that you first need to solve with some other means in order to get the final type. Now, various procedures exist to do this, like predicate abstraction and diffusion algorithm as implemented in Liquid Haskell, for example, and is also implemented in our system. But for a certain class of kappa variables, the ones that we call grammar variables, those that represent string input refinements like here, the existing approaches are insufficient. What we need is specialized grammar inference. And the key insight that allows us to find suitable assignments for these grammar variables and thereby input grammars for ad hoc parsers is that the top-level verification condition for a parser program will always be of this form. It will always be an implication that is quantified over the input string variable s, where the consequent is this string constraint phi that precisely captures all parsing operations performed on the program by the program on this input string. Now, by simply taking the string constraint phi itself as the solution for the kappa variable, the verification condition trivially becomes a tautology, and then the string refinement exactly captures those inputs that the parser accepts. So, okay, we can just use this string constraint as the grammar, right? But the problem is the string constraint isn't really a very practical grammar. It's a first-order formula. It has all these quantifiers. It's very annoying. It's as big or maybe even bigger than the original program. So we need some kind of technique to maybe turn this string constraint, which contains all the information that we need, into some form that is more concise and practical. So of course, we're going to use AI. That's right, abstract interpretation. So in this case, specifically, abstract interpretation of ad hoc parsers represented by first-order formulas. So the situation is this, right? We have some parser program P with a partially inferred refinement type and an incomplete verification condition that contains the string constraint phi, which is a first-order formula over a string variable s that captures the semantics of the parsing operations performed by P on s. Now, the concrete semantics of a first-order formula phi could be seen as all the possible assignment sigma of free variables to concrete values, such that phi is valid given these assignments under some model of the refinement logic, and in particular, such that the assignments for the variable s are all the values of the language of P. Right? Trying to compute this concrete semantics directly will generally result in an infinite set of values. I mean, this is what we had in the beginning, right? There's an infinite set of possible acceptable values for the program. Now, hence our desire for an abstract semantics that produces a finite approximation of this set, such that this sigma hat here is an assignment of free variables to abstract values. In particular, sigma hat of s is now a grammar describing perhaps a subset of the strings in the language of P. Now, to realize this abstract semantics, we introduce in our paper a novel variable-focused relational semantics and a quantifier elimination procedure. We give some specific semantics for string operations and so on. You will find all the juicy details for how exactly this works in the paper. I just want to quickly talk about the abstract domains that we're using. So the completeness of a finite approximation produced by an abstract semantics depends on the underlying abstract domains. And again, I can't go into detail about each of these, but I do want to point out that our underlying string domain, so what we use to abstract over infinite sets of strings, is based on regular expressions. So this means that we are inherently limited to inferring regular grammars only. For parsers of super-regular languages, we must necessarily under-approximate. But this limitation is in some sense modular, right? If we enhance the power of our abstract domains, then we might enhance the power of what we are able to infer. So given our abstract interpretation machinery, we can now turn this unwieldy string constraint into concise, practical grammar. Hooray. So how well does all of this work in practice? We prepared a benchmark data set by writing increasingly complex parsers for increasingly complex combinations of regular language operations by hand, arriving at 204 regular language parsers written in Python. Here are some examples of these parsers, and to be able to compute precision and recall measures, we also manually derived a ground truth grammar for each parser. The most important result, Panini exhibits 100% precision because it never over-approximates. So it always infers a sound grammar. And it shows 93% recall overall, as it only occasionally under-approximates and only for some programs with loops. This has to do with insufficient invariance. Panini has a success rate of 92%, meaning there are some parsers for which it cannot return an answer at all. And these error cases and the under-approximations, they're due to usually insufficient invariance or maybe our abstract domains are a little bit too weak. And these are things that, again, are kind of modular limitations. We hope to improve these because of the underlying mechanisms we use and then improve also our metrics here. Now, compared to other approaches, Panini occupies a unique spot. So there are a number of other grammar inference or grammar mining systems, as they're often called. These come mainly out of the fuzzing community. Their operating requirements are quite a bit different to ours because except for Panini, all of these approaches are dynamic, which means they require some kind of program execution. And most of these other approaches also require pre-existing positive input samples in some way to bootstrap their inference. So meaning you already need to know kind of part of the solution before you even begin to figure it out. So in our paper, we have some detailed benchmarks, but I mean, to summarize, Panini produces better grammars and is much faster than its competitors. I want to point out that Panini is also the only approach that can infer grammars with 100% precision. I mean, that is kind of by construction here. Panini is also, orders of magnitude faster than these other approaches. No surprise, because we don't have to execute any programs. Now, even though Panini is, already pretty great in its prototype stage, there is a lot of future work to be done. So I didn't talk at all about our front end. So currently we have a prototypical Python front end, which supports a subset of the Python language. Of course, we want to increase this subset, eventually supporting all the features of Python to be able to translate them into our intermediate representation. We want to add more source languages, maybe R, for example. And we also want to extend our intermediate representation. In particular, we already have some extensions ready to be merged in to add polymorphism and user-defined data types, which makes the language a bit more complex, but still enables easy refinement inference and also allows us to more easily improve our front end because we can, more easily translate high-level concepts. We also want to improve invariant inference. That's also a bit of a performance bottleneck and a bottleneck for our results. We want to improve the qualifier extraction heuristics we have, maybe integrate some external solvers, and of course we want to increase the strength of the abstract domains that we use. We want to increase the numerical domains so we can maybe also then infer better loops. And eventually we want to add support for super regular languages. So this is Panini. You can get it here. Please take a look, read our paper. I'll be here at the conference. I'm happy to answer any questions you have now or later over lunch. Thank you.
So could you please elaborate a little bit more about the after influencing the grammars? So I understand your idea is to infer grammars, but if you find the grammars of that program, then how do you use that?
So what would you use this for? Yeah, so okay, one use case would be testing, for example, right? If I have an input grammar, I can generate fuzz input. So what often happens, so these ad hoc parsers really are kind of code snippets that are, you know, within any other kind of program usually. So if you have any program, usually you process some kind of input, and what you would do is you would have some syntactic checks on this input maybe at the beginning, right? And so if you want to fuzz test the program, what often happens is that the fuzzer kind of immediately fails in the input checking stage, right? But if you know your input grammar, then you can generate syntactically correct inputs and then maybe figure out some semantic bugs in your code, right? What you can also do is you can just infer this grammar and show it to the user as like a type annotation, and so the user can say, oh, actually the code I wrote doesn't really parse the kind of thing that I wanted to parse, right? Or you can say, oh, now I have a regular expression, I can just replace my parsing code with a regular expression, you know? There's all kinds of interesting use cases that happens once you're able to automatically and kind of freely infer input grammars for your code.
Thank you for the talk. So you said that currently you infer like regular languages, and you want to do like the super regular languages. Can you tell a bit more about that, and like what's the next target? Like what kind of, like more precisely, what kind of language you want to you're working on now?
So I mean, right now, because we're using this regular expression-based string domain, inherently we're limited to kind of this, like theoretically, right? So what you see in practice is that, I mean, a lot of these ad hoc parsing constructs that are in like source code are often kind of regular or slightly above regular. They're not fully context-free. They're often maybe not even deterministically context-free, but there are some kind of things in between, like this classic hierarchy, where you have a mostly regular language that has some patterns that are maybe context-free or maybe even context-sensitive. I mean, a classic thing you have is like you have something where the format of your string, you have some kind of a token that kind of determines the length of the next token and so on, right? These things are technically context sensitive, but they are very limited in a way that we could maybe imagine being able to infer these kind of certain patterns in these languages, right? But it's hard to kind of really nail down precisely what this is in terms of the classic, like, you know, regular language, context-free language, context-sensitive language hierarchy, right?
Grammars for actual programming languages, for instance? Or it's like
well, that's very difficult. I mean, a lot of programming languages, they are even like, you know, more than context or whatever, or like there's, you know, isn't like Perl like Turing complete the parsing or something like that. Like that's tricky. Like, and it's not intended to infer like the grammar of some huge complex thing where you usually would have a parser generated by a parser generator anyway. You already have a grammar for that, right? The idea is this is for small snippets.
Yeah, but some actual languages like write their parsers by hand, like they have citizen parsers and.
Sure.
So.
Yeah, I mean, yeah, it would be cool. I mean, that would be eventually, if we could do that, it would be very good. But I imagine that would be very difficult because these kind of really super context-free grammars, also the programs that implement them get then very complex very quickly. Like this whole idea here depends also that these kind of input programs are written in a way that kind of aligns with their language, right? If I write a parser for a regular language, and the parser itself is going to exhibit mostly regular behavior, right? If I write this parser in a way that is like super complicated with like a lot of recursion, maybe exhibit some kind of Turing complete behavior, some indeterminism, then it's going to be also hard to statically analyze it, right? And so I foresee that as a big challenge if you want to analyze like really big parsers, you know.
Okay, thanks.
by Sivanitha Ravi. Thank you.
Can everyone hear me? All right. Hello, my name is Savita. This is my presentation on our paper, An Empirical Evaluation of Property-Based Testing in Python. This work is done with Michael Koblenz, and we're from UC San Diego. All right, let's get started. So property-based testing was first popularized in the functional programming community with libraries like QuickCheck, but now it has spread to other languages like Python. And what property-based testing allows you to do is test multiple inputs with the same test body. So in this example, we see a property-based test written in Python using the library called Hypothesis. And we have this test of this list max function, which finds the maximum of this list, and then we check that that maximum value is greater than or equal to every other element in this list. And with every property-based test, there's two components. The first one being the generator, and this is what actually produces all of those inputs. And then we have the property. And this is what we check when we're working with, when we want to assess our test. And Hypothesis is very popular in Python. So there was a 2023 survey by JetBrains, which found that around 5% of the developers they surveyed used Hypothesis. And if we tried to extend that to the entire population of Python users, that ends up being around 500,000 users. However, property-based testing can be difficult to actually do in practice. So in this example, we have our PBT version of our list max method, and then we have a regular example-based unit test version. And in our example-based unit test, we have our specific list that we're working with, and we can check the exact value of our max is 8. But if you look at our PBT, you might notice that this property doesn't actually assess the total correctness of this max function because we don't even know if that max is going to be in our list itself. So sometimes it can be difficult to come up with properties that effectively test all of the things we want to know about a particular function. So because of these difficulties, and also that it can be difficult to just come up with these properties, and it takes a long time to write a property-based test, we asked the question of should we actually recommend developers that currently just write unit tests to write property-based tests? And so from this, we have 3 research questions. The first being, how effective are property-based tests in comparison to unit tests? And also, what is the computational cost of using PBT? And if they end up being effective, what are the kinds of property-based tests that people should actually write? So looking at this first question, we're asking how effective are property-based tests at catching bugs when compared to unit tests? So what we've done is an evaluation of effectiveness that shows that property-based tests are around 50 times better at catching bugs than unit tests. So there are many ways that you can evaluate the effectiveness of a test suite. And one of the ways that you might be familiar with is with code coverage, which shows that if your tests cover a majority of the code, then your test suite is going to be more effective. But an alternative method is through mutation analysis. And the underlying idea of mutation analysis is that a good test suite should fail anything except for what the code currently does. So we have this really simple example function where we sum up 2 arguments and then return that sum multiplied by 100. And so a mutation on this source code would change one of these small aspects of this program. For instance, one of that could be changing plus to minus, or you can also change 100 to a negative 100. And these small changes in the source code are what are called mutations. And what you do in mutation analysis is that you run your test suite on each of these mutations, and you try to see if any of your tests will fail. And if one of them does, then that means your test suite is more robust. But if all your tests pass, even when there is a change, then that means that your test suite is not as robust as you thought. And although these mutations seem very insignificant, prior work has actually found that mutation detection, being able to catch these small changes in the source code, is positively correlated with real fault detection. So we can use mutation analysis to assess the effectiveness of the tests in our projects. So in our experiment, we collected a corpus of Python programs that use Hypothesis. And we tested 40 of them using this mutation analysis where we created 100 mutations per project. And what we found is that PBTs found mutations 11% of the time, while unit tests found mutations only 0.24% of the time. And the kinds of mutations that they find are pretty disjoint, with only 15% of the mutations being found by both kinds of tests. And when we ran a chi-squared analysis, we got a significant result with an odds ratio of 52, which shows that property-based tests are 52 times more likely to find a mutation than unit tests. And you can kind of interpret this as saying, like with the property-based tests, you get the same detection power as 52 unit tests. And we also considered code coverage in this. So when we controlled for code coverage in a project, we found that we got similar results with a similar odds ratio. So we see that PBTs are pretty effective at catching bugs, especially in comparison to unit tests. But a property-based test also runs hundreds of inputs. So what is the actual computational cost of using a property-based test? And especially because people run these tests in continuous integration pipelines, it's especially important that we're able to test things efficiently because people are running these all the time. So our next question asks, how does the bug finding efficacy of property-based tests relate to the number of inputs used when executing them? And so we conducted a parameter sweep experiment on just our property-based tests in our corpus, and we found that over half of mutations were found with just a single input, and 76% of them were found within the first 20. And this can be due to how the back end of hypothesis generation strategies work, but it could also be indicative that thinking of correctness as properties instead of specific input-output examples could be a reason for why the tests that people write with PBT are better at finding bugs. So we've seen that PBTs are more effective at finding bugs than unit tests, and that the computational cost of them is less than what you may expect if you were just considering them as hundreds of unit tests. So our final question is, if they are in fact effective, are there specific kinds of property-based tests that people should use? So there have been many informal guides on how to write properties for PBT, and these are 3 examples that are linked in the hypothesis documentation. So we started with these kinds of properties to see if we could automatically detect when tests correspond to each of these recommended kinds. So we came up with our third research question. We asked, what kinds of properties do Python developers check in PBTs? And so we came up with a categorization of PBTs by property, and we have definitions for 12 categories, and a tool to automatically classify PBTs into these categories. So if we recall, we have 2 pieces that are in every property-based test, a generator and a property. And what we noticed is that in order to be a property-based test, every PBT has a data flow from the generated argument produced by that generator to the actual assertion that's being checked. So we decided to use these data flow patterns to categorize our tests. So as an example, we're going back to our list max example. And if we start off with our list being generated, ls, we see that we get the max value from this, and also we look at every element. And we then compare the max to the elements of each of these. And so the overall pattern is what we call a bounds check. Now looking at something explicitly from one of our corpuses, we have this extended Euclidean algorithm test, which makes sure that when you have 2 positive integers, a and b, that you're able to find the greatest common divisor of this. So we start out with a and b, which are being generated as integers from 1 to 1,000, and then we plug it into this extended Euclidean algorithm, and then we receive d. And then from there, we check that a mod d is actually equivalent to 0. And because 0 is not related to a and b, we call this a constant, and we call this pattern a constant equality pattern. And so overall, we obtained 12 categories from this data flow analysis, and 5 of these are actually related to those recommended properties that we saw. So looking at the classification, we had around 492 Python projects in our corpus, and we categorized 94% of these. We also collected a set of 50 projects that were not in our original corpus because we used that corpus to develop this categorization, and we also categorized 94% of those. And the most common category in both of these corpuses are constant equality tests. But because we have all of these different categories, we wondered, are there certain categories of property-based tests that are more effective at finding mutations than others? So we conducted a similar evaluation of effectiveness as we did with the first research question, and we did find that some categories are more effective at finding bugs than others. So for all but 3 of the categories, we received significant results, and our top categories were the following: exception raising, which checks that a specific exception is raised; inclusion, which checks that some variable is included in some collection; and then type checking. So one thing to note is that because some of these categories had kind of sparse tests in them, we do run into a risk of sparse data bias in our odds ratios, so they could be inflated, but we still get significant results from these categories. So looking at the odds ratios overall, we see that we have most of the categories doing pretty well, but we noticed that all of the constant quality tests were pretty common in our corpus, but it is actually pretty middling when it comes to their effectiveness. So perhaps we do need better tools to help people write more effective test cases when they are using PBT. So going back to the original guiding question of whether we should recommend using property-based testing, I want to take a moment to say what this talk is not saying. So we're not saying that unit tests aren't needed. Oftentimes, you still want to use unit tests to check specific edge cases, and also certain things are just easier to test with a unit test than compared to a property-based test. And also, because our study is an observational one, we can't infer a causal relationship from writing PBTs and finding bugs. And for that, we actually need to conduct additional experiments which allow for an intervention. In addition to this, we also want to study the time cost of writing a PBT, analyze property-based testing generators, which we didn't analyze in our particular study, and also do a comparison with other languages. So overall, we have a categorization of property-based testing into 12 categories, and we've conducted experiments assessing the effectiveness of property-based testing. And we found that PBTs are more effective at finding bugs than unit tests when we use mutations as a proxy, and they also find most bugs within a few inputs. So this is a QR code to our paper, and feel free to ask me any questions.
Okay, thank you for the talk. I think we won't have a lot of time for questions. I see a lot of people queuing up. We might have 1 or 2 at most, and then I think it's a very interesting talk. You can take the questions after, to the coffee break after this session. So yes.
Okay. When comparing unit testing with PBT, one important factor is that since they are both written by human, how do you control how these tests are written? Could you elaborate on that point?
So we had the assumption that the same people were writing PBTs as were writing unit tests because we were looking at those written by in the same. There is a possibility that they could be written by different people if we had looked at the GitHub contributions, but we made this assumption, so we think it is a fair comparison that the same people would be writing the test for this project.
Thank you.
Yes. Yes, I think it is an important thing to look at, seeing how people use the results of PBTs. And I think once we do our actual human evaluation, it would be a good experiment to check how people use those. Thank you.
Thank you. We move. Actually, very inspiring talk. We move to the second presenter. Okay, so Lee will give us a talk on Frey, an efficient general purpose concurrency testing platform for the JVM.
Thank you for the introduction. So hello everyone, my name's Leo and also Al, and today we're talking about how we test concurrent programs in Java. And again, concurrence bugs are one of the notorious difficult to detect and diagnose. And this is old topic, but still really hard to do in real world. And the question we're trying to answer is how to test concurrent programs. Well, you may ask, hey, isn't this problem already solved? I'm writing Rust or I'm using TSEN, right? True and false, right? If your program has bugs caused by data races, yes, using Rust and other fancy tools like OOPSLA and thread synthesizer may help you to prevent those issues. But the issue I'm talking about today, such as deadlocks, atomicity violations, and other older violations, they are not necessarily caused by data races. And the question, to give you some example about what does those bugs look like, let's look at this simple bank account example. I'm implementing this withdrawal method, and I'm trying to call this withdrawal method into threads separately. And to do this, I can come up with a schedule where I let both threads to enter, to read the balance from the shared variable, and I do the condition check so that both threads will enter this true block. And then I let one thread to update the balance, and then the other thread to update the balance again. With this, I'm allowing two threads to both perform the transfer method, withdrawal method. And you can see that there's no data race in this program, but you still have this bug that is called atomicity violation. Well, this is not a new problem either. There are actually tons of research papers trying to implement fancy algorithms to identify this kind of bugs in concurrent programs. Well, this is true that you can use this algorithm to find bugs in program like this, but the question I'm asking today is how can you use this algorithm to analyze softwares like Kafka, Guava, and Lucene? In fact, developers aren't using this. Developers are still relying on simple unit tests to test their concurrent software. And this is a GitHub issue I got from Lucene, where they saw a concurrent bug in 2012, and in 2019, they saw the same bug again. And this time, they were saying they believed they found the root cause of this issue, and the way they test their software is just to run the software 20 times, and they observed no failure in their test runs. They believe the test was fixed until in 2021, the same failure was observed again. Well, running simple tests in a loop isn't really a good way to test your concurrent software, right? Then what is a good concurrency testing? And we do have some requirements. We don't want non-determinism. And we also want efficiency. That means that we want to control what threads to run given a time, and we also need to make sure the execution is deterministic. And the answer is not new either. We all know that controlled concurrency testing is something we want. And I'm not the first one who implements the controlled concurrency testing. In fact, in 2000, NASA has already proposed this idea about Java Pathfinder, which is a model checking tool that allows you to model the concurrent behavior of a Java program. But why aren't developers using this? And to understand applicability, we actually put two requirements to make a tool really applicable. And the first axis is expressibility, meaning that can I use this tool to find certain bugs? I mean, if your tool can only run a very limited number of programs, I can't really use them to analyze to application like Kafka. The second thing is efficiency. How long does a tool take to find certain bugs? In the previous example, you can see that running the test again and again may find a bug. It just takes 3 years. I can't really use them to test my concurrent software. So by putting all the prior work in this coordinate system, we notice that none of them are trying to achieve both expressibility and efficiency at the same time. So today, I'm going to talk about Frey and to discuss how Frey solved this problem. The high-level intuition of Frey is very simple. It tries to put some stop signs in your application so that your application will run in sequential order. Why am I doing this? The reason is that in Java language, it gives you this nice property called DRFSC, meaning that if your language if your program is data race free, it gives you this sequential consistency, meaning that you can represent all possible concurrent behavior of your program in some sequential execution of the program statements. Once I have this sequential execution, if I'm able to control the execution of the program, then I'm achieving the determinism. So now I'm having a very simple loop to test my concurrent software. At the very beginning, I stop all threads, and I will check which thread can run based on the semantic of my concurrent software. And I pick one thread to run until either the thread hits another stop sign or everyone finishes. Well, the first question is where to put stop signs, right? Prior work tries to put stop signs at all memory accesses, which led to really large search space and also very slow to run. And our solution is, our observation is that you only need to put stop signs before concurrency primitives. And it gives, of course, it gives us a very small search space, but the question is, am I going to miss bugs? Well, in fact, it won't, because if your program is data race free. So we provide a proof in our extended version of the paper, and if you combine free with any mature data race detectors, then you will not miss any bugs. The second question is how to put stop signs. Well, so one way to do that, you can just put some sleeps in your program. Again, non-deterministic and also slow to run. And our solution is to put shadow logs. Idea is very simple. We add additional logs in your application so that based on this cooperative locking and unlocking mechanism, we can achieve both deterministic and which is also fast, very fast. I can't really go into about how shadow logs are designed. I'm going to just give you some high-level intuitions. Shadow logs enforces this sequential execution, and we control the lock and unlock order to control the execution of your program. And we formally model the shadow log behavior based for all concurrency primitives under Java utility concurrent, and we also provide both soundness and completeness of the search space. And going back to the prior research, we not only support this random walk search strategy, we also support all the searching strategies proposed by prior research. So going back to the question, how am I going to test these softwares? And this is the way we evaluate our system. We collect all concurrency tests in the existing software, and we just run them again with free. By just running them, we can find already 363 unit tests can fail under certain thread interleaving, which led to 19 new bugs reported and 15 fixed so far. And some exciting news is that POS actually works the best in terms of bug finding capabilities. And the developers can't really access those algorithms just because of the lacking of this testing platform. So we got some very positive feedback from the developers. After publishing Free was on the Hacker News front page a couple times. And also, we helped the developer fixing the Lucene bug. And after we fixed the bug, the Lucene developers were very happy, and they invited us to write a blog post about how Free helped them diagnosing this bug. And after releasing Free was we got requests from developers from Elasticsearch, Amazon, and Antithesis. They all expressed their interest in integrating Free into their system. So yes, this concludes my talk today. And Free is a general purpose, efficient platform for JVM concurrency testing. And we open source Free, and we publish Free on Gradle, Maven, and as Nix Flake packages. And last but not least, I'm Leo, and I work on debugging and testing cloud systems. So you can see my prior work here, and I'm looking for tenure-track faculty jobs. And thank you.
Thank you much for the talk. We have, I think, quite a lot of time for questions.
Thank you for the great talk. So a question about how you model and control the determinism. You said you use locks. Is it possible that there are certain data structures in the concurrent library or the JDK which requires more fine-grained control than just locks? It actually supports concurrency.
Yes.
How do you deal with this?
That's a very good question. Using locks is like a very high-level idea. So we actually designed the semantic of the locks based on the concurrency primitives. Basically, the way you are locking and unlocking those shadow locks are very different based on the concurrency primitives they are controlling. So that's one part of the contribution I couldn't mention in the presentation due to the time limit, but feel free to check out our paper about how we design this. Thanks. Yep.
Hello, Jakub Skolokasis from University of Crete. I have two questions. The first one is about is Frey garbage collection agnostic, so it plays with all garbage collectors?
Yes, the answer is yes.
Okay, and the second question is that you instrument write and read and write load and stores actually post barriers and read barriers in the interpreter and all the types of JIT compilation with Frey.
So is a question about whether JIT compilation will affect how we do this lock? The answer is no. Actually, we perform this in Java. It gives you this nice property where you can instrument the application before a class is loaded, so that after we perform the instrumentation, the JIT compilation will consider our instrumentation as well. So when they do the JIT compilation, it will not affect how we perform the instrumentation, and it doesn't really affect how we control the concurrency.
Okay, and the third question, and I'm finished. Does Frey, I'm running it during my application execution or on the side? And if on the side, the testing, how it generates the inputs to test all the cases that the execution path can go?
So we do provide a sound and complete modeling of the search space, but currently we use random search strategies like PCT, POS, and random walk to decide which thread to run. Not really because it's just because the search space is huge, so give you some idea about the test we run. For Lucene tests, it usually take like 5 or 6 seconds to run for one iteration. So if we do systematic exploration, it's just too slow for us to explore all possible thread interleavings.
Okay. Thank you very much.
Thank you.
For more questions, yeah.
Okay, hello, thanks for the talk. So I would like to ask about where you insert logs. So you said you insert them on any operations which touch anything from Java util concurrent, right?
Yep.
So do you also insert them when there's a read or write a volatile variable?
Yes, we read and write to volatile variable will also introduce happens before relationship in the Java language. And also atomic variables, they also introduce happens before relationship. We'll also handle some unsafe operations as well.
Okay, thank you.
Yep.
Thank you. Yeah, I think we have 1 more minute for a question. I want to ask, did you find any real bug on system, and did you report them? Because before you show like some reaction from the developers, if you find any real bug, did you report them and how the developer reacted to these?
Yeah, that's actually very interesting. So we reported these bugs usually after we report these bugs, it takes really long time for them to come back. So not really because they can reproduce them. It's actually because even though they can reproduce them, they still can't really figure out what the root cause of them. Just because the execution is very long, and also try to narrow down the root cause take time for them. So I feel this is going to be our next step. We are going to think about how we can make improved ways to help developers to diagnose those concurrency issues.
Thank you. So the next presenter is Bo Wang, and he's going to talk about fuzzing C++ compilers via type-driven mutation.
Okay. Good afternoon, everyone. This is Bo Wang from Beijing Jiao Tong University. It's only here to introduce our work, fuzzing CPP compilers via type-driven mutation. And first, let me introduce some background. So as we all know, CPP was a very long history programming language. It was created in 1985 by Benjamin Strostrup. It features high performance and direct memory access, making it an important system-level programming language. Many essential fundamental software are written in CPP. For example, the C and CPP compiler themselves, and Clang and GCC, and important GVM, OpenGDK, and some important databases like MySQL and Redis, and Chrome browser, and also Z3 solver and CUDA, TensorFlow, and Microsoft Windows kernel. So all these important products are written in CPP. CPP is a compiler language. It's relying on compilers to translate source code into target code. So a compiler is essential in the ecosystem of CPP. However, as many complex software, compiler also may have bugs, and these bugs may cause crashes during compilation. And the worst thing is, it may incorrectly transform the codes. It may transform the correct source code into incorrect executables. So these defects in compilers may propagate it to all the generated programs. Therefore, testing CPP compilers is crucial. As we all know, CPP has a very complex type system. Anyone who have learned CPP knows the struggle. The learning curve is steep and long. So there is a joke in Chinese society, as if one developer who's writing his programs in CPP, and if he have learned 3 years, he told the other one that he mastered the language. But if he have 5 years experience, he said he understands the language. And if he had 10 years language, he say he just heard about it. So there are also many funny pages, funny figures in the internet. Compared with GVM languages like Java, CPP features have much more complex type system. It is a static typing, but also with runtime mechanisms. And it also supports type inference. It has the keyword auto. And the implementation of generic programming in CPP is based on template, not type release, such as Java. It also supports type alias. Only a few programming languages support this feature. And it also supports complex inheritance hierarchies. For example, it supports multi-inheritance. Therefore, CPP's complex type system poses high significant challenges to compiler correctness. Let's see a motivating example. This is a bug, a GCC bug. Had been hidden for 19 years before we reported it. So this program first defines a struct, a class, and it has one constructor taking one integer as input, and the third line is overloading casting operator. So in the sixth line, it has a ternary expression which requires the x and the zero, the integer 0, they should have the same type. However, x is constant constant reference of A. And the 0, if we don't have the explicit, it will go through the line 2 and to call the constructor and return an object of A. But if we insert an explicit here, if we don't have the line 3, the word, this program should be invalid. However, since we have line 3, so the 0, which is the non-pointer in C program in C type system, and would change would be casted into a type A. So this one still be valid. However, the compiler incorrectly rejected this program. Currently, there are two main categories of compiler fuzzing approaches. One is generation-based, such as C-Smith and YapGen. The one is mutation-based, such as EMI, which is proposed by Zhendong Su, and Gracie and Metamute. However, both categories struggle to fuzzing type-related features. Generation-based methods struggle to produce programs that fully access the complexity of type systems. And mutation-based approaches, and currently they overlook the type system-aware mutation operators. Therefore, we propose TY-mute. So here's the overview of TY-mute. Given a valid program, a CPP program, we first perform some necessary analysis to extract some necessary data structure, and we perform the mutation by our type-driven mutation operator. And if the operator is a well-formed mutation operator, the valid program should keep its validity, and the output also a valid one. So the compiler cannot reject it. If the program is generated by a not well-formed mutation operator, the correctness is unknown. So we further check it with well-formed rules. If the rule rejects the program should be invalid and cannot be accepted by the compiler. Otherwise, we don't have enough test oracle, so we employ differential testing. We model the CPP into a DSL, and we also build some. We also extract some necessary data structure, such as inheritance graph, accessibility, and we also model the type system. We support nominal type, which support inheritance, and we also support structural type. And based on this, we build a type lattice of the program. Based on this type structure, we design and implemented 30 mutation operators across 5 categories. And the categories are focusing about inheritance, template, type convention, and accessibility, and also object lifecycle related. Here's some operator examples. One is generic narrowing. It will change one structural type to its subtype. Here, and the second one is order lifting. We will lift one expression to its lambda. And we also construct some multi-inheritance structure. So traditional compiler testing compares compilation results across different compilers to detect inconsistencies. So this requires all input programs to be valid. However, when testing type system, we need both valid and invalid input programs. So valid for check correctness, while invalid one check error handling. So therefore, the test oracle become more challenging. So we handle this by mutator classification and the human writing checking rules. So given a valid program, if it is generated by a well-formed operator, it should be valid. And if it's produced by a not well-formed operator, we further check it by rules. So here's the evaluation. During the bug hunting experiment, we totally reported 102 bugs to GCC and LLVM, and 56 of them have been confirmed as new bugs. And here are the symptoms. As we can see, more than 40% fall into the accept invalid and reject invalid. And they cause miscompilation. Among the 56 confirmed bugs, seven of them have remained hidden for over 20 years, and 22 for 10 years, and 39 for 5 years. And one long-lasting issue has confirmed to be the root cause of a real-world issue in TensorFlow. And one unconfirmed bug led the compiler developer to submit a new issue to the CPP language standard. So here are some bug examples. This one is the root cause of TensorFlow. And here are some issues. Here are some bug examples. And also, it received some interesting comments by developers. The most interesting one is the GCC, the LLVM. The developer referred to Git pull request 30 years ago, and he commented, "Wow, looks like I got this wrong 30 years ago, oops." And we also received some comments from the developers. Okay, thank you.
Thank you. We have time for around 2-3 questions. If there's no question yet, I would like to ask, what was the bug that led them to fix the standard, something in the standard? I think you scroll very quick. Maybe just leave the laptop for a second, or if you can describe it.
Sorry, beg your pardon?
What was the bug that led to the change of the C++ standard? And to add it, so they fixed something in the standard? One of the bugs that you found?
It's about, we import a global declared enum into inside the class. So the behavior is unspecified by the standard.
So they have to either say it's unspecified or to create a subsection describing what's the case, what they did in the end, or just to mention that is, because I know if it's unspecified, it's also saying it's unspecified. So was it a case that it was not mentioned that this behavior is unspecified behavior, or was it a case when they added this behavior to the standard?
And the developer just commented that the behavior is totally unmentioned by the standard. So.
Okay. Yeah.
Okay.
Yes, I think.
I have a quick question about the soundness issue where the compiler accepts invalid programs. So to identify, I remember the 13 unique bugs. Did you have to manually inspect the type error emitted by the compiler to come up with the unique test cases, or did you have any kind of automated process to classify those into some equivalence classes of type errors?
All the output results, for example, the results of different testing or rejected by the rules, we would check them manually.
Oh, okay, thank you.
Thank you.
Yeah, I think there was another person but maybe we take it over the coffee break. Thank you for the talk. So the next talk is LegoFuzz Interleaving Large Language Model for Compiler Testing. Yanubu Ni is going to give a talk.
Okay, thanks for the introduction. Hi everyone, I'm Yunbo Ni, a first-year PhD student at the Chinese University of Hong Kong. Today I'm excited to present our work, Interleaving Large Language Models for Compiler Testing, in collaboration with my advisor, Professor Shaohua Li. Currently, we have several amazing LM-based testing tools, such as FastForAll and YFox. These tools have demonstrated great potential in testing with LMs. However, they are not so effective for testing compilers. If we take a closer look at their reported bugs, two main issues appear. The first one is the low capacity of the generated programs. For example, FastForAll only discovered 8 front-end bugs in GCC. The second is the limited symptoms of discovered bugs. The 2 bugs found by YFox were simple crash cases. This raises a key question. Can today's LM-driven testing frameworks really hold up in the wild, like in a CI pipeline? There are 2 major challenges to achieving this. First, the typical workflow of these tools feeds code or documents into an LM and asks it to generate a single test case. To produce millions of test cases, we have to curate the LM million times, which quickly becomes very expensive. Second, the generated programs are often of low quality. LM tend to produce code with syntax or semantic errors, and even when it compiles, the programs are usually too simple to trigger deep or meaningful compiler bugs. Thus, simply prompting LMs doesn't mean effective testing, so why aren't they enough for compiler fuzzing? First, LMs are too slow. Tools like FastForAll can only generate about 16,000 programs per day, while traditional fuzzers can easily produce millions in one day, making large-scale testing extremely inefficient. Second, the generated code is often invalid or too simple. For example, FastForAll's valid rate is only 37%, and many samples either fail to compile or crash right away, like the buggy example is shown here. Invalid programs get rejected early and rarely reach deeper stages like optimization or code generation. Finally, LMs struggle on real compilers. Tools like YFox cannot map high-level reasoning to low-level implementation well. To address these issues, we designed LegoFast. The core idea is simple. We decouple LM usage into 2 stages, an offline stage that builds a readable code database using LM, and an online stage that synthesizes large valid programs without killing the LM game. On the left, the offline stage collects code from real GitHub projects, lets the LM generate diverse snippets, then validates them and profiles each one. For example, we got for 1 with 1 as the input and 2 as the output. We also know like y equals to 2 when profiling. On the right, the online stage reuses these functions as Lego blocks, collecting them through function calls or global variables. For example, we try to insert for1 to for2 with the same value at line 4. With each iteration, the program grows more complex and realistic. In short, the offline stage ensures real and valid code generated by LMs. It fuses with traditional program analysis with LM understanding to ensure real and high-quality code generation, while the online stage builds deep and interconnected programs at minimal cost without killing LM's game. Now let's take a closer look at the offline stage, where we aim to generate real-world code with real capacity. Previous LM-based testing tools often feed code a model with simple context, like standard documents or small toy snips, which fail to reflect how real compilers behave in practice. Here, we instead provide real-world codes and meaningful context. So the LM can reason about the actual program logic, align syntax and semantics, and transform the snippets into compilable and realistic functions. For example, we use the real code from ACC, a small compiler. Then our prompt asks LM to convert these programs into a unified and compilable format while preserving their original semantics. This task doesn't require the model to write new code from scratch, but rather to understand, reason, and restructure the existing real-world code, which perfectly fits the strengths of the large language models. Here, it expands the complex structured parameter and replaces the external function with function from ST, which traditional tools find very difficult to do. The key takeaway here is that LM truly understands code semantics. They can reason, transform, and complete snippets, laying a strong foundation for our offline stage. So after generating these real-world functions, the next step in the offline stage is to make sure they are both valid and reviewable while maximizing the semantics for testing. In total, LegoFast constructs a database of over than 500,000 valid functions. How do we construct it? Let's take that same example before. There's a potential runtime overflow here when writing the body array. To avoid this UB, we automatically validate and profile each LM transport function using multiple compiler toolchain tools like sanitizers, like ASIN here. Functions that fail any of these checks are discarded. The remaining valid ones are then profiled to get their I/O values and runtime profiles. So, for example, we know that len equals to 1 and analog equals to 2 at the beginning. All profiled functions are stored in our reusable code database. Please note that we only construct this once and can freely reuse it later without curing the LLM gain. Now let's move on to the online stage, which focuses on building dependencies to increase complexity. LegoFast reuses the validated functions from the database, and first it generates a driver program, a seed with the main function. It calculates and prints a checksum for later differential testing. Then it builds dependency among them through function calls and shared global variables. Once the driver and dependency are ready, we can directly start fuzzing on compilers like GCC and LVM, completed without any LLM involvement. Here's how LegoFast performs iterative program analysis synthesis using what we call function breaks. For example, we want to synthesize the for function into the buffer write. How do we do that? Each function in the database comes with profiling info. For example, for takes input 1 and output 2. Also, for the buffer write, we know that analog equals 2, the same as the output of the for. So we start to replace analog with for. The function for also requires something as an input. So here we got a variable len with the same value as the input. As a result, the synthesizer simply replaces analog with a call to the for. We also added the call of the for to the driver function here to calculate the checksum. This links the two functions through data dependency, keeping the program valid while making it more complex. The second way LegoFast links pieces is with global variables. We have prepared a list of random global variables at first. For example, the g with the value 1 here. Our profiling shows that at this site, len equals to 1, so we simply replace the use of the len with g. Same before, we use g to mutate the checksum as well. Together with function call insertion, the global sharing enables LegoFast to build large and meaningful test programs. And finally, we print and compare the checksum under different optimization levels to find if there exists any compiler bugs. Finally, let's see how well LegoFast actually works in practice. So far, LegoFast has found 66 bugs, and 56 have already been fixed by compiler maintainers. What's notable here is almost half of them are miscompilations, subtle logic errors that many existing tools completely missed. Some of these bugs are quite important. One of them had existed for over 20 years, and discovery even led to an update in other tools. You can see the maintainers' reaction here. They were surprised that the bug hadn't been caught earlier. Overall, LegoFast can uncover a wide range of the issues, from crashes to deep optimization bugs, demonstrating that it's not just theoretical, it really works end to end. We also, to better understand how each part of the LegoFast contributes, we performed an evaluation study on its key modules. First, we tested different LLMs, including the legacy models GPT 3.5 and task-specific models like Chain Encoder. The results show that the framework itself has nothing to do with the choice of the LLM. Next, we examined the importance of the database. We found that real-world code plus LLM generation leads to larger and more complex program generations compared to the traditional database like serials. Finally, we studied the impact of the iteration number in synthesis. We found that the best trade-off is when the number equals to 100, which achieves highest coverage on both GCC and LVM. Together, these results confirm that LegoFast design is robust and scalable, independent of the specific models or parameter choices. Finally, we compare LegoFast with several state-of-the-art tools, including generation-based ones like Serial and LLM-based ones like FastWall and YFox. In terms of bug fighting, neither FastWall nor YFox was able to discover any miscompilation bugs, while LegoFast consistently uncovered both crashes and deeper logic issues. For coverage and speed, LegoFast achieved over 50,000 lines of code additional coverage and ran about 146 times faster than those baselines. The example on the left shows one of our synthesized programs. It forms a long dependent chain built through multiple iterations, which helps expose complex compiler behaviors that other tools simply miss. To wrap up, LegoFast opens up several promising directions for future work. First, we can explore alternative prompting methods. Second, we can plan to incorporate more sources of code snips, so we can go beyond function level synthesis. And finally, we can go beyond C compiler testing. This brick-by-brick idea doesn't just stop at compilers. It points to a broader future for LLM-driven program synthesis and automated testing. To summarize, LegoFast is a powerful and cost-effective LLM-based framework for compiler testing. It combines two stages, an offline stage that builds real and reusable complexity, and an online stage that's fast, cheap, and completely LLM-free. In real-world testing, LegoFast had already found 66 bugs, with 56 confirmed fixes in GCC and VM. And more importantly, it introduced a new paradigm for LLM-based testing, one that's easy to extend, flexible across models, and highly effective in practice. You can scan here for code and its found bugs. Thank you for listening, and I'm happy to take any questions.
We have some time for questions. I think we can have more than 2-3 questions.
Hi, Harry Goldstein, University at Buffalo. Thank you so much for the talk. This is really cool work. I really like that you're not using the LLM during the key generation loop like Fuzz for All does, for example. Although one thing I did like about Fuzz for All is that they talked about being able to kind of easily adapt to new features of the programming language. Do you know how much, do you have a sense for like whether a new feature that you add maybe 5 to 10 examples of in the database could be represented well enough in the generated test programs? Or do you think you need like quite a bit of data on a particular feature in the database in order to perform well?
Well, thanks for the question. This is also one of our ongoing work, like targeted compiler parsing. Because when a new feature appears, you need like a certain structure. Like if you want to test like loop analysis optimization parts, and you would search for the code with like multiple loops. So in our database, you can modify this database to equip the code snips with more features. Like you will count how many loops that the code has, or you can also use like OPT to check if you trigger a certain optimization path. So in that way, I think LegoFast is easy to extend to other features or even other languages, or like you can make it to a targeted compiler parsing framework. Yeah, thanks for the question again.
Great, thank you.
So I was curious, were the generated test cases really long, or did you notice that they're like the test cases that found bugs? Did you notice that there was a trend where they tended to be really huge and complex, where they had to do kind of post-processing to do test case reduction, or were they pretty concise and like targeted toward the bug that they uncovered?
Oh, thanks for the question. The answer would be this is huge, because you can see the best iteration number is 100. And that would produce around like 8,000 lines of code. And when a bug is detected, we use like C-reduce to reduce the whole program to find the real buggy program. And the average of the real buggy program is around like 20 or 30 lines. Yeah, that's the answer. Yeah.
Cool.
Thank you.
Hi, I have a quick question for the, I'm curious which components contribute more to the performance, for instance, the seed augmentation or the seed composition. So which component contributes more to the maybe coverage or bug finding?
You mean the components of the LegoFast?
Yeah.
Yeah, I think the database construction contributes the most, because like you really utilize the complexity from the real world code, and that triggers like more deeper compiler paths. Yeah.
Okay, so what if I only use the seed, the database augmented by a larger model, and use general mutation strategies? Is there such evaluation study?
Yeah, we actually did that experiment. Okay. You can check it on, in our first RQ, because we use the individual functions to test if we can find any compiler bugs. And for like we have tested for like a week, and no compiler bugs was found. Yeah.
Thank you.
Thank you.
Thank you. I don't think we have time for more questions, but I'm sure you can take it to the coffee break. So the next talk is about model-guided fuzzing of distributed system, and Ege Berkay Gulkan will give the talk.
Okay, maybe like this. Okay. So hi everyone, I'm Berkay. I'm from TU Delft, and today I'll be presenting you our work on model-guided fuzzing of distributed systems. So finding concurrency bugs in distributed systems is notoriously difficult. They're highly concurrent, non-deterministic, and prone to subtle bugs that only often surface in production. Random testing can help, but it usually misses the deeper issues. Promising technique is coverage-guided fuzzing. Does it work like this? Yeah? If it works like this. Yes? Okay. What was that? Yes. So random testing can help, but it usually misses the deeper issues. The promising technique is coverage-guided fuzzing, which is proven effective for sequential programs. But applying fuzzing to distributed systems introduces unique challenges. In particular, existing coverage metrics don't translate well. So we end up with the question, what is a good notion for coverage? To answer this, we thought formal verification methods exist for verifying distributed systems. So is there any way for us to leverage them to guide fuzzing, for them to guide fuzzing? So our idea is to power fuzzing with abstract formal models. In this case, TLA plus models, which are often available from protocol design. The key benefit is abstract model keeps essential information, but at the same time allows us to abstract away implementation level details. So now, instead of measuring something like code coverage, we treat the model states as our notion of coverage. Each time the system explores a new state in the model, that's feedback to the fuzzer. In other words, the model becomes a guide. It steers fuzzing towards unexplored and interesting behaviors. So then we should also ask the question to ourselves, why existing coverage notions are unsuitable for distributed systems. So let's illustrate this specifically on code coverage, why it is unsuitable, with a simple example. We have three processes, an app master, a worker, and a terminator. The app master coordinates the requests, the worker executes them, and the terminator handles cleanup. When the app master receives a request, it sends two concurrent messages, one to execute and one to terminate. The worker runs this task on execute, and notice here that the developer here forgot to put a null checker on its buffer. Meanwhile, the terminator receives the message and sends a flash to the worker to clean up. This is the intended behavior. Now let's consider what happens if the network conditions change the order of the events. The setup is exactly the same, but this time the execute message is delayed and the cleanup happens first. The terminator flushes the worker before its task is executed, and when the execute finally arrives, the worker tries to use its buffer, which is now null, and this results in a crash. What's important here is that both executions cover the same lines of code, but lead to very different outcomes. The bug here lies not in the code coverage, but in the ordering of the events. So unlike code coverage, model states capture the overall behavior of the system, ordering of the events, message deliveries, process interactions, not just which lines of code were actually executed. This means that two runs that execute the same code, but in different orders, map to different model states. As a result, model state coverage captures the effects of concurrency between executions, making it far more effective for testing distributed systems. So code coverage is out. Another idea is to use Mazurkiewicz traces. They're useful for distinguishing schedules syntactically and already account for concurrency as they consider the orderings of dependent events. But in practice, they're too fine-grained. They consider many orderings that ultimately lead to the same overall system behavior. So here's an illustration why traces are too fine-grained. In this state diagram, we can see how different event orderings lead to very different outcomes. But even for this tiny example, this diagram only represents a small fraction of all possible states. In real distributed systems, the state space grows exponentially with the number of nodes, messages, and other variables. On top of that, many systems include an additional setup phase, like we have in our example here. This phase often creates a bottleneck in exploration, and we don't want to waste our exploration budget navigating through it repeatedly. If we think of the circles as the system states and traces as the paths between them, we can see that many different traces lead to converge on the same state, making them unsuitable for effective guidance. So to go back to the key question, a good coverage notion should also guide us effectively through these enormous spaces. What you really need is a notion of coverage that captures the semantics of the system, not just syntactical differences in traces, but meaningful differences in its states. By using model states as our coverage metric, we capture these semantics directly. Each model state represents a distinct global configuration of the system, its processes, messages, and interactions. Trace-based coverage, on the other hand, still distinguishes many schedules that ultimately lead to the same behavior. Model state coverage abstracts away the redundancies and focuses only on what's truly different. So traces are out of the picture, as it both captures the concurrency of the system and distinguishes between the semantics. Abstract formal models provide the balance that we're looking for. So before I explain how we extend fuzzing with models, let's quickly review the basic fuzzing loop. In a typical coverage guided fuzzer, we start with a system S and initial set of test cases T0. We pick one test case, run it on the system, then collect some form of coverage notion. So there's something simple like line coverage, for instance. If this execution hits new lines, we mutate this test case and add this mutated version back to our pool. If it doesn't explore anything new, we discard it, and the loop continues. We extend the base coverage guided fuzzer with the additional components seen here in orange. This is our fuzzer, model fuzz. Instead of raw inputs, we provide seeded schedules to the system under test, and we execute them with a control scheduler. This matters because in distributed systems, the same input can lead to very different outcomes depending on the ordering of the events, as they're highly non-deterministic. The control scheduler is there to enforce that ordering. Next, we map the events that we collect during the execution into model actions and run them in the model checker. We track which states the model reaches and then feed that information back to the fuzzer. If we uncover new states in this process, we mutate the schedule and add it back to the pool. So we end up, at the end, we end up with a loop where the fuzzer generates schedules, the system executes them, and the model provides feedback to the fuzzer. The feedback loop continues to drive the exploration towards previously unexplored model states, allowing model fuzz to uncover unique and interesting system behaviors. We evaluated our fuzzer on several distributed systems, namely two-phase commit and two production implementations of Raft, etcd and Redis Raft. For baselines, we compared them against random testing, trace coverage, and line coverage, and bonus max RL, a reinforcement learning-based approach. Across all of these, we measure two things: how much coverage each method achieves, and how effective are they at finding bugs. When we look at the coverage, model fuzz consistently outperforms random testing, as well as line and trace coverage. Compared to bonus max RL, model fuzz achieves overall comparable performance with bonus max RL, but it outperforms us, especially on the etcd benchmark. But when we look at the overall results, we demonstrate that using abstract model coverage is an effective way to guide fuzzing in distributed systems compared to other coverage baselines. When we turn to bug finding, model fuzz not only discovers bugs at comparable speeds to the other approaches, but also uncover bugs that they completely miss. So you don't need to actually read the table, but for example, in Redis Raft, we found 13 bugs in total, and 11 of them are new bugs. Specifically, model fuzz was able to detect almost all of them. Importantly, 3 of those bugs could only be found by model fuzz and could not be detected by any other method within the test budget. We also discovered a new bug in etcd Raft, again only found by model fuzz. So with these results, we show that model-guided fuzzing isn't just about increasing coverage. It also directly translates into uncovering real impactful bugs in production-grade systems. So moving on from our results, let's look at where model fuzz fits within the broader space of related work. First, there are randomized approaches like Jepsen, which uses random fault injection to uncover consistency violations, and PCT-CP, which explores the state space with probabilistic guarantees. Then we have some systematic testing methods, such as PSIM and debug. Next, we move on to the learning-based and model-assisted approaches. For instance, QL and bonus max RL use reinforcement learning to guide their exploration. On the model-assisted side, Mockit directly generates traces from the model. Trace validation checks executions against model specifications, and must integrates validation checks. Must adds model checking for runtime verification within systems. Mallory and model fuzz creates a middle ground here. So Mallory doesn't directly use a model, but while Mallory allows the usage of TLA plus specifications, where they leverage the specifications to annotate interesting events within the source code. Whereas with model fuzz, we more explicitly use them for coverage feedback. Now, so let's look at one of the most closely related works in this space, as we've shown, which is Mallory, a Jepsen-based reinforcement learning-driven fuzzer for fault injection that guides the exploration through user-annotated points of interest. So we compare model fuzz and Mallory on our shared benchmark, Redistrap. The first key difference lies in how they learn from executions. Model fuzz runs many short tests, while Mallory learns through one single long execution. Because Mallory's long execution produces event traces too large to model check directly, we modified its implementation to collect abstract state information during runtime through logging. We then reconstructed the sequence of system states using the same model state definition as we use in model fuzz. So on top, we show the abstract model state coverage of Mallory and model fuzz under the same abstractions. Both perform similarly with model fuzz, achieving slightly higher coverage. In our model, we also include a set of active processes, capturing crashes and restarts, as part of the abstract state definitions that we have in our TLA plus model. Since Mallory's logs lack this information, we also provide a comparison on the bottom, excluding these details, where coverage remains similar. On the bug finding side, model fuzz replicated 2 bugs previously found by Mallory, and we also have 11 new bugs that we found. So in general, overall, they have complementary bug finding capabilities. So finally, we also have our limitations. It mainly consists of having a balance within the model. So if the model is too abstract, it will miss important behaviors, such as like process crashes or restart. But if it's too detailed, it ends up distinguishing between similar system behaviors. So the real challenge here is finding a balance within the model. So to conclude, going back to our initial slide, we had some questions. Now we answer them with model fuzz, a fuzzing approach that leverages abstract formal models and uses them to guide exploration in distributed systems. We showed that it improves coverage, consistently finds bugs, and even uncovers previously unknown bugs in real RAF implementations. The key takeaway here is that abstract models aren't just valuable at design time, but they can also serve as powerful guides for continuous testing of distributed systems. Thank you.
Thank you for the talk. We have time for around 1 or 2 questions.
Thank you, great talk. So I have one question according to the models you're using. So did you implement them? And when you have the model, how easy it is for you to map the model state to the implementation state? Say like I don't really know RAF, like how long does it really take for me to map those 2 parts?
So the first part of the question, the models already exist. So there's a huge repository of existing protocol, like TLA plus specifications. We focused on that. And the mapping is actually the mapping of events to the model actions are actually quite simple. So let me give you an example on Raft. Like the model itself uses elect a leader. So you can just, whenever you elect a leader, you can use it as an event, or it uses messages as actions. So you can just map them directly. So implementations are also driven by the models themselves.
Thanks.
Thank you. We have to go to the next speaker. I think my microphone is working. The next talk is testing random generators property-based testing as probabilistic programming. Ryan Toja is going to give the talk.
Thank you. Hello, I'm Ryan. I'm here to talk about how to use probabilistic programming to get better distributions out of the generators you use for property-based testing. So first, property-based testing, or PBT, is a technique that validates a system under test against an executable specification or property. For example, if we'd like to test the list reversal function, we might want to use the property that whenever you reverse a list twice, you get back the original list. And then to test this property, we use a program which we call a random data generator, which will randomly generate samples that are inputs to our property. So here, we'd randomly generate lists. And in PBT, the effectiveness of our testing depends on the distribution of our generator. So let's look at an example. Here's a generator for Boolean lists of up to length n. In the common case, we first use the frequency combinator in order to uniformly choose between two branches, since both have weight 1. It either chooses nil or cons, and in the case where we generate a con cell, we use flip to generate a Boolean payload for our list. That's true half the time and false the other half. And now we can run our generator to get our set of samples. But immediately, we can see that this set of samples isn't very effective for random testing because almost all of the lists are empty or have only a few elements. And this is because of the weights we chose for our random generator. In particular, if you evenly choose between generating nil or cons, half of your lists will be empty. So instead, we can generate cons more often, say 3 times as often as we generate nil, and then rerun our generator, and we get a better set of samples. But we shouldn't be satisfied with this process for a few reasons. The first is that in general, it's difficult to reason how the weights of your generator affect the final distribution, especially as the generator gets more complicated. The second reason is that we were pretty ad hoc in coming to this distribution, and we'd like more principled ways to find distributions that are better at bug finding. So this problem of generator tuning is well recognized in PBT. Some of my collaborators did a study on how developers use property-based testing, where they found that choosing probabilities is a mental strain. And there's a good blog post by John Regier in which he says that the most difficult and unsatisfactory part of engineering a good random tester is setting the probabilities properly. So we've seen the problem, which is that controlling test distributions is critical but difficult. And our proposal is to instead automatically tune our generators for desirable distributions. And to do this, we view generators as probabilistic programs. And this is useful because the probabilistic programming community has developed many techniques to reason about the distributions of probabilistic programs. So we can use these techniques to tune our generators. To see what we mean when we say that generators are probabilistic programs, let's look back at our example generator. The key property of probabilistic programming is that the result of a probabilistic program, or its semantics, isn't a single sample, but rather the distribution of values that it can produce. So here, we see that our generator has a 50% chance of generating nil. And then, because we don't actually know what weights to choose for our generator, we can use symbolic weights instead. So here, we've chosen theta n and theta c for the relative probabilities of choosing nil and cons, and theta t for the probability of the flip being true. And the key part here is that this now gives us a symbolic distribution, which allows us to recast the problem of generator tuning as finding assignments to our symbolic weights that result in the most desirable distribution. So as a simple example, let's say we want to maximize the probability of generating the list false, false. Well, this probability is right here in our symbolic distribution, so we just maximize this expression, which turns out to be done by setting the values of theta n, c, and t to 1, 2, and 0. And this example actually demonstrates the workflow that results from our approach. As the input to generator tuning, we have a generator with symbolic weights, such as the bool list generator we just saw, and a probabilistic objective, such as maximizing the probability of generating false, false, or maybe more realistically, something like targeting a uniform distribution over list lengths. Then as the output of generator tuning, we get our tuned weights. We have two main contributions that support this approach. The first is that we actually have to implement a probabilistic programming system that allows us to learn weights. We call this system loaded dice. The second is that once we can tune, we need to know what to tune for. So we propose some generator independent objectives that allow us to find bugs faster. And in our evaluation, we find that when tuning type-derived generators, we find bugs 3 to 7 times faster. So the rest of this talk, we'll go into each of these contributions in some more detail. First, we'll talk about how we implemented loaded dice. So we'll start with a simple example that's basically as simple as possible just to fit on the slide. We'll say that our generator is if a flip with probability theta is true, we return 2, otherwise we return 3. And our objective will be to target the distribution where we always return 2. Just as a quick aside, so far we've been saying our objectives in English, but the way we really specify it is as a function from distributions to real numbers that indicate how desirable those distributions are. So as we saw before, the first step was to, for a generator, compute the symbolic distribution of the samples it can produce. So for this generator, it can generate 2 with probability theta, or 3 with probability 1 minus theta. And then what we do is we combine the symbolic distribution with our probabilistic objective in order to get a loss function, which is just an expression we can minimize in order to find the theta that optimizes our distribution, that optimizes our objective. So here, this ends up being a theta of 1, as we'd hope. There are 2 main components in this process. The first is probabilistic inference, which is the task of computing the distribution from a probabilistic program. And the second is gradient descent, which we just use to minimize the loss function. Now, in implementing this, there are 2 main scaling challenges we face. The first is that the naive method for computing the gradients of a probabilistic program requires enumerating all of its execution paths. And the solution here is that it turns out that the state-of-the-art technique for doing probabilistic program inference is differentiable, so we can use the same technique to compute gradients. This technique is knowledge compilation. We don't have time to get into the details, but the gist of it is that for every sub-expression of the probabilistic program, we use a BDD to represent its distribution in a compressed form. And then, even once we can compute gradients, we still have the problem that some of the objectives themselves that we'd like to tune for, such as entropy, which we'll discuss soon, enumerate a generator's distribution just to express. And what we do here is we create gradient estimators for these objectives that allow us to approximate their gradients by sampling without needing to compute them exactly. And the specific technique we use here ends up looking like reinforce for those of you who are familiar with it. So with these improvements, we now see how to tune generators, but we'd also like to know what to tune them for. In some cases, the user might have a specific desired distribution in mind, and we can tune for this by setting our objective to minimize the distance between the generator's distribution and the desired distribution. And we can use a standard metric for distance between distributions, such as KL divergence. But the user doesn't always have a distribution in mind, so we'd like to find properties of distributions that are useful for bug finding in general. Turns out there are already some well-recognized properties that follow this in PBT, specifically validity and diversity, but we find that when we tune for these individually, they naturally conflict. So first, validity is useful when there are property preconditions you'd like to satisfy. So for example, for this generator, or for this property, it tests that for any colored binary tree, if it's a valid red-black tree, when we insert a key and value into it, then it should still be a valid red-black tree. And the thing to notice here is that if we generate a tree that's not valid, then this property is vacuously true, so those samples wouldn't even test the insertion function. So we want to generate valid red-black trees. And we can express this as an objective straightforwardly, where we want to maximize the probability that our generator produces a valid tree. But when we do this, we find that we get trivial samples. It turns out the easiest way to generate valid red-black trees is just to generate trees of one node. And it turns out this actually makes us generate fewer unique valid red-black trees than our untuned generator. But this actually points us to the other desirable property, which is that we'd like some notion of diversity among our samples. The intuition here being that diverse samples will exercise more execution paths in your system under test. However, when we tune for diversity, which we do so using a standard metric for the diversity of a distribution, entropy, we find that this is degenerate in a different way, that it incentivizes large invalid samples. Larger trees are easier to make diverse, but harder to make valid. So again, we find that when we tune a generator for this objective, we actually end up doing worse than our untuned generator. And these two objectives are in genuine conflict. We can't just take a weighted combination of them. So instead what we do is we propose a new objective that we call specification entropy, which values diversity, but only within the valid subspace of samples. And as we'd hope, when we tune for it, we find many more unique valid red-black trees than the other objectives we considered. As an example of using this objective, we took a generator for terms of the simply typed lambda calculus and tuned it so that it would make samples of diverse types. So this chart shows the distribution of the types of the terms we generate throughout tuning. At the beginning, most of the terms we generate are not well typed or of type bool, but by the end, there's a wide representation of types, none of which are overrepresented. Of course, this distribution looks good for tuning, but what we really care about in property-based testing is whether or not we're actually finding bugs. So for this, we performed an evaluation on ETNA, which is a set of PBT benchmarks. It contains a standard set of pre-placed bugs and properties, and we used it to determine the bug finding speed before and after tuning. And we found that when tuning type-based generators for specification entropy, we found bugs 3 to 7 times faster. So to conclude, we present an approach to automatically tune generators via declaratively specified distributions. Thanks for your attention.
Thank you for the talk. We have time for a few questions.
John Hughes, Chalmers.
Yeah.
So one interesting kind of test case is that collisions of values may be interesting. For example, when we test registries, you may want to generate the same name repeatedly. So can you specify that kind of property in your distributions, that you want some correlations between generated values?
Yeah, so I guess I could imagine you have a generator that produces 2 values, and then like on that you can specify like any property of the distribution. I'm not sure exactly how you'd want to incentivize 2 values to be the same, but...
No, so I'm imagining that you generate a sequence of operations, each of which manipulates a name in the registry, and then you're going to be generating the names separately, but it's a good idea to generate from a small set of names so that you often generate the same name twice.
Yeah, I think that's definitely an interesting direction to explore. I'd be curious if we could find objectives that target that.
Cool, thanks for the very cool talk. So one thing you can do, that might be easier to do than manually tuning a distribution is writing your own unit tests, right? And that's in fact what programmers often do. And one other thing you can do with probabilistic programming languages is maximize the probability of some observed data. So I'm kind of curious whether you guys have thought about, or your system can handle the case where instead of manually giving a distribution, the developer writes a bunch of unit tests that might be sort of look like the distribution they expect test cases to come from, and then you optimize the generator to match that.
This is an interesting idea. I think we haven't considered it, but I guess you could imagine the tension here is that if you've already written those tests, you want to kind of extrapolate to find more interesting things. So maybe we could tune for them, but then add some kind of regularization parameter so we don't exactly generate those samples. There's some details on the paper here on how we can regularize weights. Definitely sounds interesting to try.
Cool, thanks.
Hey Ryan, thanks for the great talk. One thing that I was wondering is what happens if you provide an objective function that sort of fundamentally is unminimizable with respect to the generator template that you've been given, right? Like if I really ask for uniform distribution with the sort of 1, 2 weights, what happens?
Yeah, that's a good observation. So I guess when we choose numeric values for the weights of our generator, the generator structure itself limits the set of distributions that are even possible to a particular set. And the thing we do here is we have techniques to basically increase the tunability of generators so that you can inject dependencies into your weights so they can express a wider array of distributions. And there's more detail on that in the paper.
Awesome, thanks.
Thank you. To move now. We have to move now to the last speaker. The talk will be about understanding and improving flaky test classification by Shanata Raman.
Hello, everyone. Thank you for the introduction. Hello, everyone. My name is Shanta Rahman. Today, I'll talk about our research, understanding, and improving flaky test classification. Flaky test is a test that can pass or fail non-deterministically when running the test many times. Let's assume we have a list of tests that are running in CI/CD environment. Oh, okay, sorry. Extend. Sorry. So flaky test is a test that can pass or fail non-deterministically when running the test many times. Let's assume we have a list of tests that are running in CI/CD environment. So when we run the test, at the first time we find that test 4 is failing, and then in the next run no test is failing. In the next run we again find there is no test failure happens, and then when we run nth time we find another test, which is test 3, is failing. So this test 3 and test 4 are known as flaky tests. So flaky tests are very bad because developers very frequently lose their trust on the test suites. So flaky test is everywhere. Google, Apple, Microsoft, BMW, Meta, they all report that flaky tests hurts their CI system. What a flaky test is? So here is an example of flaky test that is taken from an open source project, and here we see that in this test at line 5 a thread object is created, and then at line 9 it is checked that if thread object is still alive. So the expectation is that that thread will no longer alive after this 1500 milliseconds. However, the problem happens if the thread could not finish its executions within that time. At that case, test failure happens. So what makes the test flaky? So there may have different reasons why a test is flaky. For example, async await can be one of the reasons why a test is flaky. Concurrency, time, order dependence between the test, unordered collections are the root causes why a test is flaky. Now the question is, why do we care about knowing the root cause of flaky tests? So it is important to know the root causes of flaky tests because we can directly apply the repair strategies to that type of flaky test, because prior studies shows that to repair any specific category of flaky test, we first need to know the category of the flaky test. Now the question is, how can we know the flaky test categories? One possible way can be manual inspection. However, manual inspection is very time consuming. That's why we might rely on a classifier that can predict the category of the flaky test. Here the expectation will have a classifier, and there will be a test that we want to send to the classifier, and the classifier will tell us the category of that test. In this paper, we have two major contributions. The first one is flaky test classifications, and the second one is understanding the classification model. Now I'll talk about each of the steps one after another. First, investigation of existing flaky test classifiers. Flakify is one of the popular and prior state-of-the-art technique that predicts if a test is flaky or not. We ran Flakify to classify input categorize multiple categories, and we find that the macro F1 score is 81.82. However, when we look at the Flakify implementation, we find a major critical bugs. And we find that when they load, the bug is in during the loading the codebart model, it happens that each of the fault, they reuse the previously fine-tuned codebart model instead of reloading a fresh pre-trained model. As a result, data leakage issue occurs because a test can appear in a training set of one fold may appear in a test set of another fold. And after fixing this issue, we find that the F1 score goes down to 56%. We report these findings to the Flaky'5 authors, and they acknowledge our contributions and they updated their code base. And then we also look at their evaluations. What are the data sets they consider to evaluate their techniques? We find that in existing technique, that is Flaky'5 considers 5.5 times more flaky tests than the non-flaky tests. Another technique, which is FlakyCat, that contains only different category of flaky tests. There is no presence of non-flaky tests. However, in reality, we see that flaky tests are rare. Google report that 1.5% tests are flaky. Microsoft found that 4.6% of their tests are flaky. So here the question comes, then if we do some training on unrealistic data set, then our model will be biased. Hence, we propose FlakeBench, which is a realistic flaky test data set. Here our main goal is to increase the number of non-flaky tests. So that's why we start with all the projects that FlakyCat dataset contains, and we collect all the unlabeled test methods. Then we run each of the tests 100 times, and we consider each test as a valid one if we don't find any intermittent failures. And finally, we got 280 flaky tests, which is only 3% of non-flaky tests. And this also indicates that our data is highly imbalanced. So to work with this highly imbalanced data set, we propose a new fine-tuned model that can classify if a test is flaky or not, and also the category of flaky test. Here in our experimental design, we enforces the project-wise disjoint split instead of stratified k-fold cross-validations. And during model training, we also enforces the strategy so that it can handle the high imbalanced data set. For example, here we consider focal loss instead of cross entropy loss. We also use L2 regularization to give more penalty on the higher weight. Now our research question comes. Here we first look at how flaky lens perform on FlakeBench dataset, and then we also look at, we also compare our result against the open source generative language models. So here we see that when we fix Flaky'5, we find the result goes to 56.62, and our flaky lens can achieve 65.79% F score, which is 9.17 percentage point improvement. And when we compare against the open source generative language models, we find that our technique flaky lens performs the best for all category of flaky tests. Now, once we get a comparatively better model, now our main investigation point is what makes a model to make some decisions. Hence, we consider these contributions, that is understanding the classification model. Here I am again bringing back the initial example that I showed, and this test is an asynchronous flaky test, and we find that our model that is flaky lens can correctly predict the category. However, like now we want to know what are the tokens that are getting more importance. Hence, we calculate the token importance. To calculate the token importance, we measure the integrated gradient, confidence score of the model, and also how many times that token comes across different tests. And based on that, we find the attribution scores per token, and we find that for this test, we find sleep is the token that is getting maximum attribution scores. For the details, please see our paper. So here we see that what are the important tokens. Can we make some generalization per category? So here we see that here we include top 5 tokens per category. These are the most important tokens, and we also report the least important tokens. We see the attribution scores for the most important tokens are very high compared to the least important tokens, which are close to the 0. Now, we are interested to really know, like, are these important tokens actually impacting the predictions? So hence, we apply the data perturbations. And in our settings, data perturbation is works in a way that we change the code, test code, but without changing any semantics of the code. Here we apply 5 different types of data perturbation: date code, print statement, and 3 more. Here's an example how date code data perturbation works. So here it is clearly clear that this code block will never be executed because it's a while false block. And then, however, still we see that when we inject this data perturbation, our model predicts this test as a time category instead of async wait. So the reason is very clear because there are lots of tokens here that contains the time keyword. So now we want to see like how what is the impact when we consider it on per category. So is it still happening in all the tests or how the result drops? So here we see that when we apply the data perturbation considering the most important tokens, we find the accuracy drops 18%. And then when considering the least important tokens, it drops 8%. And also the minimum one is 8.32, but when you consider the least important tokens, it is only 1.76. So it clearly indicates that when we are considering the most important tokens that have the most effect in making the predictions. So in conclusion, in this paper, we built FlakeBench dataset that considers a more representative mix of flaky and non-flaky tests. And we present flaky lens, an improved flaky test classifier. We identified important tokens based on the attribution scores. We confirmed that their impact actually matters in making the decisions. Our code and repositories are available here. And on a side note, I would like to mention that I will be in the academic job market this year. I'll be happy to chat more about my research and for the future collaborations. Thank you.
Thank you for the talk. We have 2-3 questions before we can go for the coffee break. So,
hi, I'm curious. So I might have missed it on the slide, but is there a possible category of a flaky test where it seems like the test itself isn't the cause of the flakiness, but actually the system under test? So like, let's say that there's a data race going on,
yes.
but it's really subtle.
Yes. So the question is like, if the test can be flaky because of the code under test? Or
yeah, so is it able to classify, so you're classifying tests are flaky because the implementation of the test itself is flaky?
Yes, yes.
So what if there's like flaky behavior in the system under test?
Yes, yes, it can happen, especially like the example that I'm showing, the thread is waiting for few milliseconds to finish the other task, for other threads to finish its executions. So most of the cases it happens that that thread is waiting on the code under test to execute its task. But the problem happens if the test and that code under test is not properly synced. In that case, the test becomes flaky. Yes, that can happen.
Right. So like the solution there would be to like change the test, right?
Change the test, or like we have one paper before where we introduces the synchronization between the test code and the code under test. So we collect some systematically analysis and we find that location where to add the synchronization between the test code and the code under test.
Right. So like what happened? Is it able to classify like there's not an issue with the test, but the thing that you're testing actually has a data race. So you're having a flaky test that happens to find an issue every once in a while, but it's a legitimate bug that it's finding. So is it able to categorize that, or is that like kind of something that it can't find?
Yes, so if it happens that there is no problem in the test code, but still it is a data race issue, our test, and if it does not observe in the output, like if the test failure does not happen, then we are not considering as a category.
Okay, so that was just my question. Yeah, thanks.
Okay.
Hello. For these important tokens, which I guess correspond to different methods that people use to write their tests, are we able to just ban them and write all of these tests using other methods that avoid all this flakiness? Like, can you create a linter using the tokens you've identified and to reject them?
So that's a very interesting and good question. So once we know that, okay, these are the tokens that can make that test flaky, for example, thread.sleep. So that's like we want to make developers aware about that okay, this type of uses of thread.sleep can make the test flaky. So instead of doing that, we encourage the developers to use some other technique, for example, synchronization between the test code and the code under test, or some other, for example, thread.yielding, or some other things that, so that this specific weighting we can overcome. So that's the key point we investigate. That's the reason we investigate the tokens things.
All right, thank you.
Okay.
Thank you.
Thank you.
Session and.
Thank you all for coming to one of the last sessions of the day on software testing. We are going to go ahead and get started right away. If you're a speaker and you haven't talked to me, please do that. Otherwise, I will introduce our first speaker, Zen, who will be talking to us about randomized specification testing for heap manipulating programs. Take it away, Zen.
Yeah, so thank you for the introduction. So I'm not going to repeat my name, but yeah, I'm talking about randomized specification testing for heap manipulating programs. This is joint work with Benjamin C. Pierce. So our motivation is that we want to catch bugs in low-level software. So this is like things that are critical, so system software, embedded software. And we want to do this by applying property-based testing, which is that given some property, we want to generate random inputs and see if the property holds. And so when we look at applying PBT for heap manipulating programs, first thing first, like we have this random generator. Writing these generators is tedious, so we don't want to require the user to do this. For functional languages, tools can derive these from the types, but void star, what does that even mean? For theorem provers, they have certain preconditions that they can generate these generators for, such as inductive relations, but they don't target programs in languages like C. And so we want to derive generators for C functions where our property is going to be a precondition postcondition pair. And so a really important question is, what is a good program? What is the specification language that's defining this precondition postcondition pair? And so we want something that captures complex memory ownership patterns. We can check it at runtime so we can test it. And we want to be able to generate inputs that satisfy the precondition fairly quickly. And so we will look at separation logic. In particular, we will look at a fragment used by CN, which is a verification tool for C. And so in their paper, they showed that they can capture quite complex ownership patterns. There's also work fulminate, which we depend on as like our test oracle, which will take a CN specification and turn into instrumentation that will check that it holds at runtime. So our contribution is automatically generating inputs that satisfy preconditions. And so in general, summing everything up, like our approach is going to be randomized backtracking search. And so Bennett, our tool, will boil down to these steps. We start off with a CN preconditions and some predicates. We will convert that into a generator DSL. We then apply some not so interesting but necessary optimizations to simplify logical constraints, reorder when variables are generated. We then have a notion of size generation, which I won't be able to cover due to time constraints. And then finally, this goes down into a bunch of generators in C code with like no external dependencies. And so what do CN specifications look like? This might be a little bit of a surprise. I'm going to kind of quickly go through this, but I'm going to look at this from the angle of fulminate. So this is instrumentation. So we have a concrete heap on the right. We have a predicate on the left. This predicate's saying that we have a list of positive integers. We're going to say we give it a pointer, 1, 2, 3, 4. You check if it's null. Take the else branch. We have this primitive called owned, which states that it's exclusive ownership. And how fulminate would track this is that it will mark the relevant bytes and say that this has been had ownership claimed of it. And so then if something tries to claim ownership a second time, you know that there's an issue. Assertions, it just checks that they hold. And so you end up with writing predicates in this format where you take in pointers or the arguments to your function and you're producing the mathematical representation. And so then we want to have our generator DSL where we have a clear translation from the CN specification, the precondition. We want to satisfy all the constraints that CN expects. So this is logical constraints like the assertion, as well as resource constraints like the use of owned. And we want to have a relatively clear translation to C, though we can only do so well. And so our DSL largely looks like CN, which makes the translation quite trivial. We're going to track when we generate values and place them in memory, which will correspond to ensuring that we have exclusive ownership. We will be pretty explicit about the points that we can backtrack to, which helps us simplify the C implementation. And there's like a whole monadic semantics. I'm not going to cover it in the talk, but it's all in the paper. And so I'm omitting a bunch of things because they will just map one-to-one. So assertions will map to assertions, if-else to if-else. But considering what the previous predicate we looked at, we have this word take. Take means that on the right-hand side, you could be reasoning about resources. And so we will transform this into a let star, which means that on the right-hand side, we're dealing with a generator. So there's some randomness involved. And then in the case of owned is saying that P, we have ownership of some P, where we have some C-type data there. And the data that's there is X. And so rather than reading from P and setting the value of X, we're instead going to generate some X, which is going to be an arbitrary value of that C type, and then we're going to assign it to location P. And so one thing is that we are going to check every time we assign anything that it does not overlap with pre-existing assignments. And so since each assignment corresponds to the presence of owned in the original predicate, this is going to preserve exclusive ownership because we're ensuring none of these things overlap. And then let star is going to be the points that we can backtrack to, since that means that there's a generator on the right-hand side. There's a slight caveat there, but I'll show it. And so this is what the generator that corresponds to the predicate we saw would be. And so this is largely the same, but suppose we generate some P, it points to some memory, 8 bytes, let's say. We'll check, is it null? We'll generate some arbitrary struct list node. We'll try to assign it to P. And so suppose, previously we had like 2 blocks. Suppose it only has 8 bytes, but we need 16 to be able to perform this assignment. And so what we do is we will backtrack. In this case, since P is an argument, we will backtrack to the caller. And we will, importantly, carry information with this failure and say that we need at least 16 bytes. And so P will be reallocated with at least 16 bytes. And so then we re-enter this generator. We're going to generate another arbitrary struct list node. Important to note is that it's not a coincidence that the value of head here is -10, and it was -10 before we backtracked. After we backtrack to reallocate specifically, we will always make the same choices. This is because otherwise you would end up skewing the distribution of outputs to be smaller, because the larger an input that you're trying to generate, the more likely you are to backtrack to reallocate, which would regenerate a bunch of values. And so you have to really make sure that you make the same choices. And so we want to guarantee exclusivity, and so we'll do a very similar thing to what Fulminate was doing when it was checking the predicate. We will instead mark when we assign to a location to make sure that we never assign to the same location. And so then we will check an assertion. If an assertion fails, we will once again backtrack. In this case, since we backtracked before an assignment, we're going to unmark the assignment. So we went to the let star n. And we are also going to carry information when a logical assertion fails. In this case, it's going to be the variables we like quote unquote blame. The approximation we do is that we just take all the variables that are mentioned in constraint. So in this case, n.head greater than 0, the only variable mentioned is n. So we're going to try to regenerate n. And so if you keep doing this, eventually you can generate the same list that we saw with the predicate. And so what are the optimizations? So one thing, it's quite naive, but we break apart a bunch of logical assertions. And so in terms of like the and, this is quite simple. We introduce a syntactic form which does not correspond to anything that appears in CN, which is pick, which is just performing a weighted choice. Technically, what it's doing is it's doing a choice without replacement. So if it chooses one of the generators, that generator backtracks all the way to the top. It will then try a different option and keep going until it exhausts all the options. However, one thing that's important is you actually have to be quite careful when you're doing this. If you look on the right-hand side of how we're dealing with the disjunction, we're turning it one generator into 2 generators, which we're choosing between. However, if E1 and E2 are constraining the output of another generator, there's like a really specific case where we provably know that we're going to make our generator worse, and we're going to result in like more backtracking, we're going to be less likely to generate an input. And so this is detailed in the paper, but you have to make sure that you do not break apart disjunctions like that in that case. And then there's a reordering pass. We're going to, in varying levels of priority, our first priority is if we see any constraint where we have some variable equals f of some other variables, we want to generate the thing that's on this x after the values into the function. The reason why is because then instead of generating an x and checking if it's equal to this expression, you can just set the value of x equal to the expression. And then as a second thing, we also want to bias recursive generators to be called before primitive ones. And so if you imagine generating a binary search tree, you have a node, you want to generate 2 subtrees as well as the value at the current node. It's cheaper to generate the value at the current node, and so you want that to be generated later so that when you backtrack, that gets regenerated first. And then otherwise, we preserve the existing order. We also will check constraints as soon as possible. So we will take, for example, a constraint over A, B, and C and move it to right after all 3 of them have been defined. And so then we know as soon as possible if we've failed some constraints, so we can start backtracking. And so I will go straight to the evaluation. So does Bennett work with existing CN annotated code? So we took the CN tutorial, including some extensions that were used in the evaluation of the instrumentation fulminate. For nearly all the non-buggy examples, we're able to generate 100 passing test cases. Discards here mean that it backtracked all the way to the top, or it exceeded a set time limit. There was only one case where we failed to generate an input, and that's because the precondition required specifically the list 1, 2, 3, 4, 5. And so we did not end up doing that. We did, in fact, discover 2 bugs. There was an assumed fact that was used in the proof of the correctness that for pushing to a queue. And so we discovered a bug in that, and then we also discovered an incorrect base case in one of the extensions from fulminate. And then can Bennett find injected bugs? So we compared against handwritten AFL++ harnesses, which are guaranteeing that the memory shape is correct, but the logical constraints AFL++ is in charge of getting past. Here, if you look at the table, tasks are defined as a bug that we injected, the function that's being tested, as well as versions of specification. This is because for our recursive data structures, there's like many ways that you can write the predicates. We didn't even fully exhaust them, but we cover a decent set of them. And so solved here means that for one of these tasks, the bug was found in all 20 trials. And so in the case of Bennett, we were able to, in all these trials, find all the bugs and do them quite quickly. Now, do our optimization passes matter? Because they're not that interesting. And so in this visualization, which is taken from Aetna, which is a work on evaluating PBT, the numbers are these tasks that I just talked about, and they're kind of colored based off of how quickly they're found. And so you can see that if we disable the reordering pass, then in the case of the AVL tree, it will keep regenerating the right subtree before it tries regenerating the value at a particular node. And so out of the 26 tasks, 24 of them we do not find the bug consistently. And then if we disable the lifting pass of breaking apart the logical constraints on this runway simulation, which is the most complex logical precondition we had, then out of the 6 tasks we had, 5 of them fail to be solved consistently. And so the end, we synthesize generators from CN specifications. CN syntax makes this transformation relatively intuitive, and we kind of frame the synthesizing of these generators in an optimizing compiler.
Are there any questions?
Is the, so the separation logic aspect here is just that in the CN language, when it's calling owned, that correlates to a points to. And so take x equals points, takes owned p is p points to x. And so as far as we're concerned, we don't really care that much about the fact that it's separation logic. And so if you have a fragment of separation logic which constrains existential quantifiers where, so there's a paper, Brotherston et al. 2016, I want to say, Popple, which is model checking symbolic heap separation logic with inductive predicates. There's a fragment that they define in there, which is polytime to model check. I believe that fragment's very similar to the fragment that CN falls under. And so technically, this doesn't necessarily require CN's syntax. It becomes a lot more intuitive because of it. But in theory, if you're within that fragment, you can still apply the exact same thing. It's just that you don't have this nice, we turned one thing into a thing that looks the same. You'd be going from a logical formula to a program.
Hi, great talk. You mentioned that one of the examples that you couldn't solve was looking for a very specific list. Do you think if you took the optimizing compiler inspiration even further, you could sort of compile all the way to just figuring out that actually to get that exact list, you just generate the heap with exactly that list by construction?
Yeah, so there's actually a couple, okay, so there's a lot of PBT work which is specifically from Haskell, and so they take advantage of laziness a lot. And so to some extent, in this case, what you can do is you have a recursive predicate, you can unfold it once, kind of interpret it lazily where any recursive call is treated as undefined, evaluate constraints and see if one of them is definitively wrong. And so in this case, that actually does solve the input for that. However, we ran into an issue where there used to be a bunch more optimizations. However, improvements to the runtime meant that the time to actually generate a single input, even if you backtrack a lot, became like very small. And so we would have to find workloads, like we'd have to find bugs which take a lot of time to discover, because otherwise, even like a relatively fast pass on the front end, potentially you could find by doing something dumber, but you just like send so many inputs so fast.
Got it. Thank you.
The speaker. While the setup is going on, our next speaker will be Cheng Yang, who will tell us about efficient smart contract fuzzing with functional dependence guidance.
Good afternoon, everyone. My name is Chen Yang from Nanjing University of Science and Technology. Today, I'm honored to present our work, DepFuzz, a function dependence guided smart contract fuzzer. I'll structure my presentation into these 5 main sections. Let me begin with introduction. First, we introduce some background knowledge about smart contract. Smart contract typically consists of 2 core components: the stored variable and its functions. Functions are invoked by transactions to execute user-defined operations, such as token transfers. The stored variables record the outcome of these executions. So the 2 transactions can interact with each other through the stored variables. Smart contracts are often closely tied to digital assets. Therefore, this vulnerability often don't cause crash like traditional programs, but can be maliciously exploited, leading to significant financial losses. Detecting smart contract vulnerability faces 2 major challenges. First, during transaction generation, the parameter space is vast. Second, when generating sequence of transactions, we encounter the problem of transaction combination explosion. We leverage an example contract promise to demonstrate these challenges and motivate our work. The contract contains unprotected self-destruct vulnerability. However, the function self-destruct cannot be successfully invoked under the initial contract state because the condition on line 34 is not satisfied. To trigger it, one has to first call these 3 functions, judge, sign, waterfall, and center, 6 times. One can say that the number of possible combinations for random calls is explosively large. Okay, therefore we define function, but we observe that the key to find this transaction sequence is to find that the function judge sign depends on function waterfall. The dependence between functions can guide us to find the sequence more efficient. Function dependence describes a situation in which the invocation of one function cannot proceed unless a second function has been invoked first. We quantify how close a function invocation is being able to proceed using the concept of distance. Based on this, we developed DepFuzz, a function dependence guided smart contract fuzzer. DepFuzz takes the contract's bytecode and API as input. The output of DepFuzz is a detected vulnerability. DepFuzz contains 5 main components: the initial fuzzer, transaction trace analyzer, symbolic executor, dependency guided fuzzer, and vulnerability sanitizer. Now let's discuss each of these components. First, the initial fuzzer. Initial fuzzer used to test each individual functions. We here leverage the traditional hybrid firing steps to generate transactions for fuzzing. Different from traditional fuzzer, we define various distances to guide the fuzzing procedure. The initial fuzzer first calculates the distance for 4 common types of branch conditions, define how close a transaction is to triggering a branch. Based on this, it further defines the distance to trigger a pass. Furthermore, since covering a pass doesn't always immediately trigger a vulnerability, we also define separate distance for 2 common vulnerability types, integer bug and leaking ether. Let's turn into the transaction trace analyzer. Transaction trace analyzer is a key model that helps dependency-guarded fuzzer to generate transaction sequences. The purpose of transaction trace analyzer is to create a transaction pair involving read after write dependencies. Its main step, it consists of 3 main steps. That is, first, identifying the variable type. Second, driving symbolic expression of the key of the values. Third, imposing symbolic constraints upon the key of the mapping or array type variable, and imposing symbolic constraints so that the 2 transactions can write or read the same variable with the same key. This is indicating the involving read after write dependence. Next is the dependent guardian fuzzer. Dependent guardian fuzzer is used for generating transaction sequences for fuzzing. For an unfinished patch that failed to be triggered by the initial fuzzer, we first leverage the transaction pair generated by the transaction trace analyzer to determine the function dependencies. Each discovered dependency help we find one of the transactions in the transaction sequence. We iteratively discover dependencies and update the contract state until all target paths are triggered, all the vulnerabilities are found. Since we use a greedy algorithm to build a sequence, we incorporate a back tracing strategy to avoid the local optima. Next, let's return to our motivating example. To reach a self-destruct function, we first find that waterfall function depends on charge sign in the initial contract state. Therefore, we execute transaction charge sign 0 to update the contract state. In the new state, we find another dependence between waterfall and charge sign. Therefore, we concretely execute charge sign in the new contract state. By repeating this process iteratively, leading us to the final sequence that can trigger the self-destruct vulnerability. Noticing that this sequence alone might miss some of the statement in the code. For example, the code on 31. Because the previously found transaction waterfall 0 makes the variables waterfall 0 and line 24 to 1. This assignment is a conflict to the condition that needed to be satisfied at line 31. Therefore, our backtracing strategy kicks in, reconciling the dependencies between the waterfall and center. We can redetermine the dependence between the 2 functions. So finally, the statement and the line 31 is triggered. Finally, let's examine the experimental results. We evaluated depth fuzz on 5 key aspects: vulnerability detection capability, instruction coverage, and ablation study, and the effectiveness of function dependence, and a scalability experiment. We compare against several state-of-the-art tools, including 2 symbolic detectors and 5 fuzzers. We use 2 data sets, one is from FSE 2024 survey, which comprises 339 known vulnerabilities. Among them are 12 types of vulnerabilities. The first data set is used to answer RQ1 to RQ4. The second data set is originally from SMARTA, which is published at ASE 2021. It contains 500 large real-world smart contracts. The data set is used to answer RQ5. DAP5 detects 279 vulnerabilities in the first data set with no false positives, which is significantly outperforming all other tools. This chart shows the number of detected vulnerability of different tools in 10 minutes. The curve is better on top left. One can see our method demonstrated superior efficiency and effectiveness in vulnerability detection. This graph plots the coverage increase over time curve. DAP5 achieves the highest final coverage. Our ablation study revealed that function dependence contributes the most to the vulnerability detection, while the symbolic execution boosts the coverage most significantly. And the components of DAP5 complement each other. Compared to the dependency notion in the transracer, our approach finds 38 additional vulnerabilities and increases the instruction coverage by 1.5%. For the 500 large smart contract, DAP5 achieved the highest instruction coverage compared to the baseline method, which suggests that DAP5 scales well. Finally, in conclusion, we print an efficient function dependency guided smart contract finder. We also introduced a novel method, transaction trace analyzer, that can actively generate the pair of transactions involving read after the dependence. Compared to state of art method, DAP5 demonstrates high coverage and detect more vulnerabilities, proving that our method is effective. Thank you very much for your attention.
Questions?
I have a question about the transaction trace analysis. Does it happen on the fly together with the flooding process?
It analyzes the transaction trace, the transaction generated during flooding. So it analyzes at runtime.
Oh, so it's one time. Okay, great, thank you.
Any other questions? I have one for you. So you said you did not find any false positive. Does your technique guarantee that there will be no false positive, or that just happened?
We did find false positive on the benchmark data set. So our method does not guarantee that.
Okay, so false positives can happen. Can you say why? What can lead to false positives with your technique?
False positive may be happening because, for instance, our method may find
But any other type of bug?
So we are using the crash to detect the bugs. We're using address sensitizer for bug detection. But for detecting like the correctness bugs, we can simply replace the oracle with like some deep checking or hash level checking, and we can technically detect this kind of bugs as well. Thank you.
So our next speaker will be Xiao Tiang, who will talk to us about finding compiler bugs through cross-language code generator and differential testing.
Hi everyone, I'm Xiao Tiang from Nanjing University of Science and Technology. Today I'd like to share our work on fast testing JVM compilers. The title is Finding Compiler Bugs Through Cross-Language Code Generator and Differential Testing. This is a joint project with JetBrains and Wuhan University. As software systems grow more complex, projects are rarely written in just one language anymore. They are often developed in multiple languages together. For example, the picture on the left shows C and Python calling each other, while on the right, we can see Rust gradually making its way into the Linux kernel. Now compared with language pairs like Rust and C, or Python and C, which rely on C API, JVM-based languages such as Java, Kotlin, Groovy, and Scala have a big advantage. They can call each other directly at the source code level. This figure comes from our earlier study on mixed Kotlin Java projects. We found that Java and Kotlin interoperate seamlessly at the source code level, and such usage are widespread across entire projects. This poses challenges for the compilers. How do we ensure that cross-language compilation remains correct? First, let's look at an example. Here we have a Java interface A, method full, a parameter which type is list T. A Java class B implements A and overrides full with a row type. A class C extends B while also implementing A. Everything works fine so far in Java, but when a Kotlin class X extends C, the Kotlin compiler rejects it, complaining that X hasn't overridden full. Interestingly, if you write X in Java, there's no problem. The issue comes from Kotlin not supporting row types. It thinks that B didn't actually override A's full. So this bug arises from different treatments of row types in Java and Kotlin. Here's another case. A Java class A2 extends a Kotlin class A1 and implements a Kotlin interface I1. No problem here. In Java, class methods take precedence over interface methods, so A2 inherits func from A1. We should know that if A2 is written in Kotlin, it cannot be compiled, because in Kotlin, class and interface methods have the same priority, so A1's func and I1's func conflict. But when a Kotlin class A3 extends A2 and implements I1, things get messy. One Kotlin compiler version accepts it and another rejects it. The inconsistent behavior shows another bug, this time caused by different inheritance rules in Java and Kotlin. These two examples show that while JVM languages interoperate smoothly, the differences in type systems and the inheritance design create tricky challenges for compilers. Naturally, we thought that can we systematically test compilers for correctness on cross-language program. Compared to traditional testing, this brings us two big challenges. The first is program generation. Different languages don't follow a unified standard, so we generate valid cross-language programs. It's non-trivial. Second is legality. Even if we generate programs without a shared design standard, it is not clear whether they should be considered legal. To tackle this, we built a framework called cross-lang-father. The idea is simple. This picture shows the framework of cross-lang-father. Next, we will explain each part in detail. Step 1, we designed a special IR for JVM languages. For inconsistent cases, we adopt the stricter rule. For example, Java lets you skip overriding methods if the parent class and the interface all have them, but Kotlin doesn't. In our IR, subclasses must override them, making the design conservative but consistent. With this IR, we can always generate valid programs. We then apply 3 mutation operators. The first is type changer to alert type arguments. The second is function removal to drop methods. The third is long shuffle to switch languages, such as change the language of an IR class from Java to Kotlin. Finally, a translator converts IR into actual cross-language source code. Step 2. For strictly valid IR programs, we just compile them with the latest Java and Kotlin compilers as normal tests. For mutated programs, as we do not know the legality of it, we use differential testing, fix one compiler, say the latest Java, and test across 2 different Kotlin compilers, or the other way around. If one succeeds, and another fails, we flag it as a bug. Step 3, once we found a bug, we manually minimize bug triggering programs by switching languages, deleting methods, or changing types until no further reduction is possible, and then we report them. Sometimes manipulation itself can uncover new bugs. Here's the IR syntax we designed. Since we mainly concerned with types, generics, and inheritance, the IR doesn't include statements. Our generator can produce 5 to 14 classes and interfaces with configurable inheritance dips and was. The key consistent is overriding rules across languages. This table summarizes them. For example, if the parent class has an abstract method, here in the table is the second line. If the parent class has an abstract method, whether we have interface methods or not, the child class must override it. This avoids inconsistencies like the ones we saw earlier. For evaluation, we tested long-term supported versions of Scala, Groovy, and Java compilers. And for Kotlin, we targeted the 2 front ends, K1 and K2. We set out to answer 4 research questions. RQ1, can cross-lang-father really find compiler bugs? RQ2, what are the characteristics of bug triggering programs? RQ3, what are the root causes of these bugs? We found this is the most interesting. RQ4, how do different processes and mutators contribute to bug discovery? Here are the results. Cross-lang-father discovered over 20 bugs in 4 compilers, all in their latest versions. Most bugs were marked normal or major, showing significant impact. We checked issue trackers before reporting. Only 2 turned out to be duplicates. For RQ2, among the 24 bugs, 17 involved cross-language interaction, 20 involved generics, and most had a relatively deep and wide inheritance. The trigger programs were fairly complex, which makes sense. Cross-language interaction in types, generics, and inheritance are where compilers struggle most. For RQ3, together with compiler teams, we traced bug origins. Of the 7 single-language bugs, 6 came from semantic analysis of inheritance and overriding. The 17 cross-language bugs mostly came from inconsistent type and inheritance designs. Java has looser inheritance and fewer types, while Kotlin is stricter, adding knowable and non-knowable types for non-safety. This raises the question, when a cross-language program fails, which compiler should be responsible? Here is a neat case. A Java class A1 extends a Kotlin class A0, while A0 has a generic parameter nothing. Nothing is Kotlin specific, a bottom type, subtype of all types. But Java doesn't have it. So from Java's perspective, it says A0 as a raw type. As a result, Java doesn't think A0's func overrides A0's func. Since we wrote override, Java reports an error. At first, we thought this was Kotlin's problem, but the Kotlin team marked it a third-party issue. Later, Java accepted it as their bug. This shows that in cross-language compilation, the caller side often has to adopt multiple providers, type system, and rules. For RQ4, how did the process contribute? Normal testing alone found 2 bugs. In differential testing, long shuffle found 5 bugs, and the type changer was the most effective, 11 bugs. Manual minimization uncovered 3 more. To conclude, cross-long further combines a unified IR, unified overriding rules, and 3 mutators to systematically generate cross-long programs. It has proven effective at uncovering JVM compiler bugs, and in practice, we saw that using side often bears more responsibility in cross-language compilation. Looking ahead, we will focus on 2 directions. First, automating program minimization. So far, we minimize the programs manually. We tried tools like CReduce, JReduce, even large models, but the results weren't very good. Luckily, because our programs are semantically too rich, so a feature challenge is how to reduce such semantically strong programs. The second is extending our IR. Currently, our IR is limited. We plan to add more features, such as function-level generic parameters, more types, and richer bounds for generics. That's all for my talk. Thank you very much.
Can take one real quick question if there is any. Meanwhile, let's start swapping the slides. So is it fair to say that currently your technique is limited to cross-language usage where source code can be shared? Like in the case of, say, Java to C, will your technique work?
Actually, Java and C calling each other, they use JNI. It is not source code level.
Okay.
And
okay.
we mainly target at the source code level programs.
I see. Maybe another clarification question. For the differential testing part, do you use your IR there at all, or it's just normal compilation?
Can you repeat that?
So in the differential testing part, the second challenge, in your solution to the second challenge, does your IR play any role in the differential testing?
we use differential testing. That's because the IR the translated source code from IR, the legality is uncertain.
Okay.
So we use the differential testing.
I understand why you use it, but in the process of differential testing, at that point you are done with the IR, yes?
Yes.
Okay, that was my question. Thank you. Let's thank the speaker. For the last talk of the session, Yu Meng will tell us about formalizing linear motion G-code for invariant checking and differential testing of fabrication tools.
Thank you for the introduction. Hi everyone, my name is Yu Meng He. Today I'll be presenting our drawing work with Chandra and Sri. 3D printing is everywhere. Even the consumer desktop printers are used in fields ranging from medicine to everyday products. But the pictures shown here are not always what ordinary users would experience. In reality, many problems can occur in the printed objects. For example, on the left, you see the designs that users wanted to print. These were processed by software and then sent to the printer. But on the right, the printed outputs actually look quite different from the designs. In fact, many printing failures actually come from software bugs. For example, here we show the model that is passed to a slicer, and you will see what a slicer does later. But on the right, you see the preview of its output, which shows what the expected output should look like. And you can already tell the top right corner is going to print wrong. In another case, the original preview on the top looks already pretty bad, but when we try to apply some software to fix it, the result is even worse. More parts are missing. So today, I'm going to talk about how can we catch real-world failures that are actually caused by software bugs. And let's begin by taking a look at the 3D printing software pipeline. So first, users can work with CAD tools to design the objects they want to print. And the design is exported as a triangle mesh, and users may use mesh tools to manipulate or repair the mesh. And next, the slicer takes the mesh along with a bunch of parameters and converts it into G-code, which is the printer instructions. And finally, the printer executes those instructions, extruding filament layer by layer. And if everything goes right, we'll get this cute bunny, which matches the original model perfectly. But if something goes wrong, then the problem can be traced back to any of the earlier stages. For example, the model design itself might just be flawed. It can have some small, intricate features that are simply not suited for printing. The mesh could also be invalid at the geometry level. The slicer could also be buggy in handling certain geometries and thus producing incorrect G-code. So how can we catch bugs in this early pipeline? We can have separate checkers for each stage. For example, finite element analysis for the models, mesh repair tools for the mesh. However, there's still no dedicated checker for the G-code. And by filling this gap, we also realized that by checking G-code, we can also find problems in the previous stages, because those errors all eventually show up in the G-code. And now that we've decided to analyze on G-code, we can apply differential testing directly on it to find bugs. For example, to find bugs in slicers, we can check if two slicers generate the same G-code for the same model. And if they don't, then at least one of the slicers is buggy. For mesh repair tools, we can compare G-codes before and after applying the tool to see whether it fixed a problem or if it introduced new problems. For the models, we can check whether G-codes from the same model, but under different conditions, like different orientations. And if they differ, then the model could be buggy. So in every case, applying differential testing comes down to comparing two G-code programs. And since G-code is essentially a set of instructions telling the printer how to move and extrude the filament, what we really care about is whether two G-code programs are semantically equivalent, meaning that they actually represent the same object. And to make that possible, we first need to define the semantics of G-code. Basically, G-code is the instructions telling the printer how to move the nozzle and then extrude the filament. The nozzle is heated, so the plastic can flow through, which is just like squeezing out toothpaste. And to make it easier to model, we treat every piece of extruded filament as a simple cuboid. And now let me illustrate how G-code works. First, G-code is stateful, meaning that after each instruction is executed, the program state changes. And this state has two components, the current nozzle position and the set of cuboids representing the constructed object. And let's start with the first instruction. So every movement instruction in G-code starts either with G0 or G1. And here we have a G0, meaning that the nozzle will only move but not extruding any filament. So after this instruction, the nozzle will move to position 100.2, but with no extrusion. And for a G1 instruction, the nozzle will not only move to a new position, but also extrude filament along the way. So after this instruction, the nozzle will move to the new position, but also extrudes filament. So there is a new cuboid being added to the cuboid set. And the remaining two instructions are processed in the same way. And finally, the nozzle returns back to the starting point, and there are 3 cuboids in the cuboid set representing the current constructed object. And at the end of this process, you'll have a set of cuboids whose union represent the G-code program. And so now, if we want to compare two G-code programs, we could just simply take two such unions and compute their solid geometry difference. Sadly, this approach doesn't scale. For example, for this Warrior model, it already produces around 138,000 cuboids. Therefore, we decided to sample each cuboid into points, producing a point cloud for the G-code program. So now, comparing two G-code programs becomes comparing two point clouds, and this is the core idea behind our tool, which is called Glitch Finder. So as an efficient G-code diff tool, Glitch Finder goes beyond simple point cloud comparison and tackles several challenges. First of all, to compare two point clouds, the most straightforward way is to compute the Hausdorff distance, which will give us a number to measure the difference. But the problem is, a single number couldn't tell us where the errors happen. So instead, Glitch Finder segments the point cloud into unit boxes and compare them box by box. In addition, Glitch Finder tackles 3 more challenges: floating point errors that happen in segmentation, quantization, and discretization errors, and how can we highlight the largest errors. And Glitch Finder addresses them by introducing what we call augmented Hausdorff distance, combined with spatial averaging and thresholding. If you'd like to know more about the details, please go read the paper. So the output of Glitch Finder is a difference heat map. The color intensity indicates the magnitude of differences. So for this model, the cape region inside the red box has the darkest color, meaning that this area is most likely to print wrong. For our evaluation, we show that Glitch Finder is able to detect both model bugs and software bugs. And let's start with model bugs. So intuitively, a model should slice the same way no matter how it's oriented in the slicer. And more formally, if we have a model and we slice it to get the G-code, and when we apply some rotation on it and we repeat the same process, the two G-code programs should represent the same object after aligning their orientation. But if they don't, then the model often turns out to be buggy. So the motivation for this actually came from GitHub issues from popular slicer repositories. We noticed that users commonly check if the same model slice the same way, but in different orientations. And especially after they discovered that the original orientation has some problems. And by checking this property, Glitch Finder successfully found issues in 56 buggy real-world models. Specifically, Glitch Finder can find common mesh issues, like mesh with fluid normals and mesh that are not watertight, which are the problems that mesh repair tools are designed to handle. So we show one example for each case, and in both cases, the heat maps correctly highlights the problematic regions in the original orientation. Glitch Finder also finds a new class of bugs, which are models that have features that are too small to print. These issues are not detected by mesh repair tools because the concept of smallness is relative to the slicer and its parameters, but not a problem in the model itself. But in contrast, Glitch Finder can find this problematic thin wall design in the heat map. And the other application is to find software bugs. And first is slicer bugs. Glitch Finder compares two slicers, Cura and Prusa slicer, and has verified that in most cases they behave the same, but in some cases they differ. For example, here you can see the Prusa slicer generates incorrect G-code at the area which is highlighted by the heat map. And second is the mesh repair tool bugs. So we evaluated on two popular mesh repair tools, and Glitch Finder helps us to detect if the tool actually fixes a problem or not. So we showed this example earlier also. You can see in this case, not only the tool failed to repair the model, but also introduced new problems. And anything we don't have time to cover today is in the paper. If you'd like to know more about how we distinguish between true positives and false positives, and also the running time analysis, I encourage you to read the paper. So in conclusion, we introduced Glitch Finder, which is a new tool for G-code differential testing. It defines new G-code semantics with cuboid sets and uses an efficient point cloud-based diff that help us to find bugs in both models and fabrication tools. Thank you very much.
Let's take a couple of questions.
Hi. Harry Goldstein, University at Buffalo. This is awesome work, really like it. I had one technical question, which is that when you're printing, if you print two lines out of order, the points or the cuboids, in my mind, seem like they would be the same, but printing-wise, they would be very different. Do you take a look at the order that the points are created, and or how do you deal with that?
I'm sorry, in what way they're different?
So when if the 3D printer tries to print a layer that is too high, and then the layer below it, it won't work. And so those the G code is, but the points that they're printing is the same. Does that make sense?
So you're saying something happened in the printing stage?
I'm saying let's say we can also take this offline, but you've got G code that prints some plastic and then a line of plastic above it. And then you've got some G code that prints the higher one and then the one below it, which obviously isn't going to work.
So they're different, definitely.
Okay, so it would be different even though the points of those two are the same.
Yeah.
Okay.
Yes.
Thank you.
Hi, Roger Burton Patel, University of Pennsylvania. I have a question about the printing pipeline. So would it be possible to go back to the slide where you show the various places that things can go wrong? Great, yeah, thank you. Can anything go wrong in the G-code to printed objects step? And did this ever trip you up? Or is this sort of the hardware print, is that relatively robust?
So many problems can occur in the printing step, but our work is focused on the software.
Yeah, absolutely. I'm just curious if things that went wrong in the print step ever made you feel like the tool wasn't working, but it actually was just that something else was going wrong.
Yeah, so we're now focusing on the problem which happened in the printing step.
Yeah, okay, that makes sense. Thanks.
Thank you for the question.
That's
think it's a very interesting topic to use static analysis technique in the 3D software, 3D printing software. And I would like to ask, do you think is it an easy task to integrate all these systems into some real-world software?
Yeah, so like this should be useful in like differential testing of fabrication tools. Like software developers can use them to test their software to check their correctness. And also like our tool is pretty automated. So now the implementation of this just takes the model and then you can like tell it like what orientation that you want to compare against. And so it would just generate a heat map automatically. So it should be very easy to integrate into other pipelines.
Last question for me. What happened to all those bugs? Did you submit them? What were the reactions to them?
Actually, no. I think I reported one to the QA repository, and they have some experimentation, but no, like, yeah.
Okay. Well, let's thank the speaker, and thank you for coming to this session.
to the end. Can someone tell? All right. Hello, everyone. So if you've seen me in the morning, I'm the SPLASH Steering Committee Chair, Alex. And we are going to run the awards session and a special session at the insistence of Sri Raman, among others, to give you an opportunity to discuss how SPLASH, OOPSLA, Onward, and all of the events that you are seeing this week work. All right, so it's kind of driven by you. So because of that, we're going to quickly go through the awards, because the major ones we actually have awarded already, such as Influential Paper Award this morning, if you remember. The way it's going to work is that we're going to show the awards, say for the distinguished papers, and we'll ask the people who got them to stand up so that we can see who they are, and then we will clap the people, and then they can sit down. And if they want to get the certificates, we do have them here, and Charles and I and Shriram will stay around, and afterwards you can come, we can take photos, we can do anything that you like, but we won't be doing the walking around. Does it make sense? Okay? So excellent. So without any further ado, the first award we'd like to mention was the Doctoral Symposium Award that was already awarded to Amanda Zhu from the University of Wisconsin-Madison as part of the SPLASH Doctoral Symposium early in the week. It's a John Lycides Sickplan Award. So is Amanda here? Yeah, there we go. Thank you. The next set of awards is also for students. We do students first. Is our student research competition results. As you know, it ran over the past several days. We have both graduate and undergraduate categories. So would the graduate category students please stand up if you won one of the 3 awards? Are you here? Please stand up. Yes, that's right. Thank you very much. And thank you, congratulations. And now would the undergraduate category winners please stand up so that we can see who you are and find you later. Oh, yay. Congratulations. Thank you very much. And we now talk through, you already know, Wu Le, I don't need to get them to stand up, you saw them in the morning. Cheng Dan and Zhendong won the award. Onward authors are not here, unfortunately, so we already searched for them, and I'm just letting you know that this year they had 2 awards because they couldn't decide which one, to the 2 papers from Onward 2015, good, same as OOPSLA alignment for the most influential papers. So they will see it on the recording, we just clap for them. And now for the remaining awards with OOPSLA. These were the 6, just 6, distinguished paper awards for OOPSLA papers that we had. So are the authors here? Can you please stand up so that we can see who you are? Yes, yay! Congratulations. And they were already announced, I believe, on the website, so people would have been aware. Now, this is now getting to the artifact, Distinguished Artifact Awards. As you can see, we do have quite a large package to distribute, so will be other authors here from the Distinguished Artifact Awards. Wow, so many. Congratulations. So you're aware of the people here. And then finally, we acknowledge both artifact reviewers and the distinguished reviewers. These are the people who were particularly identified as being really good at providing feedback. So any of the distinguished reviewers are here? Can you please stand up? Congratulations, thank you for your services. And well, that was the award session. And now for the interesting part, Sriram, come over here. So basically, some people may or may not be aware that SPLASH exists as a combination of events, of which OOPSLA is obviously one. Some people may be wondering how it works. For example, a question I sometimes get asked is, how do I get on an OOPSLA committee? We can answer that if you are interested, or any other questions you may have. Or maybe you have questions about rounds, and whether we should have 1 or 5, or however many rounds. We are here. Sriram and Sukyun are the 2PC chairs. They'll be with us. If you have any questions about other events, we have Stephen, who is the Onward Steering Committee chair, who is also here, or any other sub-events. The organizers, Charles and Ilya, are here, and I have to manage the communication with them at all times. So, you know, now and again I get messages and things like that. So, anyone, if you have any questions, just come up to the mics and ask us.
Okay, so here's what's going on. Normally the way these things go, there's a business meeting, and at the business meeting the chairs will put up a bunch of slides, and in the slides we will tell you we got this many papers, this many were accepted, this many were rejected, this many went round 1, this many went round 2, and nobody cares. And then somebody will say, oh, and then what about the different categories of topics? We got this many static analysis papers, this many testing papers, and then you say this many static analysis papers got accepted, this many testing papers got rejected. Okay, and then people are like, okay, this many people are from India, this many people are from USA, this many people are from China, and everyone's like, okay. And then are there any questions? And of course there are questions, right? Because there's, like, people will respond to whatever you show them. So if you say, well, they're like, well, you know, how did you count the people who are both in industry and in academia? And then there'll be like a 7-minute debate about this, and none of this means anything. It's a complete waste of time. Okay? So what we thought would be much more interesting is to actually have a conversation with the community. Now, at the end of the conference, there's going to be a survey, and we ask you to please fill out the survey. We learn a lot from the survey, right? And if you have criticisms of us, you can criticize us too at the survey. But there's not an opportunity for a back and forth. Like, you submit a survey, it goes into a black hole, and who knows what happens. Right? So we're trying something completely new. There are no slides from the chairs. There's no presentation. We're just here to answer questions, and you can ask us all the questions that you have about the conference. In particular, there's a lot of students in the room, and you might be curious, how does any of this shit work? Okay? And we are happy to answer to the extent we possibly can. Okay? And I know at least, where's Max, by the way? Max New. Okay, at least Max New has a question to get us started off, so he can come and yell at us about something. And while Max is walking up, we want the rest of you to have some questions as well. Steve, I'm looking at you next. Yeah.
We do have some plants, and if necessary, we'll get like Jonathan.
Actually, he's not a plant, just so you know. Oh, Catherine has a question. Okay. Yeah, Max, go ahead.
Okay, Max New. Hello. Max New, University of Michigan. I have 2 questions. First of all, what was the breakdown of the papers by continent?
And secondly, how did you count the papers over 2 categories? Yeah.
Okay, but seriously, so I had a paper here, and the lead author on the paper is my student, and he was not able to leave for fear of not being able to get back into the country for visa issues. And well, okay, we didn't really want to do a virtual presentation or anything, so it's not about that, but just there was no official option to say that we could present at a different SIGPlan conference or the next year's conference or anything like that. And
if I didn't know better, I bet Alex wants to say something about this.
So my question is, could we improve this process and have some kind of official SIG plan policies, either at Splash or entirety of SIG plan, to address these kind of situations?
Great question. Go.
Can I answer? So, yes, I'm also happy to be on SIG plan executive, and we have a concept that we didn't exercise at this conference because of the numerous logistical problems and a lot of papers, but that will be done in 2026 because Frank has already confirmed that we are doing it, which is called SIG plan track. We have tried this before, and at the next SC chairs meeting for the 4 main conferences, the POPL, PLDI, ICFP, and SPLASH, it will be officially discussed to confirm. The idea being is very straightforward. If you haven't physically presented your paper in the last, let's say, year or so of the SIG plan events, you obviously got it published. It goes into proceedings of the ACM, and you will be able to come to any of the other 4 and submit proposal for your talk, and subject to logistical issues, not the actual research issues, we will try to accommodate it, because as a general chair, why would you say no to somebody coming in, paying a registration and attending your conference, to be honest, as long as you can accommodate the actual presentation. It is actually separate conversation we can have about runs and other things, but SIG plan track is coming, and we will try to do it across conferences. Next year, there are general chairs here, actually, except for ICFP for PLDI, Evan, and Sandrine, you're here maybe for POPL, and so you can ask them in person as well.
Okay. Happening across SIG plan?
Which Andrew needs to organize, where all of the 4 SC chairs need to actually officially agree on it. We've been pushing for it actually for a little while, because I've been pushing it ever since we sort of started moving to like New Zealand and other places. And we haven't got the agreement confirmed by all SCs, but Splash SC was always one of the more friendly to that one, if that makes sense. Yep. So for context, for people who don't
know about this, for context, there was a SIG plan track added after COVID. So all the conferences are very friendly about travel difficulties after COVID, and it sort of disappeared because it was sort of, I guess, deemed not as important anymore. One could argue about that, it doesn't matter. What I would say is people who think this is a valuable thing should take it up actually with the SIG plan leadership. As Alex said, I think Splash has always been more open to this than maybe some of the other venues. And so I think people who think this is important, write to SIG plan leadership and say this is a thing that's important to us as SIG plan members, because the more community pressure there is, the less choice they'll have about it. Right now, what Alex is saying is, well, you know, the next year's POPL chair is here, next year's so-and-so's chair, but that's not an institute, as you have correctly identified, that is not an institutional statement. And I think SIG plan should think about making it an institutional one.
Okay, thank you.
So I'm going to make a few comments about the review process, and then I will get to a question. So I'm Catherine McKinley from Google. So previously, Sriram, you can't run away. This is for you and Young. So in the very, very long ago, when we used to have in-person program committees, one of the purposes of those committee meetings was to vet the papers more broadly. So it wasn't just about the 3 people who read the paper making the decision. And so then things like missing related work, or I read a very similar paper, maybe by the same authors, maybe by different authors, and in our quest to be more efficient and make the process better, we've decided to have fewer in-person meetings. We don't have those anymore. And so the community aspect of looking at papers has declined a lot in the current structure. So how can we get some of that back? Because I think science is a community process, and if you don't get the perfect expert and you're not getting those extra eyes on the paper that we have, hurt the process. And Could we do something like use LLMs to say, if you were writing this paper, what related work would you cite, and make sure that, that some of the previous work is cited correctly for the people who aren't experts? So the seriousest topic is we can't have an expert on every paper. We have a new process where we don't get a bunch of eyes on every paper. What can we do to improve the science and the quality of reviews with the tools that we have now?
I guess anyone can start. So we had this proposal. Is it either OOPSLA or PLDI? I'm confused. I'm in both of them. So someone proposed to use LLM to have some first, filtering. But most of the SC members did not like that idea. And about this in-person PC meeting, thank you.
I didn't suggest they do the first filtering. I suggest that they create a related work section, which is a little different.
Because
right?
they've never been known to hallucinate a paper, so at least that won't be a problem. Yeah.
So we cannot say the details, but we had many instances both with authors and reviewers related to LLMs.
Right.
Right. So I think it's a really serious problem.
So I think, Catherine, your question is an excellent one, right? You're basically, people like us grew up in a generation where there was a PC of 12 people, and we all flew to some place, and we spent 2 days arguing about every one of the 83 papers, and it was awesome, right? It was an amazing educational experience for us and everything else. And we're now dealing with about 600 papers, and just the math of it suggests we have to have about 100 reviewers just because there's only so many reviewing units. And I don't think it is, I think we have to just assume that that is not the thing that is going to happen anymore. And other events like Onward didn't have a live PC, but an event like Onward that has 52 papers can have a completely different process, just as we do not have the same process as NeurEPS does with 17,000 papers, right? And each level of scale is going to have a completely different process. So I think we tried as much as one could to try to get experts and non-experts. In fact, like I believe very strongly that people get really worked up about non-expert reviewers for a paper. I think it is super healthy to have non-expert, like not all three, that would be pretty bad, but it's great to have one non-expert reviewer on a paper, because for two things. One, it's going to make the paper more accessible. It's going to force it into at least like 2 readable pages before it dives into the depths. And the other thing it's going to do is it's going to spot like bullshit. Right? Like somebody's going to be like, I don't understand this, none of this makes any sense, and it's also going to spot scientific fraud if that happens. If you have like a reviewer click, somebody's going to be like, I'm not part of this click, something shady is going on here, right? So we did not actually work that hard to have only expert reviewers, right? We didn't tip the scale too much. We tried to make sure there was some expertise, but not full expertise. The business about community communication is, I think it's unfortunate, and I have to say this, is like when you have 100+ reviewers, you do not know them personally and you can't hold them accountable, right? So like the chair's job is a very different one in this era, where it's like try to do the best you can. Now we had some astoundingly great reviewers, and we had like many, 7 of whom happened to be called out, but we had many more than that. There were lots of astoundingly great reviewers, but not all of them, and there was no accountability. Like, I think there are reviewers, we didn't know who some of them were. I mean, like, you know, we have a process by which we put people on a RC, but we don't know 120 people really well. So I think this is a great question. I'm just not going to come up with a great answer, because I think we are just dealing with a different kind of thing than the thing you and I are thinking about and that we grew up with.
Well, you can't do that because of scale.
Yeah.
So how do you create a process that protects against some of the abuses of scale and the problems with scale, so that we as a community have high quality work and we publish high quality?
So one thing we can do is monitor reviews intently, and we did that. Okay, I think like just about every review got read by us, and that's like we're talking hundreds and hundreds of reviews, right?
So
and
thank you, but that's
well,
not
no, I mean that's our
scalable
job.
either.
That's our job. And
Right?
I think the greatest thing about SIGPLAN is the quality of reviewing. It is the single greatest thing about this community, that this many people are willing to do this much work trying to do the best possible job they can. When we sent out review invitations, okay, Alex wants me to shut up, so okay.
I just want to point out that we have used area or now associate chairs for a while. It's almost a requirement to have a person dedicated to 50 to 1 paper ratio to help the RC chairs to monitor both the quality of the reviews and the chasing of timeliness. It's still in place. Plus, we currently have the OOPSLA steering committee, which is us who were the previous recent RC chairs, working through some of the quirks, improving the process. We do it every time, addressing the scalability issues. We are hitting high numbers, not 1,000 yet, but almost.
The AE does, but you know, part of our invite for those of you who are on the RC, the opening thing in the invitation was SIGPLAN has an amazing review culture and we're inviting you to be a part of it and to help us sustain it. And we kept coming back to the culture point, right? So I think there are things like that, reminding people of culture, bringing them into the culture, and then monitoring, and of course the AEs are a significant part of it as well. Some of us have been AEs for other people in this room, and other people have been AEs for us. So I think like that is a means of trying to address scale that's not the same as what you're asking for, but you know, I think it's a great conversation. We should continue the conversation offline.
We should, as a community, continue thinking
Yeah.
about how we scale.
Completely agreed.
And with high quality.
Completely agreed.
Could I just say something because it's relevant to this? So Catherine, I agree with your comments completely, and I really miss the in-person PC meetings. What I did when I chaired POPL is I tried to run a Zoom meeting. It ran across 3 different time zones, so that worked for Europe, US, and Asia. And basically either US, Europe were there, or US, Asia were there, or the other. You know, so we did it that way. It really does help. When Jan and I ran OOPSLA 22, we did it a little bit differently. We just took the papers that were more in contention and discussed those. But nonetheless, I think that we as a community for SIGPLAN, we need to see if we can make some version of that work. Because it's not just that it leads to better outcomes for the papers, there's also this matter of training junior people, right? When we were junior, we learned from the people in the room, the senior people in the room. First of all, we got to go there and perhaps impress them, but we also learned from them what the standards of the community were, and that's how they got passed down to us. And I don't know how we are passing them down exactly right now when it's only 3 people discussing each paper. So I would really love to see some version of Zoom PC meetings made to work. I think it can be made to work. It's just, it is a lot of work for the chair.
I
But
would
with
just
associate chairs, maybe it could
say,
scale.
I will just say, I don't think it's only 3 people and 3 people.
Yeah.
No, but I think this is an important clarification, right? It's not, no, it's not just like 3 reviewers just talking amongst themselves. There's 3 reviewers, there's an associate editor who's keeping track of things, and there are 2 chairs who are reading and actively participating. We've, between us, posted hundreds of messages, getting involved in lots of conversations. Perhaps the chagrin of some of the reviewers are like, could you people please shut up? But we did post a lot of messages and get interact, and part of that was exactly the cultural stuff, right? The cultural transmission. This is how we're going to do things, this is how we do things, etc. So there is some of that education happening. I think your work with the Zoom meetings was amazing. Everyone has raved about what a great job you did on sharing multiple things, and I think there's some learning there. Part of it is, I think SIGPLAN doesn't have very good like repositories of knowledge.
Yes.
Right?
Yeah.
And there's no place as a chair, I mean, like Alex wrote some notes, and there's something's in Dropbox, something's in Google Drive. ACM, the First Society of Information, doesn't know how to maintain a file. So, you know, like it's amazing. Yeah. So we have some technological problems as well that get in the way.
Yeah,
but what was your question and comment? Well, Amal, did you have something you want to say?
It wasn't a question, I just
that
wanted
was
to
just a
respond to
response.
that. 'Cause it
Thank
was-
you.
Sofia Drosopoulou from Imperial College. It's related to the question of the papers that are in contention. And a proposal that I had many years ago, I must say I didn't have the guts to put it through myself, but still I thought that it was a good proposal at the time, is that the papers that are in contention should not be judged in isolation, but with respect to the subject matter and the provenance. So I think that at the start of the deliberations, there is a set of papers that are definitely going through and a set of papers that are definitely not going through. But for the others, perhaps rather than try to decide for each of them, the 3 reviewers and perhaps the area chairs and so on, whether they are good in absolute, what they should decide is, from the pool of all these papers in contention, let's choose with the aim to have diversity in subject and diversity in authors. Kill me.
I think you should pass your comments along to next year's chairs and see what they think about it. This is luckily not our problem anymore.
But thanks for the suggestion, Sophia.
I mean, look, the area diversity is actually an interesting one. The author diversity runs into some very obvious problems, and I think you know exactly what they are. So. I think you should send this conversation over to the steering committee, and I think we should have that discussion in a broader context than
By the way, to clarify, yes, if you go to sicplan.org, you can navigate to SPLASH and figure out who is the chair of the appropriate steering committee, say POPL or OOPSLA or whatever, and do email them. Like, these emails are not ignored. So in SPLASH or OOPSLA case, you can email me.
Steve Blackburn, Google DeepMind. Very quick comment on that last conversation. I think that maintaining and establishing cultural norms is incredibly important, and that's what worries me most about the scale. End of comment. To the question that Trim asked me to ask. Yeah, look, unfortunately I only got to arrive here on Wednesday night, but I have so much enjoyed the fact that we're co-located with ICFP. There's so many conversations I've had. Yeah, there are.
Thanks, Ilya.
There are so many conversations I've had that I would not have had had we had not had that co-location. So my question is this: what's your perspective as the organisers between the 3 of you, and is this something that's going to happen again?
So SPLASH is open to help this happen. In fact, what happened in the past is just the right people in the right room happened to talk to each other to make this happen. But ICFP steering committee, some of whom are still around, but some have left, is interested to explore this further. It's not going to happen next year, obviously, because these things can take at least two years to plan. There is a serious consideration, but probably not 27, but they're really keen to look at coming back as long as people communicate clearly to the ICFP steering committee that they liked that, as well as our SPLASH attendees communicate to us to pass on to ICFP steering committee that they also enjoyed that. So that feedback is important, because otherwise people are just guessing what may happen. And I'm glad that people sort of enjoyed the collocation and have seen people from both areas.
It really strengthens our community.
That's right.
I think we should consider putting it on our final survey.
We will. Yeah. This is for, I guess, Charles and Ilya, technically, yes.
Yeah.
Hi, Harry Goldstein, University at Buffalo. So the cost and location of conferences like SPLASH and other SIGPLAN conferences varies tremendously from year to year. And I'm just wondering how possible would it be to know a little further than 1 year in advance for the purpose of long-term planning, you know, orders of magnitude of cost and things like that.
Yes, I actually know exact answers to those questions. Now, first thing about locations, the simple thing. We have realized our mistake, and there is now a coordinated spreadsheet to make sure that we are not 3 conferences in Europe, 3 conferences in Asia, 3 conferences in US.
Great.
So that is now being looked at by all of the steering committees. Regarding the cost, here is the thing. We were hit by COVID. Up until COVID, things were basically going great. We could model the conferences in hotels. The registration stayed $200 per day US for a full attendee for about 20 years without change. We didn't care about inflation. The interest rates were zero. Everyone was happy. Then COVID happened. There was a hiatus. Prices gone up a little bit in the last 25 years. So we kind of couldn't do 200 a day as we did in 2000, forget 2020, right? So we had to sort of scramble to fix things. The campus locations is something that sometimes saves money. So when I was a general chair for SPLASH'25, it was in New Zealand, it was on campus, in case anyone was there. ICFP next year, Sam is holding it on campus in Indiana University. These things are a little tricky because you need to fit it in either a break or the teaching sort of availability and things like that, which means the dates are affected. When it goes to a hotel, well, at that point, you pay the room rates that are higher, you pay the AV and other ridiculous things, which sometimes burn us badly, and like unexpected things happen. And these things are designed for professional sort of large-scale events. A typical budget of a conference in a hotel for sick plan is on the order of $500,000. Sometimes these things are a lot more, sometimes they're a lot less, but this is a current typical budget. Now, sick plan is different from many other SICs. We actually do a lot of things others don't do. We have PLMW, which is fully funded trip plus free registration that sick plan funds. We have PAC for professional activities that sick plan funds. We have covered article processing fees for those who couldn't pay it for a while. It's now changing, of course, but sick plan was funding up to now. We have quite a large, more than necessary amount of student volunteers in general so that we can actually support students coming. We require the authors of the paper to register as a student, if you like, not require a full registration to present a paper. In fact, you can pay no money, not come to conference, and still have it in PAC and PL that we will cover. The conference publishing and others have to be paid fees and all of that. We don't have the level of sponsorship that, say, my friends in robotics have, who said, well, yeah, our fees are low, but you know, we get 40 or 50% of our budget from sponsors. What's your percentage? It is not a 40 or 50% percentage. In fact, a lot of large companies have kind of pulled out from PL, and for example, our student research competition for 20 years was supported by some company, and after 20 years they said, nah, we can't afford it. So who picks up the tab? Sick plan. How does sick plan make money? There are two ways to make money. One is sick plan membership fee. We have 1,000 members for the last 20 years. It hasn't changed despite the number of submissions going up. It's $25, so we get $25,000 from sick plan membership fees every year. Everything else is whatever we make or loss on a conference. All of these things I've mentioned are covered by whether we make or loss on a conference. For a while, we were okay in 2010s. It is not a good picture ever since 2020. And doesn't matter what the numbers are, trust me, it's really bad. We're trying to get out from it, figuring out how to do it. It's a tough time right now. So any suggestions, please email the steering committees.
Yeah, Adam Chapala, MIT. I wanted to ask about your impressions watching the whole reviewing process, and in particular, multiple rounds of revision and reviewing, and just how all of this is getting calibrated across the reviewers and the authors. One caricatured impression I've gotten of a potential outcome at the moment is because the reviewers have some strongly held suggestions for presentation improvements. The paper should be presented 1 year later than otherwise, and it's just not obvious to me that that's the right equilibrium. And curious, what do you think about it?
I think that is an unfair caricature. Not only is it a caricature, it's an unfair and incorrect caricature. Okay. We did our very best to get papers not going over 1 year. In fact, we sort of actually, we did something to help authors even after the official second round deadline. We added an extra 1 week deadline just to get the papers that were close enough to the line over the wire. Okay, and we added another about 20 papers. There's at least about 20 papers here that got added that we just like burned the midnight oil to get those papers out of the queue. Okay, so I think that's not an accurate representation. In general, we monitored what was happening, and I think papers that were held over were generally for pretty reasonable reasons. But I don't think there's certainly neither a conscious effort to keep papers longer than necessary, like, oh, let's make sure every paper goes for a year. You notice there's no statistics here. There's no slide telling you how wonderfully competitive we were. We got yelled at for accepting too many papers, which we would not have gotten yelled at if we hadn't done things to get more papers over the line. So I don't think that's really what happened. I can understand that in individual cases, A, it may feel that way, B, it may even have happened in an individual case, but it did not happen collectively. Does that answer the question? Or I mean, there wasn't a question, so I don't have to answer it anyway.
Wait. The question is, what do you think about this second 2 rounds thingy? And I don't like it. Personally, I don't like it. There's so many rounds and it's so complex, too much work for the chairs and the reviewers. Reviewers are so overloaded. Yeah.
So one thing that is likely to happen from next year is we are likely to go back to a single round.
Actually, I'm going to dare do this. Can you raise your hand if you think we should have 1 round? And the second question will be if you want to have 2 rounds. So 2 questions. First, if you want to have 1 round, raise your hand.
I feel like the terminology gets overloaded. Are you talking about number of deadlines or number of reviews of a paper?
Okay, fine.
Sorry, it's an ill-defined question because we're talking about, like, is there a revision process, et cetera, et cetera. I think, okay, Alex wants a vote, we'll do a vote. Okay, so when we say 1 round, we mean the thing that happened, for example, between October and December, where you get a chance to resubmit the paper, but you don't get like a second new submission deadline, right? So there's only 1 time in the year when we do an intake of papers. 1 submission deadline in the year. Now those papers, there might be enough time to let the papers get revised and resubmitted and that sort of stuff. That all counts within 1 round. Okay, won't you vote?
I mean,
okay, I guess.
The problem is everyone uses round terminology to mean.
Well, we've just pinned it down.
This one.
So, okay. How many people want 1 round?
1 round with all of the revisions, of course, as part of that.
Oh, more people than I thought. Okay.
Okay. And no, the second question. It's impossible. Yeah, that's right.
Also just move on to the next question. Let's move on to the next question.
Email the steering committee chair with your thought, because we are currently having
Email the chair with your thoughts, thank you.
Because we actually have a working group right now, which is previous RC chairs for OOPSLA, working through exactly that problems and trying to figure out how we can improve our process. We have currently 2 rounds. In case you wondered, the one before now, we had the round 1 submission. That's what we call rounds. And then we'll have a round 2 submission in April. Right? That's what we meant by the 2 rounds. That's not the same as also figuring out how to do major revision and the conditional accept and going through many, many rounds of revision. Unfortunately, the same word, that's all. But yeah, we're working on it. Moving on. Yep.
Hello, Yanis Maragdakis, University of Athens and DDOB. So.
Whoa. Sorry? Yeah, 2 rounds. Oh, you want to vote? Okay, who wants to have 2 rounds as we have now, exactly as we have now? Oh, okay. Oh. Ooh.
How many of the people who vote for 2 rounds were on the review committee?
Oh, interesting.
Okay. Good.
Interesting.
Okay.
So actually, that is an interesting piece of data. We will include it in the survey. That's right. We will do it in the survey to get this. Yes.
Okay. First, I'll start with a comment that just arose while I was waiting in line. The ICFP and OOPSLA synergy. I also enjoyed having ICFP here the days before. 6 years ago, SIGPlan did run a questionnaire on whether some conferences could perhaps be co-located. ICFP and OOPSLA, if I remember correctly, had 5 people who actually said they would register for both. It was like an order of magnitude lower than the overlap between any other 2 SIGPlan conferences. So ICFP and OOPSLA are pretty disjoint sets, although when we meet, we enjoy each other. So let's keep that in mind. Let's not be so positive. When it works, it's fantastic. For people like me, it's fantastic. I met lots of people I know. So let's keep that in mind. Like the numbers do not favor a co-location of ICFP.
I'll just say were as opposed to are.
Sure, in 6 years, we all changed. Right. Yeah, so my main point though, so clearly, I'm a very cynical person, as you all know, so I come here and I attend all the OOPSLA sessions and I see paper after paper where I'm like, how did this get accepted? Of course, I don't see the stuff that got rejected. And
I've got my laptop. If you got some paper numbers, I can tell you.
Yeah, okay. That's not my point. In the time of overloaded review committees with multiple rounds, and many hundreds of submissions, and double-blind reviewing, where we have no idea who the authors are. I know that there's a lot of arbitrariness, and any 2 committees will come up with entirely different decisions. I'm perfectly fine with arbitrariness, but what I'd like to weed out is fraud, outright fraud, collusion, and I'd like to know what program chairs have done or will, or to encourage to do more in the future about policing outright fraud. Like someone gets a paper, they're reviewing it, they know who the authors are, and they have agreed to give them a good score, or any other kind of collusion. Is there a channel where someone can raise objections to such cases?
The good news is I'm just as cynical as you are. This will be a shock to you. So the point, no, but I bring this up because there are people I've known in the community who are appalled at even the suggestion that fraud could happen, who clearly don't know about, say, SIGACT and various other communities where things have happened. I think this is where things like the associate editors help, where having non-expert reviewers actually really helps, because those people are more likely to spot things that are going on. Right? Now, outright, like if somebody hides collusion well enough, like by definition, it's undetectable, right? I was actually expecting a slight variant of your question, so I'm going to answer the question I want to answer instead, which is basically a different problem, which is like LLM-generated stuff, okay? And we've had surprisingly little of it so far, which don't get ideas, people, just because you're hearing about this. We had relatively little of it on the paper side, and we had even less of it from what we could tell on the review side. There was one case where somebody thought their review was LLM written, and I reached out and it turned out like the author was just amazed to hear that was the way their review was characterized. And I even I'm not going to get into details here, but I made it very easy for them to say, oh, I see what happened. And I gave them a really easy out, and they didn't take the out. They're like, no, I really did write it. So I don't know. So we've seen relatively little of the LLM problem. I think we're aware of all the issues that happen, all of the frauds that happen. We're very deeply aware of the SIG-ARCH problem, for example. I think we've done the best we can to detect, but it's not certainly out of like naivete or like some amazing belief in humans. But we don't have great systematic ways.
I would mostly like to encourage a more systematic lifting of the double blind among the chairs. If there is a certain suspicion of a certain kind where someone says, hey, look, this is not making sense, check more. That's my point.
So just so I understand, can you just, for a simple brain like mine, can you just explain very concretely, the chairs do have access to the author's names anytime they want it? Yeah.
And they investigate, like, if someone raises a flag, is there an official channel for someone to raise a flag?
There's not an official channel that I'm aware of.
I mean, I'm not saying I have a solution. I'm just saying if we can come up with some process for that, it might be good, because at least it's probably not happening at all, but at least it will put the mind at ease.
There were other forms of bad behavior on the part of authors that the chairs did get actively involved in and like worked on correcting. And I will not say more about what those were.
But I'm just saying every year there is instances that happen.
As a clarification, I'm puzzled. Yanni, what you're proposing is that authors should have a way of complaining directly to the chairs, or that after a paper has been presented and you wonder how come it was
both, everything. Other reviewers.
Anybody should raise a concern about the paper, or what?
Other reviewers can raise concerns. Authors can raise concerns. Anything.
I mean,
Yannis, Hot CRP gives us a way to say good review, and both to the author and bad review, and needs work. And we can say that both as authors to the reviewers and as reviewers to other reviewers. And I suppose that the chairs do that unofficially through reading the reviews.
Come on. Come on. The good review is based on length of review.
Can we, Sukyung, okay.
We can take it offline, Yannis.
Okay. I think we've hit the point where this conversation is not being useful anymore. Let's move on to a new person, please.
Jean Pichon, Aarhus University. So there's a phenomenon that I've observed and that other colleagues have pointed out to me, that in this venue and other venues, be they online forums or other things, that when you raise a question or a query or you ask something, then you get referred to, oh, you should go to this other thing. So, maybe go to the the in-person meeting, maybe ask the steering committee. And I mean, to put it in unkind terms, I think some people get the impression that it's a bit of a pass-the-parcel game. I think to put it in fairer terms, I think people see it as disempowering, that they feel that the thing is sort of moving without progress. So is there a sort of a guideline, an official characterization of like, if you have query or complaint of type X, you should raise it to person Y or Z or venue Y or Z?
So it looks like we are not yet sure what kind of problems that would be, but usually it could be SIGPlan EC, I guess.
No, ACM has clear publication policies. They have also people that we can raise the issues, which we do with. They have processes that they follow and investigate incidents.
I think maybe there was a bit of a miscommunication. So things about, I think Gabriel Scherer wrote to the Types mailing list about holding conferences in the US or not in the US. And I think the answer was, oh, you should raise it as an in-person meeting. And then today, as people were raising questions at an in-person meeting, the answer that you were providing was, oh, you should ask the steering committee. And so there's a bit of a question like, well, what is like the limit of the sequence?
This is not a limited, there is a fixed point. My name is Alex.
So what is the fixed point? Tell me what the fixed point is.
The SIGPlan, where Ilya, myself, and a few people here are members of executive committee, we raise it in our meetings. The official communication by SIGPlan is at 2 meetings in Popl and PLDI in person, but they also discuss things offline. And these things include whether to locate conferences, I don't know, in New Zealand, not in New Zealand, and things like that come up as part of that. And then there is every, I think, 4 months or whatever, the meeting of the steering committee chairs that SIGPlan runs to pass that information down to the 4 main conferences, and that's how it propagates. So, for example, the rotation of locations is just, it doesn't happen instantly, right? Because it's 2 years out. That is now coordinated, and it was an issue raised by people who said, why are you all in, Asia in 1 year and things like that. So it's the same thing with this, US versus non-US. Well, maybe SIGPlan trackers an answer. It will be discussed at the next steering committee. It happens. That's how the process works. And if you want to communicate with SIGPlan, on sigplan.org it actually has the people, and we elect them, the 1,000 people who pay $25.
I'm one of them.
Get to vote who is going to do it for 3 years. I'm not sure how to answer it other than that's the process.
I would like to think we didn't refuse to answer a question this evening. What we said is if a lot of people feel this way, it helps to send mail to the steering committee to understand the strength of sentiment. And there's some like if you want further details, you can reach out. But okay, let me be really clear. If there's a question this evening we haven't answered, please ask it again, and I promise I will answer it. Go for it.
I think it was more a query about the process, because it feels kind of weird that it's like you have to take the next hop.
So
I think you've answered it in a satisfactory fashion. Thank you.
Yeah.
Hi. Hila Peleg, Technion. I think it's maybe a little too early to try to extrapolate from the number of submissions each one of the conferences gets as to whether our growth is linear or exponential or doubly so or whatnot. But I think it's been probably several conferences in a row where we get the email from the chair saying, oh, we've had way more submissions than we've been expecting. And each conference tends to handle it kind of in its own way, whether it's dumping more load on the review committee and whether it's threatening authors that they're going to have to review and then acting on it. Are there any plans to have a more structural thing, maybe in how the review committee is structured or something like that? Maybe get some ideas from other communities who've been dealing with scale longer, and maybe some of the communities that are dealing with it better rather than the ones that are dealing with it worse.
So it's related to the previous question. So we do have 4 conferences, right? And as Alex said before, to me, those 4 conferences were not talking to each other until now. And we do have the SIG Plan EC, and we are trying to answer those questions, but not well. So sorry that I was the SIG Plan EC member before. We didn't do the good job. But now that, as Alex said, we are collecting the data and we are going to share the list. We didn't even have a common list of keynote speakers over those 4 conferences. So there are many data that we are not using each other. So I think that's another question and another thing that we need to talk together. So thanks for the question, and we need to work on that.
Alex, do you mind also telling us how concerned we are about this as a community and as the EC person?
How concerned we are about coordination by the community?
No, I'm saying the growth of the number of submissions and
so
how hard
right now, PLDI is more or less stable at 350 or so. ICFP is at around 110-ish, kind of early hundreds, kind of. POPL is up to 380 now, but it's still not unusual. OOPSLA had a couple of hits. It went 400 when I was a PC chair, and then almost 600 now, and then it's larger than before coming up. We're afraid a little bit. It is something that we realize is a problem because the PCs are from the same SIG plan members. If you think about it, 120 PCs, that's 4 PCs, that's like half the SIG plan members, and you can't really serve all the time. The SC chairs meeting is the only way to sort of talk through that and keep updated. It is not happening as probably much as it needs to happen. If anything, we should probably meet more often. All I can say is that we are aware as the 4SC communities that this is a problem. We haven't fixed it yet.
I want to just add one more thing. I think our mortal fear when we agreed to chair is what happens if we get more submissions than we estimated for, and that's why we put the reserve reviewer policy in place, what you call threatening, that we threatened, and you can characterize it however you want, and it's no skin off my back. Call it what you like. And that was not arrived at completely independently. I actually had a discussion with colleagues in my department who represent several areas. I found out what ACL was doing. I found out what another community was doing. I studied, and then Sukyung and I discussed this quite a bit. And then we decided to come up with a particular policy based on all of that. So I think we're actually very aware of what other communities are doing. And we did it. And in fact, if you look at the blog post that we wrote on the SIG Plan blog explaining the reserve reviewer policy, it actually includes links to all of those other communities, including the 2024 versus 2025, to also show how they have changed, right? I think the problem here is nobody has great answers. It's not like there's an obvious correct answer and then like we just have a lack of information. The great thing about computer science is we keep experimenting with different formats. Should we have 1 round? Should we have 2 rounds? Should we call them rounds, call them something else? Are they conferences, journals? CS is just full of random experimentation and like some vaguely, evolutionary path. So I think all of us are trying to deal with scale are going to try different experiments, and maybe in 2 to 3 years it'll shake out. And some of the experiments may be terrible. They might have chairs threatening authors in various ways. Other people will come up with better experiments, and then we'll find a thing that works.
Just to be fair, I think the threatening was fairer than the conferences who've dumped extra work on the committee, so.
Thank you. So again, as Alex said, the 4 conferences SC chairs are now meeting, and so we are discussing, so hope for the best. Yes, Ben? Oh, didn't know that. Catherine?
So if you have ethical concerns, we have the CARES committee for informal discussions on what you might be suspecting is bad behavior, and then they can guide you to how to report different things that go wrong. And is that talk to the program chair if you're a reviewer, or if you're an author, or if something happens that's unethical, not just unwelcoming or harassment, because the community has had problems in the past, and ACM took very seriously now putting new policies in place and much better procedures for investigating things. But ultimately, ACM doesn't employ any of us, and reporting unethical behavior to each university or company is a very complicated process too. So what ACM can do is pull a paper, a paper from a conference, but as a scientist, if you're doing something completely unethical, your university or your company needs to be investigating it too. So ACM has a very limited stick for unethical behavior, and they are using it, but it's not, because they don't employ you, there's a limited amount they can do to people who aren't following the ethics of good science. But CARES is supposed to be there for you. So if you think something's not good, go talk to somebody who you trust who's on the CARES committee, and they can give you good advice for how to pursue whatever you think is not correct. And I encourage you very highly to do that.
Thank you. Okay, I want to take the 2 of you, but I also noticed we have not had a single student show up and ask a question. So I would encourage students to maybe consider, if you have a question, don't let us old fogies dominate. Giannis and I are going to be arguing for the next 20 years anyway, so. Yeah.
All right, so thank you for sparing us the boring slides before, but it would be nice if we could get those statistics maybe offline. I wanted to say something. So the best use of everyone's time here, I think, since we're in a community setting, is to be able to get feedback in bulk that's hard to get. So like, for example, having a vote like that, I think that's actually very instructive and very good use of our time. And I think what one of the previous questions was, people are suggesting things, and then there should be some discussion, but also they're kind of being cut off and said, go email these people. I think people are a little bit confused about what is the back and forth here. And I think if we could have a little bit more participation, and you're also curious about what we think about how things went. And so maybe you could also ask us and poll us and get a sentiment.
Ben, there's a whole survey that goes out at the end of the conference, okay? And that's going to get answered by hopefully everybody who attended. We have...
Okay, so I will do it. How many people have filled out a survey before?
Good, thank you.
That is good.
All right, yeah, okay. Thanks. Even if you didn't, thanks for raising your hand. Okay. Ben, I just want to point out, first of all, we have a total of 40 minutes for this session, and I'm mindful of the fact we're actually at our time limit, okay? So part of the reason we've been trying to go through this quickly is, first of all, we've never done anything like this before that I know of. We're trying to figure this out as we go along. And secondly, I'm very mindful that I want to let people get out roughly on time. So that's part of the reason we're trying to get more people to comment and get the feedback and understand what's going on. and maybe not go into every single thing back and forth because then we'll never get the next person. That's one of the reasons you're seeing. Thank you.
So I'm returning to an earlier topic. Alex, you mentioned when we were talking about budgets, surprise, you mentioned when we were talking about budgets that we had conferences, we had the pandemic, and then after the pandemic we started going in the hole. That doesn't entirely line up with my understanding of the timeline. I thought the 2022 immediately post-pandemic conferences actually were still doing reasonably well.
No, 2020 onwards, most of them made a loss.
Okay.
And more recently, like last year, every single one made a loss. Big loss.
We've made other changes since the pandemic other than existing in the world since the pandemic. Has there been any sort of systematic ways in which we run our conferences that had a distinct discontinuity that we could look at?
Sorry, what's the discontinuity?
I don't know. That's what I was asking.
Well, as far as I can tell, it was a combination of basically luck or circumstances we couldn't control to an extent where we were making decisions and committing ourselves, and then kind of stuck in contracts that sometimes worked to pull out, some didn't, and people kind of stopped looking, if that makes sense, to like how the conferences were organized. And then we went back to normal after 2 years, hiatus, and people kind of forgot how they used to run the conferences before COVID and started sort of, like that's my understanding, making decisions and things like that. Well, it's maybe an offline thing to discuss, but...
this is exactly what's going to piss off people.
Yeah,
okay, let me give you two quick answers, okay? Sure. One is the corporate world changed significantly, right? ZERP ended and like all kinds of things changed about how corporate sponsorship and things like that work. The other is there were significant personnel changes. Now, I hope you will recognize that we don't want to talk about every detail in public, but there were significant personal changes. Annabelle Satin, who many of us know, Annabelle no longer works with us. And so there's been an entire learning process, and all those years Annabelle learned to optimize our events. All that knowledge was lost. Does that compute as a cause?
That sounds like a discontinuity.
Yeah, and so there's like a whole new learning about how the contracting works in a new regime. So even Annabelle may have had all sorts of struggles in the new regime, but we had a new regime and a whole new set of people, and that combination has caused some difficulties that we're trying to work out now, and a lot of learning has happened.
Great.
Good. Really quick. Okay, tell you what. Here's the thing. It's now 6:30. Anybody who wants to leave is welcome to, I mean, you've always been welcome to leave. Some of you walked out already. You're always welcome to leave. You're not actually hostage or anything like that. But we'll stick around and answer questions. I'll stick around and answer questions for people who want to ask questions.
If you want to take a photo, though, with the certificate.
Go outside. Yeah, there's a photo
Charles
booth or something.
Is the general chair and has all the certificates.
So we're gonna, me and the SRC chair and the artifact chair will be standing outside if you want to get your certificate. And leave will be outside.
So anyone who is here was just waiting for the photos and the certificates, there they are. You can come out. The photographer, Philip, maybe you can come with them, and we will basically do everything that you wanted in terms of obtaining the certificate. But anyone who wants to carry on the discussion,
go ahead.
Should I ask now or wait?
Just wait for...
Yeah.
Go for it.
All right, so well, here's a student question since you wanted one.
Yes.
There were two different paper submission portals, one for the main reviewing version and one for the camera-ready version. I think this was the first time this has happened, but well, is the plan to integrate those two eventually, or just to switch entirely to using one of the two, or?
No. So for those of you who are not familiar with the process, so basically there's the hot crap is how the reviewers, the program committee deals with the paper, okay? There's a company that gets hired to do the final processing of the paper. And that company has its own mechanism because it has a completely different set of concerns. They are not in the review process, they are more in the production process, and that is a completely different set of software and a different set of concerns. It's not actually a new thing. It's always been the case that the people who handle the final paper tend to be a little different from the people, like there was a company called Sheridan Printing, there's another company called Aptara, there's a company called Conference Publishing. They're all different entities that tend to have their own somewhat different processes. So it's not a completely new thing, and I don't think that will change. We may have been bad at giving instructions. That's always a possibility. We probably were. But the fact that there are two different things is because there are two different processes. One is a review and decision-making process. The other is the actual printing publication process. Does that make sense?
Yes, thank you.
Thank you. Next.
Hi, Jeremy, Rochester Institute of Technology. I'm a new PhD student. People may have left who are relevant to hear this based on previous discussions, but having just come for PLMW at a joint conference, it was particularly effective, I think, at exposing me to a lot of new topics and things. So I think that was particularly good of having the co-located conferences. But my question is, I've been perusing the SIGPlan website and so on, and I think there's a lot of things that are really well documented in terms of policies. I mean, relatively speaking, that there's policies and guidance and everything. Maybe it's somewhere deep in the bylaws that I didn't read, but I don't understand financially, how does the organization work as sort of an international thing?
You're asking about ACM, I guess, rather than SIGPlan. So SIGPlan is one small part of a bigger organization called Association for Computing Machinery. Now, that organization existed since 1960-something, I guess, a while. And we do have some people from the higher up in it, but they've just left. There was a couple from publication board. And it makes sure the SIGs exist, right? Now, special interest groups are then going to be grouped in things like ours, which is SIGPlan, and as well as others. Now, what it used to do as a massive thing for a while was the digital library in the last several decades, which is the one you go to and you look at the papers and you read them. And they had, or
yeah, I think I understand what ACM is. I mean, that was clarifying a little bit, but yeah, I mean, and if you don't think it's a valuable thing to talk about, that's fine, but
what's the financial thing? Because, I mean, for example, the reason that we run the conferences is for us to have the way to sort of meet and to you know, communicate and publish our results. Now, when we run them, the HQ, if you like, of the ACM is the ones who do the actual like invoices or pay people, right? So, I mean, it's not an organization that's out there to make a lot of money. Yeah. This is us. So that's what the bylaws discuss. So I'm not sure.
Okay. I think you're okay. My guess is that your question is from the SIGPlan webpage. It is difficult for you to understand the financial running of this entity. Yes. I think that's your question, right? So for example, you would like to know, for example, where does the money go? What is the money spent on? How much revenue does SIGPlan get in a year and how much does it spend in a year? That would be an example of a thing that would have helped you? Yeah. Okay, Alex, can you find that information on the SIGPlan page?
It's not on a web page, but SIGPlan in 1 year, the turnover is around $2.5 or $3 million, which is mostly from the conferences that we run. And that basically balances out almost evenly with a particular percentage mandated to be given to ACM to run the rest of it, which they change depending on their basically costs. And that's all we do. We just report numbers.
I think the answer to your question is you are correct that you are unable to find it even though there's other things documented, because what Alex has confirmed is that information's not on the webpage. I don't think it's a desire to be private. I think it's just more it hasn't happened. And I hesitate to say this because I'm going to get flamed again, but you might consider writing to Alex and saying, could you put this information on the webpage because I would like to see it, because frankly, so would I. So maybe you and I will both write to Alex.
If we're allowed.
Yeah, there may be some question about whether we're allowed. It seems weird as a nonprofit that it wouldn't be allowed, but there may be something. But I think you're right. I think it's a good idea for SIGPlan to make clear where's the money coming from, where's it going.
Hi, I'm Purva. I'm a student at UCLA. So I guess my question is more of a comment around the artifact evaluation and how it works with the main track. So it's relevant for this OOPSLA, it's relevant for all 4 conferences in general. It has always, not always, my experience has been that artifact submission deadline is before the final, quote unquote, final deadline, which kind of forces us to divide our attention. So would it be possible to experiment with having artifact submission deadline after the revision deadline? Yeah.
So, as the inventor of artifact evaluation, I have some strong opinions on this matter, and therefore I'm probably not the most qualified person to talk about it. But first of all, I have two comments on this. First is we have to have the artifact evaluation process done before the final paper, before the the eventual paper, because of the badging. Okay, but the goal of artifact evaluation is not first you write the paper and then you think about oh, maybe we should actually make the data public to somebody, right? The whole goal has always been you should be doing your research in a sufficiently responsible way that if somebody wanted to read it, they could read it and they could make sense out of your thing, right? Every now and then there are reviewers who say, I don't actually trust the data in this paper. I mean, not even trust, it's not like you lied, but I think maybe you have a performance improvement at 10%. It might be explicable by this instead of that. I would like to be able to run it myself and see whether that is true. Okay? It would be.
I think she's not talking about the camera-ready deadline. I think she's talking about the deadline for revisions when you're conditionally accepted.
Yes, because sometimes in those conditional accept requirements, there are changes required, the reviewers have asked changes in experiments, slight changes in the experiments, which requires a need to update the artifact. And now, if I need to submit the artifact and my paper is not ready, so how do I submit these?
Here's what happened.
Yes.
There's a very easy solution to this problem, which we chose not to use, and we chose to accept a much messier solution. The very easy solution is only papers that have already been accepted can submit for artifact evaluation.
Okay.
Okay? Then you agree there's no problem.
There is still a problem.
What's the problem?
And it's probably not an OOPSLA specific problem, because in other conferences where you don't have the major revision or minor revision, they might still choose conditional accept because the changes in experiments are not.
Yeah, but I'm saying once the paper's in accept status, only papers in accept status can submit an artifact.
Are you saying conditional accept or accept?
No, accept. Accept.
Okay.
Accept. Do you agree that if you're only accepted papers can submit an artifact? We agree there's no problem.
Yes.
Okay.
Agreed.
If we had done that, a whole bunch of people would not have been able to get artifact badging this year. Okay? So we had to make a compromise. The compromise we made is we said we will also allow conditional accept papers, knowing full well that there is this problem of these things are going to be changing, and we said therefore you can resubmit your artifact near the end of the artifact evaluation pipeline dates so that you can get the last final thing reevaluated. That was a compromise to enable more authors to get artifact evaluation. If we had not done that compromise, anybody who got a conditional accept would not, in fact, it would kind of have leaked the status of a lot of papers because why does this paper obviously has an artifact and has no badges? Well, it must have not been accepted as a regular accept. Okay, so we were trying to make it easier for more not easier, we were trying to make it possible for more authors to get artifact badging with the way the dates line up, and this is one of the difficulties of having 2 review rounds, is there's just not enough time. Okay, it would have been great to finish all of this and then start that. There was literally no way of doing that with the timeline. That's why we chose to make this compromise, and any author who didn't want to participate didn't have to participate. We were giving authors a choice. And I think we even sent mail explaining this what's happening, but maybe we didn't. I can't remember. Yeah.
Okay.
Does that make sense?
Yes.
Yeah, it's a compromise to try to make a bunch of difficult to reconcile things somehow badly fit together as opposed to not fit together at all.
Okay.
Yeah. Karine? Let's move on to more questions. Yeah, okay. Next question over there, please. Go ahead.
Hi, Amanda Liu, student at MIT. I was wondering, lately to my chagrin, I've been reading a lot of machine learning venue papers, and something that I found actually kind of interesting, educational, and just kind of piqued my interest is the open review structure. And one thing that you talked about is just the quality of reviews in this community, and I definitely agree. And even reading the reviews for my own papers, I've learned a lot. And so I was wondering, what are your thoughts on implementing something like that?
I'll let Sukyung speak for herself because I think each of us has to speak for ourselves. I think it's kind of an interesting culture. I don't think it is SIGPLAN's culture, and it would take like a significant cultural shift to move to that model. I think part of the problem is at least people who are not used to the model would find it very uncomfortable. That doesn't mean it's necessarily a bad thing, it's just a different thing. And I think it's got some strengths, it's got some weaknesses. It just seems hard to move, from one fixed point to another fixed point, and it's a very distant fixed point. In a way, I guess it seems like the kind of thing that maybe we should have a conversation about, but certainly I hear no attempt to have a conversation about it because nobody seems to be clamoring for it inside SIGPLAN. And I know that's not much of an answer, but I don't, I've thought about it, we talked about it a little bit when we were chairs, like, should we do open reviews? Like, I think it would be like, if 2 chairs tried to change it, it would be like a massive revolution and people would yell at us even more than they're yelling at us tonight. So it would take some effort. It might be an experiment somebody to consider. Yeah. We thought about it and we decided we had enough to do and didn't want to take it on. Yeah, I mean, I will say that I'm not saying it's an equivalent or substitute for it, but artifact evaluation tends to have a little bit of that flavor. Artifact evaluators are always students, and so they do get some sense of what the review process looks like and what it's like to be participating in a program committee of some sort. It's not the same as program reviewing, but it is a way to bring students into the mix a little bit more. It's not the same as a shadow PC, but it actually gives them more teeth than a shadow PC does. I know, I'm not unaware, I'm aware of that, yes. I'm saying that there's something we do that they don't, and there's something they do we don't, and some chair with more time and energy should try to think about doing that. Yeah.
So you spoke a bit about how the artifact is like a culture thing where you really care that the artifact is somehow useful for somebody else to reproduce. What do you think about making sure that this is tied to the decision of the paper? And this has been the perennial question from day one. When artifact evaluation was invented, people were appalled at the idea this might happen because that would mean fewer papers would be accepted. And so the mechanism was designed purposely to say, no, don't worry, your wonderful papers will be accepted whether the artifact works or not. What has always been left unstated is what happens if an artifact evaluation comes back and says, actually there's nothing here, this is all complete garbage. Right? But I think there is actually a mechanism for that, which is that it is a journal and we do have, ACM Digital Library has policies. So in principle, if the artifact this paper is complete like nothing here is true, it's all lies, right? And if we were to converse with the authors, we could use that as an argument to make a fraud case against the paper and try to have the paper be pulled from the digital library. So there is actually a mechanism for pulling that off. So in a way, it's kind of like maybe the best of both worlds. We don't have to, because otherwise like that timing and everything gets so much more complicated. And so maybe it's not a bad compromise, given that the digital library has a mechanism for pulling papers. And maybe we should make that clearer to authors so that they realize, oh shit, this could happen. Please.
Yeah.
Thank you.
Shut up, please.